Hey everyone! Tonight we begin with one of humanity's oldest and most persistent dreams, the idea that death might not be the final chapter of our story after all. Before we get started, take a moment to like this video and subscribe, but only if you truly enjoy these calming explorations of science's most profound mysteries. And let me know in the comments where you're listening from, and what time it is for you right now. I love seeing our global circle of listeners from so many places and time zones, all pondering the same ancient questions about mortality and what lies beyond. So find your most comfortable position, perhaps dim the lights a little, and let your mind wander with me into territories where science fiction is rapidly becoming science fact. Tonight, we're exploring why some of the brightest researchers on Earth believe we might be living in the last generation that has to accept death as inevitable. Death seems like the most fundamental fact of existence. Every living thing that has ever existed has eventually stopped existing. Every person you've ever known will someday be gone. Every pet, every plant in your garden, every tree in the forest outside your window. It's the great equalizer, the final period at the end of every life sentence. But hold that thought gently, because, as it turns out, even something as seemingly absolute as mortality is much more negotiable than our ancestors ever imagined. Let's start with the most curious fact about human psychology and death. We are, as far as we know, the only species that spend significant mental energy contemplating our own eventual non-existence. A rabbit doesn't lie awake at night wondering if there's anything after the final heartbeat. Your cat doesn't seem troubled by existential dread about the brevity of feline life. But humans have been obsessing over death and how to avoid it since we first developed the cognitive capacity to understand that we, too, would someday cease to be. This obsession has given birth to some of the most compelling stories ever told. Think about it for a moment. Nearly every culture that has ever existed has created myths about immortality, about ways to cheat death, about beings who live forever. It's as though our species has been collectively working on the same problem for thousands of years, turning it over and over in our minds, exploring it through story and legend and dream. The ancient Mesopotamians told the Epic of Gilgamesh, where the hero king searches desperately for the secret of eternal life after witnessing the death of his beloved friend Enkidu. He travels to the ends of the earth, faces impossible trials, and ultimately discovers a plant that grants immortality, only to have it stolen by a serpent while he sleeps. The story is nearly 4,000 years old, and yet it captures something so fundamentally human about our relationship with mortality that it still resonates today. The Greeks gave us Tithonus, the mortal man who was granted immortality by the gods, but forgot to ask for eternal youth. He lived forever, but continued aging, eventually becoming so ancient and decrepit that he begged for death. It's a cautionary tale, but notice that even the caution assumes immortality is possible. It's just a matter of getting the details right. Norse mythology speaks of the gods themselves living in constant fear of Ragnarok, the twilight of the gods, the end of everything. Even beings of immense power and longevity are not truly immortal in the Norse worldview, and yet the stories are filled with attempts to delay or prevent this cosmic death, with magical apples that grant extended life and heroes who dare to challenge fate itself. The vampire myth, which has captivated human imagination for centuries, is perhaps the most psychologically complex exploration of immortality in folklore. Consider what the vampire represents. It's a being that has achieved the thing humans want most, eternal life, but at a terrible cost. The vampire must prey upon the living, must exist in shadow, must sacrifice human connection and warmth and the simple pleasures of mortal existence. Its immortality is a curse rather than a blessing. But here's what's fascinating about vampire mythology. Despite all the horror, despite all the obvious downsides, vampires in stories are rarely portrayed as truly wanting to die. Even in their cursed state, they choose existence over non-existence. This tells us something profound about the human psyche. We find eternal life appealing even when it comes with terrible conditions attached. Modern vampire stories have evolved to explore this psychological territory even more deeply. Interview with a Vampire presents us with Louis, a vampire who is deeply troubled by his immortal condition, who mourns his lost humanity, who suffers existential anguish about his eternal existence. And yet, when given opportunities to end his immortal life, he hesitates. He continues to exist. There's something in the vampire narrative that acknowledges how difficult it would actually be to choose non-existence, even when existence has become painful. What these stories reveal is that humans have always intuited something that modern science is only now beginning to confirm. Death is not necessarily inevitable. It's not written into the fundamental laws of physics. It's more like a biological habit, a pattern that life has fallen into, rather than an absolute requirement of existence. Every culture has also developed its own theories about why death exists in the first place. Some see it as punishment, a consequence of disobedience or moral failing. The biblical story of the Garden of Eden suggests that humans were originally immortal and that death entered the world through sin. This narrative implies that mortality is not our natural state, that we were meant to live forever. Other cultures view death as part of a cycle, necessary for renewal and rebirth. Hindu and Buddhist traditions speak of the wheel of samsara, the endless cycle of death and rebirth, where individual death is not the end, but rather a transition to a new form of existence. In these traditions, the goal is not to avoid death, but to escape the cycle entirely, to achieve a state of being that transcends both life and death. Indigenous cultures often see death as a return to the land, to the ancestors, to the spiritual realm from which we came. Death becomes not an ending, but a homecoming, a rejoining with the larger web of existence. These traditions tend to view the fear of death as a kind of spiritual immaturity, a failure to understand our proper place in the cosmic order. But here's what's remarkable about all these different cultural approaches to mortality. Whether death is seen as punishment, transition, or return, nearly every tradition also includes stories about beings who have managed to transcend it. There are always the immortals, the undying ones, the figures who have somehow stepped outside the normal pattern of birth, aging, and death. Chinese mythology speaks of the eight immortals, Taoist figures who achieved eternal life through spiritual cultivation and alchemical practices. These aren't gods in the Western sense, but rather humans who discovered the secret of transcending mortality through wisdom and discipline. The implication is that immortality is achievable, that it's a skill or state of being that can be learned and mastered. Celtic folklore is filled with references to the otherworld, a realm where time moves differently, where beings live for centuries or millennia without aging. The Tuatha Dé Danann, the mythical people of Ireland, are said to possess immortality, not through magic but as their natural state of being. Humans occasionally glimpse this other world or even travel there, sometimes returning to find that decades have passed in what seem like days, or discovering that they themselves have been touched by immortal time. Hindu traditions speak of the Chiranjeevi, the seven immortals who are said to still be alive somewhere in the world, having transcended death through various means, spiritual achievement, divine blessing, or special circumstances. The suggestion is that these individuals walk among us still, indistinguishable from mortals but carrying within themselves the secret of eternal existence. What's fascinating is how specific and detailed these immortality myths tend to be. They're not vague promises of life after death or abstract spiritual concepts. They describe particular methods, specific practices, identifiable individuals who have actually achieved what the rest of us can only dream about. It's as though our ancestors were conducting thought experiments about immortality, working out the practical details of what it might actually be like to live forever. The alchemical traditions of medieval Europe were explicitly focused on discovering the Philosopher's Stone, which was believed to grant not just the ability to transmute base metals into gold, but also to confer immortality upon its possessor. The greatest alchemists, figures like Nicolas Flamel, were rumoured to have actually succeeded in creating the stone and achieving eternal life. Flamel in particular is said to have lived for centuries beyond his supposed death date, using his alchemical knowledge to maintain his youth and vitality. These weren't considered fantasy stories by the people who told them. They were treated as historical accounts, as real possibilities, as goals worth dedicating entire lifetimes to pursuing. The medieval alchemists weren't just mixing chemicals in hopes of making gold. They were conducting what they believed to be rigorous scientific research into the nature of life and death, convinced that mortality was a problem that could be solved through sufficient knowledge and skill. The Renaissance brought us figures like Paracelsus, who declared that death was not natural but rather a disease that could be cured through proper medicine. He wrote extensively about life extension, about methods for maintaining youth and vitality indefinitely. His ideas influenced generations of physicians and natural philosophers who approached aging and death as medical problems rather than metaphysical inevitabilities. Even the scientific revolution didn't immediately dispel these ideas. Isaac Newton spent as much time studying alchemy as he did developing the laws of motion and gravitation. He was convinced that the secrets of immortality were hidden in ancient texts and chemical processes, waiting to be rediscovered through careful experimentation. His private papers reveal an obsession with life extension that rivals his passion for understanding planetary motion. The point is that some of the greatest minds in human history have taken immortality seriously as a scientific possibility, rather than a mere fantasy. They understood something that we're only now rediscovering. The assumption that death is inevitable might be the biggest assumption we've ever made, and it might be completely wrong. But here's where things get really interesting. While our ancestors were creating myths and legends about immortality, nature was quietly conducting its own experiments with eternal life. It turns out that death, far from being a universal law of biology, is actually a relatively recent evolutionary innovation. For the first several billion years of life on Earth, nothing died of old age. Let's take a closer look at this remarkable fact. The earliest forms of life were essentially immortal. Single-celled organisms like bacteria don't age in the way that multicellular creatures do. A bacterial cell can divide indefinitely, with each new generation being essentially identical to the previous one. From the perspective of the individual cell, this is a form of immortality. The original cell continues to exist in its descendants, and there's no built-in expiration date, no programmed senescence, no inevitable decline. This pattern persisted for billions of years. Life was immortal by default. Death, when it occurred, was due to external factors like predation, disease, or environmental catastrophe. But the intrinsic capacity for indefinite existence was the baseline condition of living things. So what changed? Why did evolution apparently invent death? This is one of the most profound questions in biology, and the answers are both surprising and encouraging for those of us interested in extending human lifespan. The current scientific consensus is that aging and death evolved as adaptive strategies, not inevitable consequences of being alive. In other words, we die because evolution found death useful, not because death is inherently necessary for life to exist. Consider the mathematical logic of evolution from the perspective of genetic fitness. In most natural environments, the probability of survival decreases over time due to predation, disease, accidents, and environmental changes. An organism that reproduces early and often has a better chance of passing on its genes than one that conserves resources for an indefinitely long future that it might not survive to see. Evolution therefore favoured organisms that invested heavily in reproduction and relatively little in long-term maintenance and repair. It's more efficient from a genetic perspective to build an organism that functions well for a few reproductive cycles and then breaks down, rather than to invest the enormous resources that would be required to maintain perfect functionality indefinitely. This is where the lobster comes in, and why these remarkable creatures have become symbols of hope for longevity researchers around the world. Lobsters appear to be biologically immortal. They don't age in the traditional sense. They don't become weaker or more vulnerable as they get older. They don't experience the progressive decline in function that characterizes aging in most animals. Instead, they continue to grow, molt and reproduce throughout their lives, which can span several decades or even longer. The secret lies in their telomeres, the protective caps on the ends of chromosomes that normally shorten with each cell division in most animals. In humans, telomere shortening is one of the primary mechanisms of aging. Our cells can only divide a limited number of times before their telomeres become too short, leading to cellular dysfunction and eventual death. But lobsters produce an enzyme called telomerase throughout their lives, which constantly repairs and rebuilds their telomeres. This means their cells can continue dividing indefinitely without the accumulated damage that leads to aging in other creatures. A lobster that avoids predation, disease, and accidents could theoretically live forever, growing larger and larger with each passing year. This isn't just theoretical. Lobster researchers have found specimens that are estimated to be over 100 years old, still healthy, still reproducing, still growing. The largest lobster ever caught weighed over 40 pounds and was estimated to be at least a century old, possibly much older. There's no biological reason that lobster couldn't have continued living and growing for many more decades. Lobsters aren't the only creatures that have mastered biological immortality. The immortal jellyfish, Turritopsis dohrnii, has developed an even more remarkable strategy. When faced with physical damage, starvation, or old age, this tiny jellyfish can reverse its aging process entirely, transforming back into its juvenile state and beginning its life cycle anew. It's like a butterfly turning back into a caterpillar, or an adult human somehow reverting to childhood. The process is called transdifferentiation, and it involves the jellyfish's cells essentially forgetting what type of cells they were supposed to be and returning to a pluripotent state, like stem cells. The jellyfish then rebuilds itself from the ground up, creating a fresh young body to house its genetic information. This process can apparently be repeated indefinitely, making the immortal jellyfish potentially eternal. Hydras, small freshwater polyps related to jellyfish and sea anemones, display a different type of immortality. They possess extraordinary regenerative abilities and show no signs of aging. A hydra can be cut into pieces, and each piece will regenerate into a complete healthy organism. They maintain this regenerative capacity throughout their lives, constantly renewing their cells and tissues. What's remarkable about hydras is that they seem to have solved the problem of cellular aging entirely. Their stem cells remain perpetually young and active, continuously replacing old or damaged cells throughout the organism. Scientists have been studying hydras in laboratory conditions for over 60 years, and some individual specimens have shown no signs of aging or decline throughout that entire period. Even more intriguing are certain trees that appear to achieve functional immortality through clonal reproduction. The Pando Aspen Grove in Utah consists of over 40,000 individual trees that are all genetically identical clones of a single original organism. The root system that connects and supports all these trees is estimated to be between 80,000 and 1 million years old, making it possibly the oldest living organism on Earth. The Pando colony achieves immortality through a form of distributed existence. Individual tree stems may die and be replaced, but the underlying organism, the root system and genetic identity, persists indefinitely. It's like immortality through replacement parts, a biological version of the Ship of Theseus paradox. These examples from nature prove beyond doubt that biological immortality is possible. Evolution has discovered multiple pathways to indefinite lifespan, multiple solutions to the problem of aging and death. The fact that humans and most other complex animals age and die is not because immortality is impossible, but because evolution found mortality advantageous under most circumstances. But circumstances have changed dramatically. Humans now live in environments where the evolutionary logic that favoured aging no longer applies. We've largely eliminated the predation, starvation, and environmental instability that made short lifespans adaptive for our ancestors. We have medical technology that can prevent or treat most of the diseases that historically killed people before aging became a factor. We've created social structures that allow older individuals to continue contributing to society rather than becoming burdens. In other words, we've created conditions where the biological immortality that worked for our single-celled ancestors might work for us as well. We've changed the game, and now we need to change the rules to match. This realization has sparked a revolution in longevity research. Scientists are no longer asking whether it's possible to extend human lifespans significantly. They're asking which of nature's immortality strategies can be adapted for human biology, and how quickly we can make that adaptation happen. The most promising research focuses on cellular aging mechanisms, particularly telomeres and the cellular processes that maintain and repair them. Human cells do produce telomerase, but in most adult tissues, this production is severely limited. This appears to be an evolutionary safeguard against cancer, since rapidly dividing cells with unlimited replicative potential can become malignant. But researchers have found ways to boost telomerase production safely, at least in laboratory conditions. Studies with mice have shown that increasing telomerase activity can extend lifespan and improve health span, the period of life spent in good health. The mice lived longer, showed fewer signs of aging, and maintained their cognitive and physical abilities well into what would normally be considered old age. Human trials are just beginning, but early results are encouraging. Some studies have shown that lifestyle interventions like meditation, exercise, and stress reduction can naturally increase telomerase activity and slow telomere shortening. Other research is exploring pharmaceutical approaches to safely boost telomerase production in human cells. Meanwhile, researchers studying hydras are trying to understand how their stem cells remain perpetually young. If we could figure out how to maintain human stem cells in a similarly youthful state, we might be able to achieve the same kind of indefinite regenerative capacity that keeps hydras biologically immortal. Scientists working with the immortal jellyfish are investigating the transdifferentiation process that allows these creatures to reverse their aging. While full body age reversal might be beyond current human capabilities, understanding the molecular mechanisms could lead to targeted therapies that reverse aging in specific organs or tissues. The regenerative abilities of certain animals are also being studied intensively. Salamanders can regrow entire limbs, hearts, and even portions of their brains. Zebrafish can regenerate heart tissue after injury. Planarian worms can regenerate their entire bodies from tiny fragments. Each of these capabilities represents a potential therapeutic target for human medicine. Perhaps most intriguingly, researchers are beginning to understand the role of cellular senescence in aging. Senescent cells are cells that have stopped dividing but haven't died. They accumulate in tissues over time and secrete inflammatory compounds that contribute to aging and age-related diseases. Studies in mice have shown that removing senescent cells can extend lifespan and improve health, effectively turning back the biological clock. Early human trials of senolytic drugs, compounds that selectively eliminate senescent cells, are showing promising results. Patients treated with these drugs show improvements in physical function, reduced inflammation, and other markers of improved health. We might be looking at the first generation of true anti-aging therapies. But the most remarkable developments are happening at the genetic level, where scientists are beginning to understand the molecular switches that control aging and longevity. Certain genes, when activated or deactivated, can dramatically extend lifespan in laboratory animals. Some of these genetic modifications can double or even triple the normal lifespan of mice, and the animals remain healthy and active throughout their extended lives. The implications are staggering. If similar genetic modifications could be safely applied to humans, we might be looking at lifespans measured in centuries rather than decades. And unlike the mythical immortality of folklore, this wouldn't require selling our souls or becoming monsters. It would simply involve turning on biological processes that already exist within us, genetic capabilities that evolution has built into our cells but normally keeps switched off. Gene therapy. Technology is advancing rapidly, and what seemed impossible just a few years ago is now routine in laboratory settings. We can already edit human genes with precision, targeting specific genetic sequences and modifying them with minimal side effects. The technology exists to implement longevity genetic modifications in human cells. The main barriers now are regulatory rather than scientific. Some researchers believe we're only decades away from achieving what they call longevity escape velocity, the point where medical advances extend lifespan faster than time passes. In other words, for every year you live, medical progress adds more than a year to your remaining lifespan. Once we reach that point, age becomes optional for anyone with access to the technology. Consider what this means for someone who's 20 years old today. If longevity research continues advancing at its current pace, they might live to see therapies that can extend their lifespan to 150 years. If they make it to 150, they'll have access to even more advanced technologies that could extend their life to 300 years. If they make it to 300, well, by then, aging might be as antiquated as smallpox. This isn't science fiction anymore. These are serious scientific projections based on real research progress. Major technology companies are investing billions of dollars in longevity research. Google's Calico Labs, Amazon's longevity initiatives, and numerous biotech startups are all working on different aspects of the aging problem. The smartest minds in Silicon Valley are convinced that death is just another engineering challenge waiting to be solved. But even more encouraging is what we're learning about the cellular basis of aging itself. For most of human history, we've thought of aging as wear and tear, the inevitable result of living in a physical body over time. We assumed that aging was like the deterioration of a machine, with parts gradually wearing out until the whole system breaks down. But that's not how aging actually works. Aging is an active biological process, controlled by specific genes and molecular pathways. It's more like a computer program running in our cells than like mechanical breakdown. And programs can be modified, debugged, or even completely rewritten. The discovery that aging is programmed rather than inevitable has revolutionized how researchers approach longevity. Instead of trying to fix the damage caused by aging, they're working to modify the program that causes aging in the first place. Instead of treating the symptoms, they're addressing the root cause. This is where Ponce de Leon comes back into our story, because it turns out he was looking in the wrong place for something that actually exists. The fountain of youth isn't hidden in some remote location, is not a magical spring or an ancient artifact. The fountain of youth is inside every cell in your body, waiting to be turned on. Every human cell contains the complete genetic instructions for building and maintaining a youthful, healthy organism. The same DNA that guided your development from a single fertilized cell into a complex multicellular being also contains the information needed to repair damage, regenerate tissues, and maintain optimal function indefinitely. The problem isn't that we lack the genetic machinery for indefinite life. The problem is that most of this machinery gets turned off as we age. Evolution programmed our cells to focus on growth and reproduction during youth, and then to gradually shut down maintenance and repair processes as we get older. But those processes are still there, encoded in our DNA, waiting to be reactivated. Recent research has shown that many aspects of aging can be reversed by reactivating youthful gene expression patterns. Scientists can take cells from elderly donors, reprogram them to express genes normally active in young cells, and watch as the cells become functionally younger. They regain their regenerative capacity, their resistance to damage, their ability to divide and function normally. Even more remarkably, these cellular rejuvenation techniques are beginning to work in living animals. Researchers have reversed aging in the retinas of old mice, restoring their vision to youthful levels. They've rejuvenated muscle tissue, brain tissue, and other organs using similar approaches. The animals don't just live longer, they become biologically younger, with the physical capabilities and disease resistance of much younger individuals. The techniques involve activating what are called Yamanaka factors, a set of proteins that can reprogram adult cells back to a stem cell-like state. Named after Nobel Prize winner Shinya Yamanaka, these factors essentially reset the cellular clock, erasing the molecular signatures of aging and restoring cells to their youthful condition. The discovery of Yamanaka factors has opened up entirely new possibilities for treating aging and age-related diseases. Instead of trying to prevent aging or slow it down, we might soon be able to actively reverse it, turning back the biological clock and restoring tissues to their peak functionality. Clinical trials are already underway for some of these rejuvenation therapies. Patients with age-related macular degeneration are being treated with reprogrammed cells that could restore their vision. People with heart disease are receiving regenerative therapies that could reverse damage to their cardiovascular systems. Alzheimer's patients might soon benefit from treatments that rejuvenate brain tissue and restore cognitive function. But perhaps the most exciting development is the growing understanding of how lifestyle factors influence the aging process at the cellular level. It turns out that many of the things our grandparents told us were good for us, eating well, exercising regularly, managing stress, getting enough sleep, actually work by activating the same molecular pathways that longevity researchers are trying to target with drugs and gene therapy. Exercise, for example, doesn't just keep your muscles strong and your heart healthy, it also activates cellular cleanup processes that remove damaged proteins and organelles, essentially giving your cells a spring cleaning. It stimulates the production of new mitochondria, the cellular powerhouses that provide energy for all cellular functions. It promotes the growth of new brain cells and strengthens the connections between them. Caloric restriction, eating fewer calories while maintaining good nutrition, has been shown to extend lifespan in virtually every species tested, from yeast to primates. The mechanism appears to involve activating stress response pathways that enhance cellular repair and maintenance. When cells sense that nutrients are scarce, they shift from growth mode to survival mode, investing more resources in maintaining their existing components rather than building new ones. Intermittent fasting, cycling between periods of eating and fasting, seems to provide many of the same benefits as caloric restriction without requiring a permanent reduction in food intake. During fasting periods, cells activate autophagy, a process that literally means self-eating, where cellular components that are old or damaged are broken down and recycled. It's like giving your cells the opportunity to renovate themselves on a regular basis. Meditation and stress reduction practices have been shown to influence aging at the molecular level by reducing chronic inflammation and supporting telomere maintenance. Chronic stress accelerates cellular aging through multiple pathways, while stress reduction techniques can slow or even reverse these processes. Even social connections and sense of purpose appear to influence biological aging. People with strong social relationships and a sense of meaning in their lives tend to live longer and age more slowly than those who are isolated or feel that their lives lack purpose. The mechanisms are still being studied, but it appears that psychological well-being translates directly into cellular health. The remarkable thing is that these lifestyle interventions don't just add years to your life, they add healthy years. People who follow evidence-based longevity practices don't just live longer, they remain physically and mentally capable well into what used to be considered old age. They experience what researchers call compressed morbidity, where the period of illness and decline at the end of life is shortened, while the period of healthy active living is extended. This suggests that we don't have to wait for advanced medical technologies to begin benefiting from longevity research. Many of the most powerful anti-aging interventions are available right now, requiring nothing more than changes in behavior and lifestyle. We can begin implementing them immediately while we wait for more advanced treatments to become available. The convergence of these different approaches, genetic engineering, cellular reprogramming, pharmaceutical interventions, and lifestyle modifications, is creating unprecedented opportunities for extending human lifespan. We're not just working on one solution to aging, we're developing an entire toolkit of approaches that can be combined and customized for individual needs and circumstances. Some people might benefit most from genetic modifications that enhance their natural longevity genes. Others might respond better to cellular reprogramming therapies that directly reverse aging at the tissue level. Still others might achieve significant life extension through optimized nutrition, exercise, and stress management. The future of longevity medicine will likely involve personalized approaches that take into account individual genetics, medical history, and lifestyle preferences. But perhaps the most profound implication of current longevity research is what it suggests about human potential more generally. If we can solve aging, if we can extend healthy human lifespan by decades or centuries, what else becomes possible? Think about the cumulative effect of experience and learning over an extended lifespan. Someone who lives for 200 years could master multiple careers, learn dozens of languages, develop expertise in completely different fields. They could witness and participate in historical changes that span centuries rather than decades. They could form relationships and create works of art or science that build on decades or centuries of accumulated wisdom and skill. Extended lifespans could transform human society in ways we're only beginning to imagine. Economic systems built on the assumption of 70-year lifespans would need to be completely reimagined. Educational systems that front-load learning into childhood and young adulthood would need to become lifelong endeavors. Social institutions like marriage and family structures would evolve to accommodate relationships that could span centuries. The environmental implications are also staggering. People who expect to live for centuries might make very different decisions about environmental sustainability and long-term resource management. Climate change becomes a much more personal issue when you expect to personally experience the consequences of today's environmental policies over the next several centuries. Space exploration and colonization become much more feasible when the people planning and executing these missions could personally see them through to completion over multi-century timescales. The development of truly sustainable technologies and social systems becomes not just an ethical imperative, but a practical necessity for people who plan to be around to experience the long-term consequences of current decisions. But even more fundamentally, extended lifespans could change what it means to be human. Our current understanding of human development, psychology, and social behavior is based on the assumption of limited lifespans. We don't know what human beings become when they have centuries to develop and mature rather than mere decades. Would a person who has lived for 300 years think and feel differently than someone who has lived for 50? Would they develop forms of wisdom and understanding that are impossible to achieve in a normal lifespan? Would they become fundamentally different kinds of beings, still recognizably human but possessing capabilities and perspectives that we can barely imagine? These questions might seem like science fiction, but they're becoming practical considerations as longevity research advances. The children being born today might live to see their own children, grandchildren, great-grandchildren, and many generations beyond. They might witness and participate in the entire future history of human civilization on Earth and beyond. The realization that death might be optional, that aging might be reversible, that human lifespans might be indefinitely extendable, is perhaps the most significant development in human history. It's comparable to the agricultural revolution, which allowed humans to move beyond hunting and gathering, or the Industrial Revolution, which mechanized human labor and transformed society. But unlike those previous revolutions, which changed how humans live, the longevity revolution could change the fundamental nature of human existence itself. We're not just talking about living longer, we're talking about the possibility of indefinite existence, of human beings who never have to face the biological inevitability of death. This brings us back to those ancient myths and legends about immortality. Our ancestors weren't just telling stories, they were expressing a deep intuition about human potential. They understood, perhaps better than we have until recently, that mortality is not necessarily an unchangeable fact about human existence. The vampires and immortals of folklore weren't just fantasy creatures. They were thought experiments about what humans might become if we could transcend our biological limitations. The alchemists searching for the philosopher's stone weren't just misguided mystics. They were early researchers working on the same problems that occupy today's longevity scientists. Ponce de Leon wasn't a fool for searching for the fountain of youth. He was simply looking in the wrong place. The fountain of youth isn't somewhere out there in the world. It's in here, in our cells, in our genes, in our understanding of how biological processes can be controlled and modified. The difference between the mythical immortality of the past and the scientific immortality that's becoming possible today is that we're approaching it through rigorous research and evidence-based methods rather than magic and wishful thinking. We're not trying to make deals with supernatural forces or discover magical artifacts. We're learning how biology actually works and figuring out how to make it work better. But the goal is the same. The dream is the same. The fundamental human desire to transcend mortality, to continue existing, to keep learning and growing and experiencing remains unchanged. We're just finally developing the tools to make that dream a reality. The question is no longer whether it's possible to extend human lifespan significantly. The question is how quickly we can make it happen, how widely we can make it available, and how we can prepare society for the implications of success. The answers to those questions will determine whether we truly are living in the last generation that has to accept death as inevitable, or whether we're simply the generation that began the transition to something unprecedented in human history, the possibility of biological immortality for ordinary human beings. As we drift towards sleep tonight, it's worth contemplating the possibility that the person lying in your bed right now might be among the first humans to experience what every culture has dreamed about since the beginning of recorded history. You might be part of the generation that finally answers the question that has haunted and inspired humanity for thousands of years. What would you do with an indefinitely extended lifespan? How would you live differently if you knew you had centuries rather than decades ahead of you? What would you learn, create, or explore given unlimited time to pursue your interests and develop your capabilities? These aren't hypothetical questions anymore. They're practical considerations for anyone who expects to live through the next few decades of scientific progress. The fountain of youth that Ponce de Leon searched for in the swamps of Florida is being discovered in laboratories around the world, one gene, one cell, one biological pathway at a time. The death problem, as some researchers now call it, might actually be solved sooner than most people realize. And when it is, everything changes. Everything we think we know about human life, human society, human potential, all of it becomes open to revision and reimagining. The vampire's promise of eternal life might no longer require fangs and blood. The lobster's biological immortality might become available to creatures far more complex than arthropods. The cellular fountain of youth might flow not just in mythology but in the very real, very practical world of modern medicine. But let's delve much deeper into these ancient stories of immortality, because the more we examine them, the more they reveal about human psychology and our relationship with mortality. Every culture's immortality myths contain surprisingly sophisticated insights about the nature of life, death, and what it might actually mean to live forever. Take the Greek myth of the Sibyl of Cumae, who was granted immortality by Apollo but forgot to ask for eternal youth. The story goes that she eventually became so ancient and withered that she was kept in a jar, and when children asked her what she wanted, she would whisper that she wanted to die. This tale explores one of the most fundamental questions about immortality. Would eternal life be a blessing or a curse if it came without eternal health and vitality? The myth anticipates one of the central challenges of modern longevity research. It's not enough to simply extend lifespan if those extra years are filled with disease, disability, and suffering. The goal isn't just to live longer, it's to live better for longer. Scientists call this concept health span extension, the idea that medical interventions should focus not just on adding years to life, but on adding healthy, functional years to life. This distinction becomes crucial when we consider the current state of human aging. The average person in developed countries can expect to live into their 70s or 80s, but they can also expect to spend the last decade or more of their lives dealing with chronic diseases, physical limitations, and cognitive decline. Simply extending this pattern would create a world where people live to be 150 but spent 50 years of that lifespan in nursing homes or struggling with dementia. The ancient Greeks understood this problem intuitively. The immortality myths almost always include cautionary elements about the importance of maintaining not just life but quality of life. The story of Tithonus, granted immortality but not eternal youth, serves as a warning about the dangers of achieving one without the other. Modern longevity researchers have taken this lesson to heart. The most promising anti-aging interventions focus on maintaining biological function rather than simply preventing death. The goal is to keep people biologically young for as long as possible, so that a person who is chronologically 100 might have the physical and mental capabilities of someone who is currently 30. This approach is sometimes called negligible senescence, the idea that aging could be slowed to such a degree that it becomes essentially unnoticeable over human timescales. A person with negligible senescence might age 1 biological year for every 10 or 20 chronological years, maintaining their youth and vitality for centuries. The concept isn't as far-fetched as it might sound. We already see examples of differential aging rates in human populations. Some people age much more slowly than others due to genetic factors, lifestyle choices, or environmental conditions. The challenge is to understand what accounts for these differences and then apply that knowledge to help everyone age more slowly. Genetic studies of centenarians, people who live to be 100 or older, have revealed that many of them share certain genetic variants that appear to protect against age-related diseases and cellular damage. These variants don't just help people live longer, they help them remain healthy and active well into their later years. One of the most studied longevity genes is FOXO3, which is involved in cellular stress resistance and DNA repair. People with certain variants of this gene have significantly higher chances of living to be 100, and they tend to maintain their cognitive abilities and physical health much better than their peers. Another important longevity gene is ApoE, which affects cholesterol metabolism and brain health. People with protective variants of ApoE have lower risks of heart disease and Alzheimer's disease, two of the leading causes of death and disability in older adults. But here's what's particularly exciting about these genetic discoveries. The protective effects of longevity genes can potentially be mimicked through medical interventions. If we understand how a particular gene variant protects against aging, we can develop drugs or therapies that provide similar protection to people who don't naturally carry those variants. This is already happening with some longevity pathways. The drug metformin, originally developed to treat diabetes, appears to activate some of the same cellular pathways that are enhanced in people with natural longevity genes. Studies suggest that people who take metformin not only have better blood sugar control, but also live longer and have lower rates of age-related diseases. Rapamycin, another drug originally developed for a different purpose, to prevent organ transplant rejection, has been shown to extend lifespan in laboratory animals by activating cellular cleanup processes, similar to those enhanced by caloric restriction. Human trials are underway to test whether rapamycin can provide similar benefits for healthy aging in people. But the genetic approach to longevity raises fascinating questions about human enhancement and the nature of identity. If we can modify our genes to make us live longer and age more slowly, are we still the same species? Are we still human in the traditional sense? Or are we becoming something new? These questions echo themes from vampire mythology in unexpected ways. Vampires in literature often struggle with questions of identity and humanity. They retain their memories and personalities, but their fundamental nature has been changed. They exist in a liminal space between human and something else, neither fully mortal nor truly divine. Modern longevity research might be taking us into similar territory. If we can extend human lifespan to centuries or millennia, if we can maintain youthful bodies and minds for hundreds of years, if we can enhance our cognitive abilities and physical capabilities beyond normal human limits, what does it mean to be human? The question becomes even more complex when we consider the possibility of consciousness uploading or digital immortality. Some researchers believe that within the next few decades, it might be possible to map the human brain in sufficient detail to create digital copies of human consciousness. These digital minds could potentially exist indefinitely, free from the biological limitations that constrain physical brains. But would a digital copy of your consciousness be you? Or would it be something else, wearing your memories like a mask? This is a modern version of the ancient philosophical question about the ship of Theseus. If you replace every part of a ship with new parts, is it still the same ship? The vampire myth explores similar themes of continuity and change. A vampire retains the memories and personality of their human self, but their body has been fundamentally transformed. Are they the same person they were before, or are they a new being that simply remembers being human? These questions aren't just philosophical abstractions anymore. They're becoming practical considerations as longevity research advances. If we can replace aging organs with laboratory-grown alternatives, if we can enhance our cognitive abilities through genetic modification or brain-computer interfaces, if we can transfer our consciousness to digital substrates, at what point do we stop being human and become something else? The answer might be that the distinction doesn't matter as much as we think it does. Human identity has always been fluid and contextual. The person you are today is different in many ways from the person you were 10 years ago, yet you consider yourself to have continuity of identity across that time. Your body has replaced most of its cells, your brain has formed new connections and pruned old ones, your personality and beliefs may have changed significantly, yet you're still you. Perhaps the enhanced, life-extended humans of the future will simply represent the next stage of human development, just as modern humans represent an evolution from our earlier ancestors. We're already very different from the humans who lived thousands of years ago in terms of lifespan, health, cognitive abilities, and social organization, yet we consider ourselves to be the same species. But let's return to the specific mechanisms that make biological immortality possible, because understanding these processes in detail reveals just how close we might be to achieving significant life extension in humans. The lobster's biological immortality depends on several key factors that work together to prevent aging. First, as mentioned, lobsters maintain active telomerase throughout their lives, which prevents their chromosomes from degrading with each cell division. But telomerase alone isn't sufficient for immortality. It also has to be carefully regulated to prevent cancer. Cancer is essentially what happens when cells gain the ability to divide indefinitely without proper constraints. In most mammals, including humans, telomerase activity is limited in adult tissues precisely to reduce cancer risk. It's a trade-off between aging and cancer. Limiting telomerase prevents runaway cell division but also causes cellular aging. Lobsters have somehow solved this problem. They maintain high telomerase activity without developing the kinds of cancers that would be expected in mammals with similar levels of cellular proliferation. Understanding how they achieve this balance could be the key to developing safe longevity therapies for humans. Recent research suggests that lobsters have enhanced DNA repair mechanisms that prevent the genetic damage that typically leads to cancer. They also appear to have more effective immune surveillance systems that can detect and eliminate potentially cancerous cells before they become problematic. These discoveries are leading to new approaches for human longevity research. Instead of simply trying to boost telomerase activity, scientists are working on comprehensive interventions that enhance telomerase, improve DNA repair, and strengthen immune function simultaneously. The goal is to recreate the lobster's biological immortality in a form that's compatible with human physiology. Early results from animal studies are encouraging. Mice that have been genetically modified to express enhanced DNA repair genes and optimized immune function can tolerate much higher levels of telomerase activity without developing cancer. They live significantly longer than normal mice and show fewer signs of aging throughout their extended lifespans. But lobsters also have other advantages that contribute to their potential immortality. They have remarkable regenerative abilities, capable of regrowing lost limbs and repairing damaged organs. This regenerative capacity doesn't decline with age the way it does in most animals. Human beings actually possess significant regenerative abilities that we rarely think about. Your liver can regenerate from as little as 25% of its original mass. Your skin constantly replaces itself, with most skin cells being less than a month old. Your blood is completely replaced every few months. Even your bones are constantly being broken down and rebuilt throughout your life. The problem is that this regenerative capacity declines with age. A child who breaks a bone will heal much faster than an elderly person with the same injury. Young people recover from cuts and bruises more quickly than older adults. The regenerative machinery is still there in older bodies, but it becomes less efficient and less active over time. Understanding why regenerative capacity declines with age is one of the key challenges in longevity research. If we could maintain youthful levels of regenerative ability throughout life, many of the problems we associate with aging would disappear automatically. Recent research has identified several factors that contribute to age-related decline in regeneration. One important factor is the accumulation of senescent cells, cells that have stopped dividing but haven't died. These cells secrete inflammatory compounds that interfere with the normal repair and regeneration processes. Removing senescent cells from aged animals can restore youthful regenerative capacity. Mice that have had their senescent cells eliminated can regrow hair, heal wounds, and repair muscle damage much more effectively than untreated aged mice. Human trials of senolytic drugs, which selectively eliminate senescent cells, are showing similar promising results. Another factor that affects regeneration is the decline in stem cell function with age. Stem cells are the body's natural repair crew, capable of differentiating into many different cell types to replace damaged or worn-out tissues. But stem cells become less active and less effective as we age. Researchers have found ways to rejuvenate aged stem cells, restoring their youthful function and regenerative capacity. Some approaches involve exposing aged stem cells to factors found in young blood, which can reset their biological clocks and restore their proliferative ability. Parabiosis experiments, where old and young animals are surgically connected so they share a circulatory system, have shown that young blood contains factors that can rejuvenate aged tissues. When old mice are exposed to young blood, their muscles become stronger, their brains function better, and their overall health improves dramatically. Scientists have identified some of the specific factors in young blood that have these rejuvenating effects. Proteins like GDF11 and oxytocin appear to play important roles in maintaining tissue regeneration and repair. Clinical trials are underway to test whether supplementing these factors can provide anti-aging benefits in humans. But perhaps the most remarkable aspect of lobster biology is their apparent immunity to many of the diseases that plague aging humans. Lobsters rarely develop cancer, heart disease, or neurological disorders. They don't experience the cognitive decline that affects many elderly humans. They remain sexually active and reproductively capable throughout their long lives. This disease resistance appears to be related to their enhanced cellular maintenance systems. Lobsters have particularly efficient mechanisms for clearing damaged proteins and organelles from their cells. They also have robust antioxidant systems that protect against the cellular damage caused by reactive oxygen species. Human cells have similar protective mechanisms, but they become less effective with age. The accumulation of damaged proteins is a hallmark of aging and is associated with many age-related diseases, including Alzheimer's disease, Parkinson's disease, and heart failure. Researchers are developing therapies that can enhance the cellular cleanup processes that become impaired with age. Some approaches involve drugs that activate autophagy, the process by which cells digest their own damaged components. Others focus on enhancing the proteasome system, which is responsible for breaking down damaged proteins. Caloric restriction and intermittent fasting appear to work partly by activating these cellular cleanup processes. When cells are under mild stress from reduced nutrient availability, they become more efficient at recycling damaged components and maintaining their internal organization. Exercise has similar effects, activating cellular stress response pathways that enhance repair and maintenance. The physical stress of exercise triggers adaptive responses that make cells more resilient and better able to deal with damage. Even heat and cold exposure can activate beneficial stress responses. Sauna use and cold water immersion have been associated with increased longevity in some populations, possibly because they trigger cellular stress response pathways similar to those activated by exercise and caloric restriction. The concept underlying all of these interventions is hormesis, the idea that mild stress can be beneficial by activating adaptive responses that make organisms more resilient. It's like giving your cells a workout, challenging them in controlled ways that make them stronger and more resistant to damage. But lobsters also benefit from their external environment in ways that might not be applicable to humans. They live in cold water, which slows down metabolic processes and reduces the rate of cellular damage. They have hard shells that protect them from physical injury. They live in an environment that's relatively stable and predictable. Humans live in much more challenging environments from a biological perspective. We're exposed to pollution, stress, processed foods, and many other factors that can accelerate aging. We live at temperatures that maximize metabolic rate rather than longevity. We've created lifestyles that often work against our biological longevity mechanisms. But this also means that we have opportunities to modify our environment and behavior in ways that could significantly extend our lifespans. We can choose to eat foods that activate longevity pathways. We can exercise in ways that trigger beneficial stress responses. We can manage our stress levels and optimize our sleep patterns. Some researchers believe that optimal lifestyle interventions alone could extend healthy human lifespan to 120 years or more, even without advanced medical technologies. The theoretical maximum human lifespan, based on our current understanding of human biology, might be around 150 years. But when we combine optimal lifestyle interventions with the emerging medical technologies for life extension, the possibilities become much more dramatic. Gene therapies that enhance natural longevity mechanisms, cellular reprogramming techniques that reverse aging at the tissue level, and pharmaceutical interventions that target specific aging pathways could potentially extend human lifespan far beyond anything we've seen before. The question isn't whether significant life extension is possible, it's how quickly we can develop safe and effective interventions and how widely we can make them available. The basic science is already well established. We understand the key mechanisms of aging and have identified multiple targets for intervention. Now let's turn our attention to the immortal jellyfish, Turritopsis dohrnii, because this remarkable creature has solved the aging problem in a completely different way that might be even more applicable to humans than the lobster's approach. The immortal jellyfish achieves its immortality through a process called transdifferentiation, where mature cells transform back into immature pluripotent stem cells. When the jellyfish faces stress, injury, or old age, it essentially hits a biological reset button, reverting to its juvenile form and beginning its life cycle anew. This process is extraordinary because it violates one of the basic assumptions about multicellular development, that cellular differentiation is irreversible. In most organisms, when a cell commits to becoming a specific cell type, a muscle cell, a nerve cell, a skin cell, it loses the ability to become other cell types. The immortal jellyfish has found a way to reverse this process, allowing its cells to de-differentiate and then redifferentiate into whatever cell types are needed. The implications for human longevity are staggering. If we could learn to trigger controlled transdifferentiation in human tissues, we might be able to regenerate entire organs, reverse age-related damage, and essentially reset our biological clocks whenever necessary. Recent research has shown that human cells retain much more plasticity than previously thought. Under the right conditions, adult human cells can be reprogrammed to behave like embryonic stem cells, capable of developing into any cell type in the body. This process, discovered by Shinya Yamanaka and colleagues, earned them the Nobel Prize in Physiology or Medicine. The Yamanaka factors, as they're now known, are a set of proteins that can reprogram adult cells back to a pluripotent state. In laboratory conditions, scientists can take skin cells from an adult human, expose them to Yamanaka factors, and transform them into induced pluripotent stem cells that have the same developmental potential as embryonic stem cells. These reprogrammed cells can then be coaxed to develop into any desired cell type: heart cells, brain cells, liver cells, muscle cells. The technology already exists to take a skin sample from a patient and generate any type of replacement tissue they might need, all from their own genetic material. But the immortal jellyfish goes even further than this. It doesn't just reprogram individual cells, it reprograms its entire body simultaneously, transforming from an adult form back to a juvenile form while maintaining its essential biological identity. It's like a butterfly turning back into a caterpillar, but retaining some memory of having been a butterfly. Understanding how the immortal jellyfish coordinates this whole body reprogramming could lead to regenerative therapies that go far beyond simply replacing damaged tissues. We might be able to rejuvenate entire organ systems, or even the whole body, essentially allowing people to cycle between biological ages throughout their lives. Imagine being able to live your life in cycles, spending decades accumulating experience and wisdom, then undergoing a biological reset that restores your body to its youthful condition while preserving your memories and personality. You could have the experience of an elder with the body of a young adult, over and over again throughout an indefinitely extended lifespan. This might sound like science fiction, but the basic mechanisms are already understood and being studied intensively. Researchers have successfully used partial reprogramming techniques to reverse aging in specific tissues in laboratory animals. They've restored vision in elderly mice by reprogramming retinal cells, rejuvenated muscle tissue in aged animals, and even reversed some aspects of brain aging. The key insight from this research is that aging might not be as irreversible as we've always assumed. The molecular signatures of aging, the accumulated damage that makes cells and tissues function poorly, can potentially be erased through controlled reprogramming processes. But there are also significant challenges to overcome before these techniques can be safely applied to humans. Uncontrolled cellular reprogramming can lead to cancer, as cells lose their normal growth constraints and begin dividing uncontrollably. The immortal jellyfish has somehow solved this problem, maintaining genetic stability throughout its reprogramming cycles, but we don't yet understand how it achieves this balance. Another challenge is maintaining biological identity throughout the reprogramming process. The immortal jellyfish remains recognizably the same organism even after its transformation, but it's not clear how it preserves its essential characteristics while allowing its cells to de-differentiate and redifferentiate. For humans, the equivalent challenge would be maintaining memories, personality, and consciousness throughout a biological reset process. We would want to become biologically younger without losing the accumulated experiences and knowledge that make us who we are. Recent research suggests that memories and other aspects of identity might be more distributed and resilient than previously thought. Studies of patients who have undergone extensive brain surgery or tissue replacement have shown that core aspects of personality and identity can survive significant biological changes. But the immortal jellyfish also raises fascinating questions about the nature of individual identity over time. If a jellyfish cycles through multiple life stages, transforming from adult back to juvenile and then to adult again, is it the same individual throughout this process, or is each cycle a new organism that happens to share genetic material with the previous one? For humans, contemplating biological reset technologies, these questions become deeply personal. If you could undergo a process that restored your body to its 20-year-old condition, but preserved your 40-year-old memories and experiences, would you still be the same person? Would you be a 40-year-old in a 20-year-old body, or would you be something new? The vampire mythology again provides a useful framework for thinking about these questions. Vampires undergo a fundamental biological transformation that grants them immortality, but they retain their human memories and personalities. They exist in a state of suspended development, neither aging nor dying, but also not quite alive in the conventional sense. Modern regenerative medicine might create similar states of suspended or cyclical development. People might live for centuries, periodically resetting their biology to maintain youth and health while accumulating experiences and wisdom across multiple lifetimes worth of existence. But the immortal jellyfish has also revealed something else important about the nature of biological immortality. It's not necessarily a continuous state. The jellyfish doesn't live forever in the sense of never changing or never facing mortality. Instead, it has developed a strategy for surviving mortal crises by transforming itself into something that can continue living. This suggests that human immortality might not involve simply stopping the aging process, but rather developing the ability to recover from age-related damage whenever it becomes life-threatening. Instead of preventing aging, we might learn to periodically reverse it, allowing people to grow old and then become young again as needed. This cyclical approach to longevity might actually be more sustainable than trying to maintain a constant state of youth. It would allow people to experience the full range of human development, from youth through maturity, while providing an escape route from the terminal decline that currently marks the end of human life. The immortal jellyfish also demonstrates that biological immortality doesn't require magical or supernatural processes. It's achieved through perfectly natural biological mechanisms that follow the same physical and chemical laws that govern all life. The jellyfish isn't cheating death through some mystical process. It's using sophisticated molecular machinery to control its own development and aging. This naturalistic approach to immortality is important because it means that similar capabilities could potentially be engineered into other organisms, including humans. We're not trying to violate the laws of nature, we're trying to understand and apply biological processes that already exist. But let's also consider the Hydra, another creature that has achieved a form of biological immortality through yet another strategy. Hydras are small freshwater polyps that show no signs of aging under laboratory conditions. Some individual hydras have been maintained in research laboratories for over 60 years without showing any decline in their regenerative abilities or overall health. The hydra's immortality appears to be based on its extraordinary stem cell system. Unlike most animals, where stem cell populations decline with age, hydras maintain active stem cell populations throughout their lives. These stem cells continuously replace old or damaged cells, keeping the hydra's tissues in a constant state of renewal. Hydras can be cut into pieces, and each piece will regenerate into a complete healthy organism. They can regrow their entire body from tiny fragments, including their nervous system, digestive system, and reproductive organs. This regenerative capacity doesn't decline with age, suggesting that hydras have solved the problem of stem cell aging that limits regeneration in most other animals. The key to the hydra's immortality appears to be a combination of factors. First, they have a very simple body plan with only 2 cell layers and a basic nervous system. This simplicity makes it easier to maintain and repair their tissues. Second, they have evolved mechanisms for preventing the accumulation of cellular damage that typically accompanies aging. Hydras also have unusually robust DNA repair systems that can fix genetic damage before it accumulates to harmful levels. They produce high levels of antioxidants that protect against cellular damage from reactive oxygen species. They have efficient mechanisms for eliminating damaged proteins and organelles. But perhaps, most importantly, hydras have evolved a population structure that prevents the evolutionary pressure that normally favours aging. In most animals, natural selection favours rapid reproduction and early death, because resources spent on long-term maintenance could otherwise be invested in producing more offspring. Hydras reproduce both sexually and asexually, budding off genetic clones that can establish new populations. This means that an individual hydra's reproductive success isn't necessarily limited by its own lifespan. The same genetic material can continue reproducing indefinitely through multiple generations of clones, removing the evolutionary pressure to trade longevity for reproductive output. This insight has important implications for human longevity research. It suggests that achieving biological immortality might require not just solving the technical problems of cellular maintenance and repair, but also addressing the evolutionary constraints that have shaped our aging process. Humans evolved in environments where extrinsic mortality from predation, disease, and accidents was very high. Under those conditions, it made evolutionary sense to invest heavily in early reproduction rather than long-term maintenance. But in modern environments where extrinsic mortality is much lower, those evolutionary constraints no longer apply. We might be able to use medical interventions to override the evolutionary programming that causes aging, essentially hacking our own biology to achieve the kind of indefinite lifespan that works for creatures like hydras. Gene therapy, pharmaceutical interventions, and lifestyle modifications could potentially reprogram our cells to prioritize maintenance and repair over the reproductive urgency that drives natural aging. But hydras also demonstrate that biological immortality doesn't necessarily mean invulnerability. Hydras can still be killed by extreme environmental conditions, toxic chemicals, or physical destruction. Their immortality is specifically immortality from aging, not immortality from all possible causes of death. This distinction is important for understanding what human life extension might actually look like. Even if we solve the aging problem completely, people would still face risks from accidents, violence, infectious diseases, and other external threats. Biological immortality wouldn't make humans invulnerable, it would simply remove aging as a cause of death. Statistical models suggest that even with perfect biological immortality, the average human lifespan would still be limited by external risks. Depending on the accident rate and other factors, the average lifespan of an immortal human might be anywhere from several hundred to several thousand years. But even this limited form of immortality would transform human society in unprecedented ways. People who expect to live for centuries would make very different decisions about education, career development, relationships, and long-term planning. The accumulated knowledge and experience of individuals who have lived for hundreds of years could accelerate scientific and cultural progress in ways we can barely imagine. The hydra's approach to immortality also suggests that maintaining youth and health indefinitely might require accepting a certain level of biological dynamism. Hydras achieve their immortality partly by constantly renewing their tissues, essentially rebuilding themselves on an ongoing basis. They're not the same collection of cells from day to day, but rather a pattern of organization that maintains itself through continuous change. Human beings already work this way to some extent. Most of the cells in your body are replaced regularly, with different tissues having different turnover rates. Your intestinal lining replaces itself every few days. Your skin cells are replaced every few weeks. Even your bones are completely rebuilt every few years. The challenge with human aging is that this replacement process becomes less efficient over time. Stem cell populations decline, DNA repair mechanisms become less effective, and the cellular machinery responsible for maintenance and renewal gradually breaks down. Understanding how hydras maintain their regenerative capacity indefinitely could provide insights into how to enhance human cellular renewal processes. If we could keep our stem cell populations young and active, maintain efficient DNA repair systems, and prevent the accumulation of cellular damage, we might be able to achieve hydra-like biological immortality. But this brings us to the remarkable discovery that Ponce de Leon was actually looking in the wrong place for something that genuinely exists. The fountain of youth isn't hidden in some remote geographical location. It's encoded in the genetic instructions that guide cellular development and maintenance. Every cell in your body contains the complete genetic blueprint for building and maintaining a healthy, youthful organism. The same DNA that guided your development from a single fertilized cell into a complex multicellular being also contains instructions for repairing damage, regenerating tissues, and maintaining optimal function indefinitely. The problem isn't that we lack the genetic machinery for youth and longevity. The problem is that this machinery is regulated by biological programs that prioritize short-term survival and reproduction over long-term maintenance. Evolution has programmed our cells to focus on getting us through the reproductive years, with relatively little investment in maintaining function beyond that point. But these biological programs can potentially be modified through medical interventions. We can use drugs, gene therapy, lifestyle modifications, and other approaches to reprogram our cells to prioritize maintenance and repair throughout our lives rather than just during youth. Recent research has identified many of the specific genes and molecular pathways that control cellular aging and maintenance. The mTOR pathway, which regulates cellular growth and metabolism, can be modulated to promote longevity. The AMPK pathway, which senses cellular energy status, can be activated to enhance cellular maintenance processes. The sirtuins, a family of proteins involved in stress response and DNA repair, can be upregulated to improve cellular resilience. Each of these pathways represents a potential target for anti-aging interventions. Drugs that modulate these pathways are already in clinical trials, and some have shown promising results for extending health span and potentially lifespan in humans. But perhaps the most exciting development is the growing understanding of how epigenetic modifications control aging and cellular function. Epigenetics refers to changes in gene expression that don't involve changes to the underlying DNA sequence. These modifications can be thought of as software running on the hardware of our genetic code. As we age, our cells accumulate epigenetic changes that alter gene expression patterns and contribute to cellular dysfunction. But unlike genetic mutations, epigenetic changes are potentially reversible. We might be able to reset the epigenetic state of aged cells, essentially reprogramming them to express genes in the same patterns as young cells. This is exactly what happens during the cellular reprogramming process that creates induced pluripotent stem cells. The Yamanaka factors work by resetting epigenetic modifications, allowing adult cells to revert to an embryonic-like state where they can develop into any cell type. Researchers are now working on developing partial reprogramming techniques that can reverse some of the epigenetic changes associated with aging without completely erasing cellular identity. The goal is to make old cells function like young cells while preserving their specialized functions and accumulated adaptations. Early experiments with partial reprogramming have been remarkably successful. Researchers have restored vision in aged mice by partially reprogramming retinal cells, essentially making old eyes young again. They've rejuvenated muscle tissue, improved cognitive function, and reversed other aspects of aging in laboratory animals. These results suggest that aging might be much more reversible than previously thought. Instead of viewing aging as an irreversible accumulation of damage, we might need to think of it as a potentially reversible change in cellular programming. The fountain of youth that Ponce de Leon searched for in the swamps of Florida is actually encoded in every cell of our bodies. We carry within us the genetic instructions for maintaining youth and health indefinitely. The challenge is learning how to access and activate these instructions throughout our lives. But the cellular fountain of youth isn't just a metaphor, it's becoming a literal reality as researchers develop technologies that can rejuvenate aged cells and tissues. Stem cell therapies can replace old, dysfunctional cells with young, healthy ones. Gene therapies can enhance the expression of longevity genes and repair age-related genetic damage. Pharmaceutical interventions can activate cellular maintenance processes and improve resistance to aging. The convergence of these different approaches is creating unprecedented opportunities for extending human health and lifespan. We're not just working on one solution to aging, we're developing an entire toolkit of interventions that can be combined and customized for individual needs. Some people might benefit most from genetic enhancements that boost their natural longevity mechanisms. Others might respond better to cellular reprogramming therapies that directly reverse aging in specific tissues. Still others might achieve significant life extension through optimized combinations of diet, exercise, stress management, and pharmaceutical interventions. The future of anti-aging medicine will likely be highly personalized, taking into account individual genetic profiles, medical histories, lifestyle factors, and personal preferences. Instead of a one-size-fits-all approach to longevity, we'll have precision medicine approaches that optimize interventions for each person's unique biology and circumstances. But perhaps the most profound implication of understanding aging as a programming problem rather than a hardware failure is what it suggests about human potential. If we can reprogram our cellular software to maintain youth and health indefinitely, what else becomes possible? Enhance cognitive function through genetic modifications or brain-computer interfaces, improve physical capabilities through muscle enhancement or neural optimization, extended sensory abilities through technological augmentation. The same technologies that could eliminate aging might also enable enhancements that go far beyond normal human capabilities. We might be approaching a future where the distinction between treatment and enhancement becomes increasingly blurred. Therapies designed to treat age-related diseases might also improve function beyond normal human baselines. Interventions intended to extend lifespan might also enhance cognitive abilities, physical strength, or sensory perception. This prospect of human enhancement raises important ethical and social questions. If life extension technologies also provide enhancement benefits, how do we ensure they're distributed fairly? How do we prevent the creation of a privileged class of enhanced individuals who live for centuries while others remain limited to normal human lifespans? These questions become even more complex when we consider the cumulative effects of life extension over time. Someone who lives for 200 years while maintaining youthful health and cognitive function could accumulate knowledge, skills, and resources that give them enormous advantages over people with normal lifespans. The social and economic implications of significant life extension are staggering and largely unpredictable. Economic systems based on the assumption of 70-year working lives would need to be completely reimagined. Educational systems that front-load learning into childhood and young adulthood would become obsolete. Social institutions like marriage and family structures would evolve to accommodate relationships that could span centuries. But there are also enormous potential benefits. People who live for centuries could develop levels of expertise and wisdom that are impossible to achieve in normal lifespans. They could witness and contribute to historical changes that span generations. They could form relationships and create works of art or science that build on hundreds of years of accumulated experience. The environmental implications are also significant. People who expect to live for centuries might make very different decisions about environmental sustainability and resource management. Climate change and other environmental challenges become much more personal when you expect to personally experience the consequences of today's decisions over the next several hundred years. Space exploration and colonization become more feasible when the people planning and executing these missions could personally see them through to completion over multi-century timescales. The development of truly sustainable technologies and social systems becomes not just an ethical imperative but a practical necessity for people who plan to be around to experience the long-term consequences of current decisions. But let's dive deeper into the specific molecular mechanisms that make cellular immortality possible, because understanding these processes in detail reveals just how achievable significant life extension might be for humans. The cellular machinery that maintains youth and prevents aging already exists within us. It just needs to be properly activated and maintained. At the heart of cellular aging lies the fundamental process of DNA replication and repair. Every time a cell divides, it must copy its entire genome, a process that involves reading and reproducing over 3 billion base pairs of genetic information. This copying process is remarkably accurate, but it's not perfect. Small errors accumulate over time, and the protective caps on chromosomes, called telomeres, gradually shorten with each division. In most human cells, telomeres act like a molecular countdown timer. They start long in young cells and get shorter with each division until they reach a critical length that triggers cellular senescence or death. This mechanism evolved as a protection against cancer, preventing cells from dividing indefinitely and potentially becoming malignant. But the creatures that achieve biological immortality have found ways around this limitation. Lobsters, as we've discussed, maintain active telomerase throughout their lives, constantly rebuilding their telomeres and allowing their cells to divide indefinitely without hitting the replicative limit that constrains human cells. The enzyme telomerase is actually present in human cells, but it's mostly inactive in adult tissues. We have the genetic instructions for producing telomerase, and we can manufacture the enzyme when needed, but evolutionary programming has turned it off in most of our cells as a cancer prevention mechanism. Recent research has shown that it's possible to safely reactivate telomerase in human cells under controlled conditions. Scientists have developed techniques for temporarily boosting telomerase activity to restore telomere length without triggering uncontrolled cell division. These approaches could potentially reset the cellular aging clock and extend the replicative lifespan of human tissues. But telomeres are just one piece of the aging puzzle. Even cells with perfectly maintained telomeres can still accumulate other types of damage that impair their function over time. Proteins can become misfolded or damaged by oxidative stress. Mitochondria, the cellular powerhouses that produce energy, can develop defects that reduce their efficiency. The cellular machinery responsible for quality control and maintenance can itself become damaged or dysregulated. This is where the lessons from hydras become particularly relevant. These creatures have evolved comprehensive cellular maintenance systems that prevent the accumulation of damage that normally accompanies aging. They maintain robust protein quality control mechanisms that can detect and eliminate damaged proteins before they interfere with cellular function. Hydras also have exceptionally efficient autophagy systems, the cellular recycling processes that break down and recycle damaged organelles and protein aggregates. When cellular components become old or damaged, autophagy machinery tags them for destruction and recycles their molecular components into new, functional structures. Human cells have similar autophagy systems, but they become less efficient with age. The decline in autophagy function is thought to be one of the key contributors to cellular aging and age-related diseases. Many of the protein aggregates that characterize neurodegenerative diseases like Alzheimer's and Parkinson's result from failures in autophagy-mediated protein clearance. But here's the encouraging news. Autophagy function can be enhanced through various interventions. Caloric restriction, intermittent fasting, exercise, and certain pharmaceutical compounds can all boost autophagy activity and improve cellular maintenance. Some researchers believe that enhancing autophagy might be one of the most effective ways to slow aging and extend healthy lifespan. The drug rapamycin, originally developed as an immunosuppressant, has gained attention for its ability to enhance autophagy and extend lifespan in laboratory animals. Studies have shown that rapamycin can extend the lifespan of mice by up to 25%, while also improving their health during aging. Rapamycin works by inhibiting a protein complex called mTOR, which serves as a master regulator of cellular growth and metabolism. When mTOR activity is reduced, cells shift from growth mode to maintenance mode, investing more resources in repair and cleanup processes rather than new protein synthesis and cell division. This metabolic shift mimics some of the effects of caloric restriction, which is the only intervention that has been consistently shown to extend lifespan across a wide range of species. Animals on calorie-restricted diets live longer, have lower rates of age-related diseases, and maintain better physical and cognitive function as they age. The mechanism behind caloric restriction's anti-aging effects involves multiple pathways, but one key factor is the activation of a family of proteins called sirtuins. These proteins function as cellular stress sensors, becoming more active when nutrients are scarce and coordinating a comprehensive response that enhances cellular resilience and longevity. Sirtuins promote DNA repair, enhance mitochondrial function, reduce inflammation, and activate many of the same cellular maintenance processes that are enhanced in naturally long-lived animals. They essentially reprogram cellular metabolism to prioritize long-term survival over short-term growth and reproduction. Pharmaceutical companies are developing drugs called sirtuin activators that can mimic the effects of caloric restriction without requiring people to dramatically reduce their food intake. The most famous of these compounds is resveratrol, found in red wine, which can activate sirtuins and has been shown to extend lifespan in some laboratory animals. But more potent sirtuin activators are now in development, compounds that are hundreds of times more effective than resveratrol at activating these longevity pathways. Early human trials suggest that these drugs can improve metabolic health, enhance physical performance, and potentially slow aspects of the aging process. Another crucial component of cellular immortality involves maintaining mitochondrial function throughout life. Mitochondria are often called the powerhouses of the cell because they produce most of the energy that cells need to function. But mitochondria have their own DNA, separate from the nuclear DNA that contains most of our genetic information, and this mitochondrial DNA is particularly vulnerable to damage. As we age, mitochondrial DNA accumulates mutations that impair energy production and lead to cellular dysfunction. This mitochondrial decline is thought to contribute to many age-related diseases, including heart disease, neurodegenerative disorders, and muscle weakness. But mitochondria also have remarkable regenerative capabilities when they're functioning properly. They can fuse together to share resources and repair damage. They can undergo fission to segregate damaged components. They can even be completely replaced through a process called mitophagy, where old, damaged mitochondria are eliminated and new ones are generated. The key to maintaining mitochondrial health throughout life appears to be preserving these quality control mechanisms. Exercise is one of the most effective ways to enhance mitochondrial function, stimulating the production of new mitochondria and improving their efficiency. Regular physical activity can literally reverse age-related mitochondrial decline, restoring energy production to youthful levels. Certain nutritional supplements may also support mitochondrial health. Compounds like NAD plus precursors, CoQ10 and PQQ, have been shown to enhance mitochondrial function and may help prevent age-related mitochondrial decline. Some researchers believe that maintaining optimal mitochondrial function could be key to achieving significant life extension. But perhaps the most exciting developments in cellular immortality research involve understanding how cells can be completely rejuvenated through reprogramming processes. The discovery that adult cells can be converted back to embryonic-like stem cells has revolutionized our understanding of cellular aging and opened up entirely new possibilities for reversing the aging process. The process of cellular reprogramming involves exposing adult cells to specific transcription factors, the Yamanaka factors, that can reset their epigenetic state and restore their developmental potential. These reprogrammed cells, called induced pluripotent stem cells or iPSCs, behave like embryonic stem cells and can develop into any cell type in the body. But researchers have also discovered that partial reprogramming, where cells are exposed to reprogramming factors for shorter periods or at lower doses, can reverse aspects of cellular aging without completely erasing cellular identity. Partially reprogrammed cells become functionally younger while retaining their specialized characteristics. This partial reprogramming approach has been used to reverse aging in various tissues in laboratory animals. Researchers have restored vision in aged mice by partially reprogramming retinal cells, rejuvenated muscle tissue in elderly animals, and even improved cognitive function by reprogramming brain cells. The implications for human medicine are profound. If partial reprogramming techniques can be safely applied to human tissues, we might be able to literally turn back the biological clock, making old organs function like young ones again. Instead of just slowing the aging process, we could reverse it. Clinical trials of cellular reprogramming therapies are already beginning for certain applications. Companies are developing treatments for age-related macular degeneration using reprogrammed retinal cells. Others are working on therapies for heart disease, neurodegeneration, and other age-related conditions using various reprogramming approaches. But the ultimate goal of cellular immortality research is to develop comprehensive interventions that can maintain cellular health and function indefinitely. This might involve combining multiple approaches, genetic modifications that enhance natural longevity mechanisms, pharmaceutical interventions that activate cellular maintenance pathways, periodic cellular reprogramming to reverse accumulated aging damage, and lifestyle optimization to support all of these processes. The technology to implement many of these interventions already exists or is in advanced development. Gene therapy techniques can modify human cells to express enhanced versions of longevity genes. Drug delivery systems can target specific cellular pathways involved in aging. Cellular reprogramming protocols can rejuvenate aged tissues. The main barriers now are regulatory approval and ensuring safety for long-term use. Some researchers believe that comprehensive cellular immortality therapies could be available within the next 2 to 3 decades. The scientific foundations are already well established, and the pace of technological development in biotechnology and medicine is accelerating rapidly. But achieving cellular immortality also requires addressing the broader biological systems that support cellular function. Cells don't exist in isolation. They're part of complex tissues and organs that must work together to maintain health and function. Immortal cells would be of little use if the organs they comprise still fail due to structural problems or systemic dysfunctions. This is where we can learn from creatures like certain trees that achieve functional immortality through system-level approaches. The Pando aspen grove, which we mentioned earlier, achieves its remarkable longevity not just through cellular immortality, but through a distributed organizational structure that can survive and adapt to changing conditions over millennia. Pando consists of thousands of individual tree stems connected by a shared root system. When individual stems die due to disease, fire, or other causes, new stems can grow from the root system to replace them. The genetic individual, the root system and its associated genome, persists even as the visible components, the individual trees, are periodically replaced. This distributed approach to immortality suggests that human longevity might also require system-level interventions that go beyond just maintaining individual cells. We might need to develop ways to periodically regenerate or replace entire organs, while maintaining the continuity of the overall organism. Advances in regenerative medicine are already moving in this direction. Researchers can now grow functional organs in laboratory conditions using a patient's own stem cells. These lab-grown organs can potentially replace diseased or aged organs while being genetically identical to the patient, eliminating the risk of immune rejection. Three-dimensional bioprinting technology is advancing rapidly, allowing researchers to create complex tissue structures with precise spatial organization. Within the next decade, it might be possible to print replacement organs on demand, providing perfect biological replacements for hearts, kidneys, livers, and other organs as they wear out or become diseased. But even more ambitiously, some researchers are working on developing completely artificial organs that could outperform their biological counterparts. Artificial hearts that never wear out, artificial kidneys that filter blood more efficiently than natural kidneys, artificial livers that can process toxins more effectively than biological ones. The combination of biological and artificial organ replacement could potentially eliminate organ failure as a cause of death, allowing people to maintain optimal physiological function indefinitely by upgrading or replacing components as needed. But this raises fascinating questions about personal identity and continuity. If you gradually replace all of your organs with either lab-grown biological alternatives or artificial substitutes, are you still the same person? This is another version of the Ship of Theseus paradox that we considered earlier in relation to vampires and consciousness uploading. The answer might depend on how we understand the relationship between physical substrate and personal identity. If consciousness and identity emerge from patterns of information processing rather than from specific physical structures, then gradual replacement of biological components might not affect personal continuity any more than the natural replacement of cells and molecules that already occurs throughout our lives. Your body is already constantly replacing its components. Most of your cells are younger than you are, having been generated after your birth through ongoing processes of cell division and tissue renewal. The atoms that make up your body are constantly being exchanged with the environment through breathing, eating, drinking, and excretion. Yet you maintain a sense of continuity and identity throughout these changes. Deliberate organ replacement or enhancement might simply represent an extension of these natural processes, allowing for more comprehensive and controlled renewal of biological systems. Instead of waiting for natural processes to replace worn-out components, we could proactively upgrade or refresh our biological hardware to maintain optimal function. But the prospect of indefinite life extension through cellular immortality and organ replacement also raises important questions about resource allocation and environmental sustainability. If people live for centuries rather than decades, how do we manage population growth and resource consumption? How do we balance individual desires for extended life with collective needs for environmental sustainability? These questions become even more complex when we consider global inequities in access to life extension technologies. If expensive longevity treatments are only available to wealthy individuals or developed nations, we could see the emergence of fundamental biological inequalities that persist for centuries rather than generations. On the other hand, life extension technologies that become widely available could help address some existing global challenges. People who expect to live for centuries might invest more heavily in education, environmental protection, and long-term thinking. The accumulation of human knowledge and experience over extended lifespans could accelerate scientific and technological progress in ways that benefit everyone. The economic implications of significant life extension are also profound and largely unpredictable. Traditional economic models assume that people will work for approximately 40 to 50 years and then retire, supported by savings and social programs. If people live and work for 200 years, all of these assumptions break down. We might need to develop entirely new economic frameworks that can accommodate multi-century careers, periodic career changes and retraining, and the accumulation of wealth and resources over extended timescales. The concept of retirement might become obsolete, replaced by periodic sabbaticals for renewal and reinvention throughout extended lifespans. Educational systems would also need fundamental restructuring. Instead of front-loading education into childhood and young adulthood, learning would need to become a lifelong endeavour. People might pursue multiple degrees and careers throughout their extended lives, continuously adapting their skills and knowledge to changing circumstances. But perhaps the most significant implications of cellular immortality involve the potential for human enhancement beyond normal biological limits. The same technologies that could eliminate aging might also enable improvements in cognitive function, physical capabilities, and sensory perception that go far beyond what natural evolution has provided. Genetic modifications that enhance cellular repair mechanisms might also boost cognitive performance. Pharmaceutical interventions that activate longevity pathways might improve memory and learning capacity. Cellular reprogramming techniques might be able to enhance brain function and sensory abilities. We might be approaching a future where the distinction between medical treatment and human enhancement becomes increasingly blurred. Therapies designed to prevent age-related cognitive decline might also improve intelligence beyond normal human ranges. Interventions intended to maintain physical health might also enhance strength, speed, and endurance beyond natural limits. These possibilities raise important ethical questions about human enhancement and social equity. If enhancement technologies are expensive and not universally available, they could create new forms of inequality based on biological capabilities rather than just social or economic factors. But they also offer extraordinary possibilities for human flourishing and achievement. Enhanced cognitive abilities could accelerate scientific and technological progress. Improved physical capabilities could enable new forms of artistic expression and athletic achievement. Extended lifespans, combined with enhanced abilities, could allow individuals to reach levels of expertise and creative accomplishment that are impossible within normal human constraints. The convergence of cellular immortality, organ replacement, and human enhancement technologies could fundamentally transform what it means to be human. We might be approaching a future where biological limitations that have constrained human potential throughout history become optional rather than inevitable. But returning to the cellular fountain of youth that exists within each of us, the most immediate and practical implications involve the lifestyle choices and medical interventions that are already available or in development. We don't have to wait for advanced genetic modifications or cellular reprogramming therapies to begin benefiting from longevity research. Many of the most powerful anti-aging interventions can be implemented right now through evidence-based lifestyle modifications. Regular exercise activates many of the same cellular pathways that are enhanced in naturally long-lived animals. Optimal nutrition can provide the raw materials needed for cellular repair and maintenance. Stress management techniques can reduce the chronic inflammation that accelerates aging. Sleep optimization is particularly important for cellular health and longevity. During sleep, the brain's lymphatic system becomes more active, clearing out toxic proteins that accumulate during waking hours. Sleep is also when many cellular repair and maintenance processes are most active. People who consistently get high-quality sleep tend to age more slowly and live longer than those who are chronically sleep-deprived. Intermittent fasting and caloric restriction can activate cellular stress response pathways that enhance repair and maintenance. These interventions don't require expensive technologies or medical procedures, just changes in eating patterns that can significantly impact cellular aging processes. Social connections and sense of purpose also appear to influence biological aging through mechanisms that are still being studied. People with strong relationships and meaningful goals tend to have lower levels of chronic inflammation, better immune function, and slower cellular aging than those who are isolated or feel that their lives lack meaning. The remarkable thing about these lifestyle interventions is that they often provide immediate benefits while also contributing to long-term longevity. People who adopt evidence-based longevity practices typically report better energy, improved mood, enhanced cognitive function, and greater physical capacity within weeks or months of making changes. This suggests that the cellular fountain of youth isn't just a future possibility, it's already partially accessible through optimizing the biological processes that already exist within us. We can begin activating our cellular repair and maintenance systems immediately while we wait for more advanced medical technologies to become available. The pharmaceutical interventions that are currently in development could significantly amplify the effects of lifestyle modifications. Drugs that enhance autophagy, activate sirtuins, or boost mitochondrial function could provide anti-aging benefits that are difficult to achieve through lifestyle alone. Metformin, the diabetes drug that appears to have anti-aging properties, is already being prescribed off-label by some physicians for longevity purposes. Rapamycin is being used experimentally by some individuals seeking life extension benefits, though its long-term effects in healthy people are still being studied. NAD+ boosters, supplements that enhance cellular energy metabolism, are widely available and have shown promising results in animal studies and early human trials. These compounds could potentially slow cellular aging and improve health span without requiring prescription medications. But the most exciting developments involve the integration of multiple approaches to create comprehensive anti-aging protocols. Instead of relying on a single intervention, future longevity medicine will likely combine genetic modifications, pharmaceutical treatments, cellular reprogramming, organ replacement, and lifestyle optimization in personalized packages tailored to individual needs and circumstances. Some people might benefit most from genetic modifications that enhance their natural DNA repair mechanisms. Others might respond better to pharmaceutical interventions that activate specific longevity pathways. Still, others might achieve the best results through optimized nutrition and exercise programs, combined with periodic cellular rejuvenation therapies. The key insight from studying creatures like lobsters, immortal jellyfish, and hydras is that biological immortality isn't a single solution, but rather a collection of complementary strategies that work together to maintain cellular and organismal function indefinitely. Humans will likely need similarly comprehensive approaches that address all of the different mechanisms that contribute to aging and death. But we also have advantages that these naturally immortal creatures lack. We have advanced medical technologies that can intervene in biological processes with precision and control that would be impossible through natural evolution alone. We can design and implement longevity strategies that are more sophisticated and effective than anything that evolution has produced. We also have the ability to modify our environment and behavior in ways that support longevity goals. We can eliminate many of the environmental stressors and risk factors that contribute to aging and death. We can optimize our nutrition, exercise, and lifestyle choices based on scientific understanding rather than evolutionary constraints. Most importantly, we have the cognitive capacity to understand and manipulate the biological processes that control aging and longevity. We can study creatures like lobsters and hydras, identify the mechanisms that make them biologically immortal, and then engineer those same mechanisms into human biology. The cellular fountain of youth that Ponce de Leon searched for in the physical world actually exists in the biological world, encoded in the genetic instructions that guide cellular development and maintenance. We're learning how to read these instructions, understand how they work, and modify them to achieve the longevity that humans have always dreamed of. The question is no longer whether significant life extension is possible, but how quickly we can develop safe and effective interventions and how widely we can make them available. The basic science is already well established. The technological tools are being developed rapidly, and early interventions are already showing promising results. We might truly be living in the last generation that has to accept aging and death as inevitable biological facts. The children being born today might live to see their own children, grandchildren, great-grandchildren, and many generations beyond, not through some supernatural intervention, but through the careful application of scientific knowledge to the biological processes that control human lifespan. The vampire's dream of eternal life, the alchemist's search for the philosopher's stone, Ponce de Leon's quest for the fountain of youth, all of these ancient aspirations might be achievable through the practical application of modern biological science. We're not trying to violate the laws of nature or discover magical solutions to mortality. We're learning how nature already solves the aging problem in other species and figuring out how to apply those solutions to human biology. The immortal creatures that exist in nature prove that biological immortality is possible within the constraints of natural law. The challenge for human longevity research is to understand how these creatures achieve their immortality and then adapt those mechanisms for human physiology and human society. But as we've seen throughout this exploration, the achievement of biological immortality would represent just the beginning of a much larger transformation in human existence. Extended lifespans would enable forms of learning, creativity, and achievement that are impossible within the constraints of normal human mortality. They would allow for the accumulation of wisdom and experience over timescales that dwarf individual human generations. They would also require fundamental changes in how we organize society, manage resources, and think about individual identity and purpose. The prospect of living for centuries or millennia raises questions about human nature and human potential that we're only beginning to grapple with. But these are good problems to have, challenges that arise from success rather than failure, complications that emerge from achieving something that humans have wanted for thousands of years rather than from continuing to accept limitations that may no longer be necessary. As we prepare for sleep tonight, we might be among the last generation of humans to drift off with the assumption that our time is necessarily limited, that aging is inevitable, that death is the final chapter of every human story. Tomorrow's children might grow up with very different assumptions about human potential and the nature of mortality itself. The fountain of youth flows not through some distant land, but through the cellular machinery that already exists within us, waiting to be understood, activated, and optimized. The keys to biological immortality lie not in supernatural intervention, but in natural biological processes that we're learning to control and enhance. Ponce de Leon was searching in the wrong place for something that actually exists. The immortal creatures that have captured human imagination throughout history aren't fantasy beings, but natural organisms that demonstrate the possibility of indefinite biological existence. The vampire's promise of eternal life might be achievable without fangs, blood, or supernatural transformation, simply through the careful application of biological knowledge to human physiology. We stand at the threshold of potentially the most significant development in human history, the possibility of transcending the biological limitations that have constrained human potential since our species first emerged. The death problem, as some researchers now call it, might actually be solvable through science rather than magic, through understanding rather than wishful thinking, through careful research rather than desperate searching in remote locations. The ancient myths about immortality weren't just stories. They were expressions of human intuition about possibilities that modern science is finally beginning to realize. The lobster's biological immortality isn't just a curious fact about arthropod biology. It's a demonstration that indefinite cellular lifespan is compatible with complex multicellular life. The hydra's regenerative immortality isn't just an interesting feature of simple organisms, it's proof that biological systems can maintain themselves indefinitely under the right conditions. Most importantly, the cellular fountain of youth isn't just a poetic metaphor, it's a literal description of the genetic and molecular machinery that exists within every human cell. Machinery that we're learning to understand, control, and optimize for human longevity and enhancement. This brings us to one of the most fascinating aspects of contemporary immortality research: the fact that some of the world's wealthiest and most influential people are betting their fortunes on the possibility that death is an engineering problem waiting to be solved. Silicon Valley has become the modern equivalent of Ponce de Leon's expedition, except instead of searching through swamps and jungles, today's explorers are funding laboratories and biotech companies in pursuit of the same ancient dream. The billionaire's obsession with defeating death represents something unprecedented in human history. Never before have individuals with such vast resources and technological sophistication focused so intensively on the problem of mortality. These aren't medieval alchemists working with primitive equipment and wishful thinking. These are some of the smartest, most successful people on the planet, individuals who have already solved seemingly impossible engineering challenges, and they're convinced that aging and death are simply the next problems to tackle. Peter Thiel, the co-founder of PayPal and one of the earliest investors in Facebook, has become perhaps the most vocal advocate for what he calls the war on death. Thiel doesn't just talk about life extension as a distant possibility, he treats it as a moral imperative and a practical necessity. In his view, death is the greatest enemy that humanity faces, responsible for more suffering than war, disease, and natural disasters combined. Thiel has invested hundreds of millions of dollars in longevity research through his various venture capital funds and philanthropic efforts. He's funding research into everything from genetic therapies that could extend cellular lifespan to artificial organs that could replace failing biological systems. He's also personally experimenting with various life extension protocols, including a controversial procedure called parabiosis, where he receives transfusions of blood from young donors. The parabiosis experiments that Thiel has reportedly undergone are based on research showing that young blood contains factors that can rejuvenate aged tissues. When old mice are connected to the circulatory systems of young mice, their muscle strength improves, their cognitive function enhances, and various markers of aging are reversed. The idea is that young blood contains proteins and other molecules that can essentially reset the biological clocks of older organisms. While the scientific evidence for parabiosis is compelling in animal studies, the translation to humans is still experimental and controversial. The procedures are expensive, the long-term effects are unknown, and there are significant ethical concerns about creating a market for young people's blood. But Thiel's willingness to experiment on himself demonstrates the level of commitment that some individuals are bringing to the pursuit of life extension. Jeff Bezos, the founder of Amazon and one of the world's richest individuals, has taken a different but equally ambitious approach to the longevity challenge. Through his venture capital firm, Bezos Expeditions, he's invested heavily in a company called Unity Biotechnology, which is developing drugs that can eliminate senescent cells from the body. Unity's approach is based on the recognition that senescent cells, cells that have stopped dividing but haven't died, accumulate in tissues as we age and contribute to age-related diseases through the inflammatory compounds they secrete. By developing drugs that can selectively eliminate these problematic cells while leaving healthy cells unharmed, Unity hopes to essentially clean house in the aging body, removing the cellular debris that contributes to decline and dysfunction. The company's lead drug candidate has shown promising results in early clinical trials for osteoarthritis, with patients experiencing significant improvements in joint function and pain reduction. If successful, senolytic drugs could provide a relatively simple way to slow aging and improve health span by periodically clearing out the cellular junk that accumulates over time. Bezos has also invested in other longevity-focused companies, including Altus Labs, a company that was founded specifically to work on cellular reprogramming technologies for age reversal. Altus has attracted some of the world's leading experts in aging research and has raised over $3 billion to pursue ambitious goals like reversing aging at the cellular level and extending healthy human lifespan by decades. The level of funding that companies like Altus have attracted represents a fundamental shift in how longevity research is being approached. Instead of relying primarily on government funding and academic research, which tends to be conservative and slow-moving, private investors are pouring billions of dollars into high-risk, high-reward approaches that could potentially achieve dramatic life extension within the next few decades. Google's approach to longevity research through its subsidiary Calico Labs represents yet another model for how technology companies are tackling the aging problem. Calico, which stands for California Life Company, was founded with the explicit goal of understanding the biology of aging and developing interventions that could significantly extend healthy human lifespan. Unlike traditional pharmaceutical companies that focus on treating specific diseases, Calico is taking a more fundamental approach, trying to understand the basic biological processes that cause aging and then developing interventions that target these root causes rather than just symptoms. They're using advanced computational approaches, including artificial intelligence and machine learning, to analyze massive datasets about aging and identify potential targets for intervention. Calico has partnerships with major pharmaceutical companies like AbbVie, allowing them to combine Google's computational expertise with traditional drug development capabilities. They're working on everything from genetic therapies that could enhance cellular repair mechanisms to drugs that could modulate the fundamental pathways that control aging. The company has been relatively secretive about its specific research programs, but they've published papers on topics like the genetics of exceptional longevity and the role of cellular senescence in aging. They've also made significant investments in research infrastructure, including a state-of-the-art research facility that's designed specifically for aging research. What's particularly interesting about the tech industry's approach to longevity is how they are applying the same mindset that has revolutionized computing and communications to biological problems. They're treating aging as an information processing challenge, a complex system that can be understood, modeled, and ultimately reprogrammed to achieve better outcomes. This computational approach to biology is enabling new kinds of research that weren't possible before. Instead of relying solely on traditional experimental methods, researchers can now use artificial intelligence to analyze genetic data from thousands of individuals, identify patterns that might not be apparent to human researchers, and design interventions based on these computational insights. Machine learning algorithms are being used to identify genetic variants associated with exceptional longevity, predict which interventions might be most effective for individual patients, and even design new drugs that could target specific aging mechanisms. The same technologies that have transformed industries like transportation, communication, and entertainment are now being applied to the fundamental challenge of human mortality. Oracle founder Larry Ellison has taken yet another approach, focusing his longevity investments on more immediate and practical interventions. Through his foundation, Ellison has funded research into anti-aging drugs, genetic therapies, and medical technologies that could extend healthy lifespan within the next decade rather than waiting for more speculative breakthroughs. Ellison's investments have supported research into drugs like rapamycin and metformin, which show promise for slowing aging in humans based on their effects in laboratory animals. He's also funded research into genetic factors that contribute to exceptional longevity, hoping to identify interventions that could provide similar benefits to people who don't naturally carry protective genetic variants. The billionaire focus on longevity research has created a unique ecosystem where academic researchers, biotech entrepreneurs, and technology companies are collaborating in ways that weren't possible before. The influx of private funding has accelerated research timelines, enabled more ambitious projects, and attracted top talent from other fields to work on aging-related challenges. But this concentration of longevity research in the hands of wealthy individuals and technology companies also raises important questions about equity and access. If effective life extension technologies are developed primarily through private funding, will they be available only to those who can afford them? Could we see the emergence of a longevity divide where the wealthy live for centuries while others remain constrained by normal human lifespans? These concerns are not merely theoretical. Many of the most promising longevity interventions being developed are likely to be expensive, at least initially. Genetic therapies can cost hundreds of thousands of dollars per treatment. Cellular reprogramming procedures require sophisticated laboratory facilities and highly trained personnel. Even relatively simple interventions like parabiosis or senolytic drugs could be priced out of reach for most people. But the technology industry's approach to longevity research is also influenced by a particular worldview that sees aging and death as engineering problems that can be solved through sufficient intelligence and resources. This perspective has been enormously successful in other domains, enabling the development of technologies that seemed impossible just decades ago. But biological systems are more complex than computer systems in many ways. They've evolved over billions of years to balance competing demands and constraints that might not be immediately apparent to engineers and computer scientists. The assumption that aging can be solved like a software bug might be overly optimistic, even with unlimited funding and the brightest minds working on the problem. On the other hand, the tech industry's approach has already produced some remarkable successes. The cost of genetic sequencing has dropped by orders of magnitude in just a few decades, making personalized medicine possible. Artificial intelligence has accelerated drug discovery and enabled new approaches to understanding complex biological systems. The computational tools being developed for longevity research are likely to have applications far beyond life extension. Elon Musk, while not as directly focused on longevity research as some of his peers, has approached the problem from a different angle through his work on brain-computer interfaces. His company Neuralink is developing technologies that could potentially preserve human consciousness by creating direct connections between brains and digital systems. The idea is that if human consciousness could be augmented or backed up through technological means, we might be able to transcend biological limitations entirely. Instead of trying to keep biological brains alive indefinitely, we could potentially transfer human consciousness to more durable substrates or create hybrid biological digital systems that combine the best features of both. This approach to immortality through consciousness preservation represents a radical departure from traditional biological approaches to life extension. Instead of trying to maintain the same physical body indefinitely, it envisions a future where human minds could exist in various forms, sometimes in biological bodies, sometimes in digital systems, sometimes in hybrid configurations that we can barely imagine today. The technical challenges involved in consciousness preservation are staggering, and many neuroscientists are skeptical that human consciousness can be reduced to patterns of information that could be preserved or transferred. But Musk's work on brain-computer interfaces is already producing remarkable results, enabling paralyzed patients to control computers and robotic devices through thought alone. Mark Zuckerberg has taken a more indirect approach to longevity research through the Chan Zuckerberg Initiative, which he founded with his wife Priscilla Chan. Their goal is to cure, prevent or manage all human diseases by the end of the 21st century, which would effectively eliminate most causes of death and dramatically extend human lifespan. The Chan Zuckerberg Initiative is funding research into basic biological processes, disease mechanisms, and therapeutic interventions across a wide range of conditions. While they're not explicitly focused on aging research, many of their funded projects have implications for longevity and health span extension. Their approach emphasizes the development of new scientific tools and technologies that can accelerate research across many different fields. They're funding the development of advanced microscopy techniques, computational tools for biological research, and new methods for studying human development and disease. This focus on research infrastructure and tools could have profound long-term impacts on longevity research. Many of the limitations in current aging research stem from the lack of appropriate tools for studying complex biological systems over long timescales. By developing better instruments and methodologies, the Chan Zuckerberg Initiative could enable breakthroughs that wouldn't be possible with current technology. The involvement of technology billionaires in longevity research has also changed the culture and expectations around aging research. Instead of accepting aging as a natural and inevitable process, there's a growing sense that death is an optional limitation that can be overcome through sufficient intelligence and effort. This shift in perspective has attracted new talent to the field and encouraged more ambitious research goals. Young scientists who might have gone into computer science or engineering are now choosing to work on biological problems related to aging and longevity. Entrepreneurs are founding companies specifically focused on life extension rather than just treating age-related diseases. The result is a kind of positive feedback loop where increased funding and attention attract more talent, which leads to faster progress, which attracts even more funding and talent. The field of longevity research is growing exponentially, with new companies, research programs, and clinical trials being announced regularly. But the billionaire's obsession with defeating death also reflects deeper anxieties about mortality and control that are particularly acute among people who have achieved extraordinary success in other domains. These are individuals who are accustomed to solving problems through intelligence, hard work, and resource allocation. The prospect of death represents perhaps the only challenge that can't be overcome through conventional means. For people who have built global empires and transformed entire industries, the idea that they might be defeated by something as mundane as biological aging is particularly galling. They've spent their lives proving that seemingly impossible challenges can be overcome through innovative thinking and aggressive execution. Why should mortality be any different? This psychological dimension of the longevity research boom is important because it helps explain the level of commitment and resources being devoted to the problem. These aren't people who are casually interested in living a little longer or staying a little healthier as they age. They're individuals who see death as an unacceptable limitation on their ability to continue contributing to human progress and achieving their goals. The sense of urgency around longevity research is also influenced by demographic realities. Many of the billionaires funding this research are in their 50s, 60s, or 70s. They don't have the luxury of waiting decades for breakthrough treatments to be developed. They need solutions that can be implemented within the next 10 to 20 years if they're going to personally benefit from the research they're funding. This time pressure has led to some controversial approaches, including self-experimentation with unproven treatments, investment in speculative therapies that might not work, and advocacy for accelerated regulatory approval processes that could potentially compromise safety. The billionaire longevity researchers are essentially betting their own lives on the success of their investments. But their willingness to take these risks has also accelerated progress in ways that might not have been possible through traditional research channels. Academic research institutions and government agencies are typically very conservative about funding speculative research or approving experimental treatments. Private investors can move much more quickly and take bigger risks. The competition between different billionaire-funded research programs has also created a kind of longevity race, where teams are competing to achieve breakthrough results first. This competitive dynamic can drive innovation and accelerate progress, though it can also lead to premature claims and overhyped results. Some critics argue that the billionaire focus on longevity research is fundamentally selfish, a way for wealthy individuals to buy their way out of the universal human condition while ignoring more pressing global health problems. They point out that the resources being devoted to life extension research could potentially save many more lives if they were directed toward addressing infectious diseases, malnutrition, and other problems that primarily affect poor populations. But supporters of longevity research argue that the benefits of defeating aging would ultimately be available to everyone, not just the wealthy individuals who funded the initial research. They point to other technologies that were initially expensive and exclusive but eventually became widely available, like computers, smartphones, and internet access. The development of effective longevity treatments could follow a similar pattern, starting with expensive experimental procedures available only to wealthy early adopters, then gradually becoming more affordable and accessible as the technology improves and scales up. Eventually, life extension treatments might become as routine and affordable as vaccines or antibiotics. This potential for democratization is one reason why some researchers and ethicists support the billionaire-funded approach to longevity research, despite concerns about equity and access. They argue that private funding can accelerate research in ways that wouldn't be possible through public funding alone, and that the ultimate benefits could be enormous for all of humanity. The global impact of successful longevity research would indeed be transformative. If aging could be eliminated or significantly slowed, it would prevent millions of deaths every year and improve the quality of life for billions of people. The economic benefits alone would be staggering, as societies would no longer need to support large populations of elderly individuals who require expensive medical care and social services. But the billionaire approach to longevity research also highlights the broader trend toward privatization of scientific research and development. Increasingly, breakthrough technologies are being developed by private companies rather than government agencies or academic institutions. This shift has both advantages and disadvantages for scientific progress and public welfare. Private funding can enable more rapid progress and more ambitious goals, But it also means that research priorities are determined by wealthy individuals and profit-seeking companies, rather than by democratic processes or public interest considerations. The longevity research being funded by billionaires reflects their particular interests and perspectives, which may not align with broader social needs or priorities. This brings us to another fascinating aspect of the contemporary immortality quest, the laboratory work that's creating what can only be described as Frankenstein's approach to conquering death. While billionaires fund the research, teams of scientists around the world are literally building new forms of human life, piece by piece, organ by organ, cell by cell. The modern Frankenstein's laboratory doesn't look like the Gothic castle workshop of Mary Shelley's imagination. Instead, it's a gleaming biotech facility filled with three-dimensional printers, bioreactors, gene sequencing machines, and microscopes powerful enough to manipulate individual molecules. But the fundamental goal is remarkably similar to Victor Frankenstein's original ambition: to defeat death by assembling life from non-living components. Three-dimensional bioprinting represents perhaps the most dramatic example of this technological approach to immortality. Researchers can now literally print living tissues using specialized printers that deposit cells instead of ink. These bioprinters can create structures as simple as skin grafts, or as complex as beating heart tissues, liver sections, or even rudimentary organs. The process starts with taking cells from a patient, often stem cells that can develop into different types of tissues. These cells are mixed with biocompatible materials that serve as scaffolding and nutrients. The bioprinter then deposits this cellular mixture layer by layer, following digital blueprints that specify exactly where each type of cell should be placed. Over the course of days or weeks, the printed structure develops into functional tissue. The cells multiply, differentiate into specialized types, and begin performing their biological functions. Blood vessels grow throughout the tissue to provide nutrients and oxygen. The artificial scaffolding dissolves away, leaving behind what is essentially a laboratory-grown replacement part for the human body. Companies like Organovo have already demonstrated the ability to print functional liver tissue that can be used for drug testing and toxicity studies. Their printed liver models can metabolize drugs, produce proteins, and perform other functions of natural liver tissue for several weeks in laboratory conditions. Other researchers have printed skin grafts that have been successfully transplanted onto burn patients, where they integrated with the patient's existing tissue and provided permanent wound healing. The printed skin contained all the major cell types found in natural skin, including blood vessels and nerve connections. The ultimate goal of bioprinting research is to create entire replacement organs that could be transplanted into patients whose own organs are failing due to disease or aging. Instead of waiting for organ donors or dealing with immune rejection problems, patients could receive organs printed from their own cells, guaranteed to be compatible and free from the diseases that affected their original organs. Several research groups have successfully printed rudimentary hearts that can beat rhythmically, though these are still far from being suitable for transplantation. Others have created kidney tissues that can filter blood and produce urine, liver sections that can process toxins, and lung tissues that can exchange gases. The challenges involved in printing complete transplantable organs are enormous. Organs like hearts, kidneys, and livers are incredibly complex structures with intricate internal architectures that must be precisely replicated for proper function. They contain multiple cell types arranged in specific patterns, complex vascular networks that supply nutrients to every cell, and control systems that coordinate their activities. But progress is accelerating rapidly as printing technologies improve and researchers develop better understanding of how to guide cellular development and organization. Some experts predict that the first bioprinted organs suitable for human transplantation could be available within the next decade. The implications for human longevity are staggering. If we can reliably print replacement organs on demand, organ failure would no longer be a cause of death. Hearts, kidneys, livers, lungs, and other vital organs could be replaced as often as necessary to maintain optimal function throughout indefinitely extended lifespans. But bioprinting is just one approach to the technological reconstruction of human biology. Researchers are also developing sophisticated artificial organs that could outperform their biological counterparts in many ways. artificial hearts that never wear out, artificial kidneys that filter blood more efficiently than natural ones, artificial livers that can process toxins more effectively than biological organs. The total artificial heart developed by Syncardia Systems has already been successfully implanted in over 1,700 patients as a bridge to heart transplantation. These artificial hearts can keep patients alive for years while they wait for donor organs, demonstrating that complex biological functions can be successfully replaced by engineered alternatives. Artificial kidney devices are being developed that could potentially free dialysis patients from the need for regular treatments. These artificial kidneys would be implanted permanently and would continuously filter the blood, providing better quality of life and potentially better health outcomes than current dialysis treatments. But perhaps the most ambitious artificial organ projects involve the brain, the organ that many people consider to be the seat of human identity and consciousness. While we're still far from being able to replace or augment entire brains, researchers are making remarkable progress in developing brain-computer interfaces that could potentially preserve or enhance human cognitive abilities. Companies like Neuralink are developing implantable devices that can read neural signals and translate them into digital commands. These devices could potentially allow paralyzed patients to control computers, robotic limbs, or other devices through thought alone. But they also raise the possibility of more fundamental interactions between human brains and digital systems. If brain-computer interfaces become sophisticated enough, they might enable the backup and restoration of human memories, the enhancement of cognitive abilities through digital processing, or even the gradual replacement of biological brain functions with artificial alternatives. This could provide a path to immortality that doesn't depend on maintaining biological tissues indefinitely. The idea of consciousness uploading, transferring human minds to digital substrates, has been a staple of science fiction for decades. But advances in neuroscience and computer technology are making it seem less fantastical and more like a genuine possibility for the future. Recent research has shown that it's possible to record and stimulate neural activity with remarkable precision. Scientists can already read simple thoughts from brain activity patterns and can influence behavior by stimulating specific brain regions. The technology for directly interfacing with human consciousness is advancing rapidly. But consciousness uploading would require understanding human consciousness itself at a much deeper level than we currently possess. We would need to know exactly which patterns of neural activity correspond to specific thoughts, memories, and aspects of personality. We would need to be able to recreate these patterns in artificial systems that could support conscious experience. These are profound challenges that may take decades or centuries to solve, but the potential payoff would be enormous. True immortality through the preservation of human consciousness in substrates that could potentially last indefinitely and be copied, backed up, or transferred between different physical systems. Even without full consciousness uploading, brain-computer interfaces could provide significant longevity benefits. They could compensate for age-related cognitive decline, enhance memory and processing speed, and provide backup systems for critical brain functions. If biological brains begin to fail with age, artificial systems could potentially take over their functions seamlessly. Researchers are also working on more direct approaches to brain preservation and repair. Stem cell therapies could potentially regenerate damaged brain tissue. Gene therapies could enhance the brain's natural repair mechanisms. Pharmaceutical interventions could prevent or reverse the molecular changes that contribute to cognitive aging. The combination of biological and technological approaches to brain health could potentially maintain cognitive function indefinitely, ensuring that extended lifespans would be accompanied by preserved mental abilities. Instead of facing the prospect of centuries of life with declining cognitive abilities, future humans might enjoy enhanced mental capabilities throughout indefinitely extended lifespans. But the Frankenstein's laboratory approach to immortality also involves more fundamental modifications to human biology. Researchers are developing genetic therapies that could enhance natural human capabilities, making us more resistant to disease, aging, and environmental challenges. CRISPR and other gene editing technologies have made it possible to modify human genetics with unprecedented precision. These tools could potentially be used to enhance natural longevity genes, repair genetic defects that contribute to aging, or even add entirely new capabilities to human biology. Some researchers are working on genetic modifications that could make humans more resistant to radiation, allowing for safer space travel and exploration of harsh environments. Others are developing genetic enhancements that could improve physical strength, endurance, or sensory capabilities. The ethical implications of human genetic enhancement are profound and controversial, but from a purely technical standpoint, the tools already exist to make significant modifications to human biology. The main barriers are regulatory rather than technological. Gene therapies for treating genetic diseases are already being approved for clinical use. The same technologies could potentially be used for enhancement purposes, blurring the line between medical treatment and human augmentation. If we can fix genetic defects that cause early death, why not enhance genetic factors that could extend healthy lifespan even further? The regenerative medicine approach to immortality focuses on enhancing the body's natural ability to repair and replace damaged tissues. Instead of replacing organs with artificial alternatives, this approach aims to maintain biological systems in optimal condition throughout extended lifespans. Stem cell therapies could potentially regenerate any type of tissue in the human body. Instead of waiting for organs to fail and then replacing them, we could periodically rejuvenate them using the body's own regenerative capabilities enhanced through medical intervention. Researchers have already demonstrated the ability to regenerate heart muscle after heart attacks, restore vision by regenerating retinal tissue, and repair spinal cord injuries using stem cell therapies. These approaches could potentially be expanded to provide comprehensive body-wide regeneration on a regular basis. The combination of genetic enhancement, artificial organ replacement, brain-computer interfaces, and regenerative medicine could create entirely new forms of human existence. Future humans might have enhanced genetics, artificial organs that outperform biological ones, digital brain augmentation, and access to complete bodily regeneration as needed. These enhanced humans would be recognizably human in many ways, retaining human consciousness, emotions, and social connections, but they would also possess capabilities that go far beyond current human limitations, potentially including indefinite lifespans, enhanced cognitive abilities, improved physical performance, and resistance to diseases and environmental challenges that would be fatal to unenhanced humans. The Frankenstein's laboratory approach to immortality represents the logical endpoint of medical technology development. If we can understand how biological systems work, we should eventually be able to repair, replace, or enhance them at will. Death would become optional. Limited lifespans would become a choice rather than an inevitability, and human capabilities could be expanded far beyond their current biological constraints. But this technological approach to immortality also raises fundamental questions about human identity and what it means to be human. If we replace most of our biological components with artificial alternatives, enhance our genetics, augment our brains with digital systems, and regenerate our tissues on a regular basis, are we still the same species that evolved on Earth millions of years ago? The answer might depend on how we define humanity and personal identity. If being human is primarily about consciousness, emotions, social connections, and cultural continuity, then technological enhancement might not change our essential nature. We would still be recognizably human, just with better tools and capabilities. But if being human is primarily about biological constraints and limitations, then technological enhancement could represent a transition to something post-human, a new form of existence that transcends traditional human categories. This brings us to our final exploration for tonight, the remarkable people who seem to have already begun this transition, individuals whose lifespans have stretched far beyond normal human limits, and who provide glimpses of what extended human existence might actually look like. These are the Methuselah Files, the carefully documented cases of people who refuse to die on schedule, and who might hold clues to the practical realities of significantly extended human lifespans. But there's something even more profound we need to explore together. Something that pushes the boundaries of what it means to be human in ways that might make cellular reprogramming seem almost quaint by comparison. We're venturing into territory where the line between biology and technology doesn't just blur, it disappears entirely, where consciousness itself becomes something we can potentially copy, transfer, and preserve beyond the fragile vessel of flesh and bone that currently houses it. The idea of uploading human consciousness, of creating what some call digital souls, has long been the province of science fiction writers and futurists who dream in silicon and code. But here's where things get genuinely fascinating, and perhaps a little unsettling in the most wonderful way. The distance between science fiction and scientific possibility has been shrinking at an almost alarming rate, and we're now at a point where some of the most brilliant minds in neuroscience, computer science, and philosophy are asking not whether consciousness can be digitized, but when and how. Ray Kurzweil, the inventor, futurist, and now director of engineering at Google, has been making predictions about this technological convergence for decades. His track record is remarkable enough to make even skeptics pause and listen. He predicted the rise of the internet, the defeat of world chess champions by artificial intelligence, the development of portable computers that could access wireless information networks, and the emergence of speech recognition technology, all with startling accuracy. When Kurzweil talks about consciousness uploading, he's not engaging in wishful thinking or science fiction fantasizing. He's extrapolating from observable trends in computational power, brain scanning technology, and our growing understanding of neural networks. According to Kurzweil's timeline, by the 2030s, we'll have the computational power and understanding necessary to create detailed simulations of human brains. By the 2040s, he predicts we'll be able to upload human consciousness to digital substrates, effectively achieving a form of immortality that sidesteps biological limitations entirely. These aren't random dates pulled from thin air. They're based on his analysis of exponential improvements in computing power, the miniaturization of brain scanning technology, and the accelerating pace of neuroscientific discovery. But let's pause here and consider what consciousness uploading actually means, because the concept is far more complex and philosophically rich than it might initially appear. When we talk about uploading consciousness, we're not simply talking about creating a copy of someone's memories or personality traits. We're talking about the fundamental question of what makes you, you. Is your consciousness simply the pattern of neural connections in your brain, the specific way information flows through biological circuits, or is there something more, something that couldn't be replicated in silicon and code? This question touches on one of the deepest mysteries in all of science, the hard problem of consciousness. Neuroscientist David Chalmers coined this term to describe the challenge of explaining why we have subjective, first-person experiences at all. It's relatively easy from a scientific perspective to explain the functional aspects of consciousness, how the brain processes information, forms memories, makes decisions. But explaining why there's something it's like to be you, why you have an inner experience of redness when you see a red rose, or an inner experience of joy when you hear your favourite song, that remains profoundly mysterious. When it comes to consciousness uploading, this mystery becomes intensely practical. If we create a perfect digital replica of your brain, complete with all the same neural connections and patterns of activity, would that digital entity be you? Or would it be a copy that thinks it's you while the real you ceased to exist when your biological brain stopped functioning? This isn't just philosophical navel-gazing. The answer to this question determines whether consciousness uploading represents genuine immortality or an elaborate form of suicide followed by the creation of a digital imposter. The philosophical puzzle becomes even more intricate when we consider the continuity of identity over time. Right now, as you listen to this, the atoms in your body are constantly being replaced. The cells in your brain are regularly recycled, with new proteins being synthesized and old ones being broken down. In a very real sense, you're not physically the same person you were 7 years ago, yet you feel like the same continuous self. This suggests that identity might indeed be more about pattern than substrate, more about the organization of information than the specific matter in which that information is encoded. Recent advances in neuroscience are providing tantalizing clues about how consciousness might work and whether it could theoretically be replicated in digital form. The Connectome project, an ambitious attempt to map every neural connection in the human brain, is making steady progress. We've already mapped the complete connectomy of simpler organisms like the roundworm C. elegans, which has exactly 302 neurons and 7,000 synaptic connections. More impressively, researchers have used this connectomy to create computer simulations that can replicate many of the worm's behaviours. But scaling from 300 neurons to the roughly 86 billion neurons in the human brain represents a challenge that's not just quantitative, but qualitative. The human brain isn't simply a larger version of a worm's brain. It has emergent properties, layers of complexity and recursive loops that create something far greater than the sum of its parts. The prefrontal cortex alone, responsible for abstract reasoning and planning, contains circuits of staggering complexity that we're only beginning to understand. Yet the progress in brain simulation technology is genuinely remarkable. The Blue Brain project, led by Henry Markram at the Swiss Federal Institute of Technology, has successfully simulated small columns of rat brain tissue with extraordinary detail. These simulations include not just the electrical activity of neurons, but also the complex biochemical processes that support neural function. When stimulated, these digital brain columns respond in ways that are virtually indistinguishable from their biological counterparts. Even more intriguingly, recent work in artificial intelligence has shown that when you scale up neural networks to sufficient size and complexity, they begin to exhibit emergent behaviors that weren't explicitly programmed. Large language models, for instance, develop the ability to reason about abstract concepts, engage in creative problem solving, and even demonstrate what appears to be a form of self-reflection, despite being trained simply to predict the next word in a sequence. This suggests that consciousness might indeed be an emergent property of sufficiently complex information processing systems, regardless of whether those systems are biological or digital. The implications of this possibility are staggering. If consciousness can be replicated in digital form, then death becomes optional in a way that goes beyond even the most ambitious biological life extension technologies. A digital consciousness wouldn't be subject to cellular aging, genetic diseases, or the physical vulnerabilities that plague biological bodies. It could potentially exist for as long as the technology to support it continues to function, backed up and replicated across multiple systems to ensure its preservation. But this digital immortality would come with its own unique challenges and philosophical puzzles. Would a digital consciousness experience time in the same way we do? Could it be slowed down or sped up? Could multiple copies exist simultaneously? And perhaps, most importantly, would such an existence feel meaningful and fulfilling to the consciousness experiencing it? Kurzweil envisions a future where consciousness uploading isn't a binary transition from biological to digital existence, but rather a gradual merger. He predicts that we'll first develop brain-computer interfaces that allow seamless communication between biological neural networks and artificial ones. Over time, more and more of our cognitive processing might be offloaded to digital systems until the boundary between biological and artificial intelligence becomes meaningless. In this scenario, consciousness uploading wouldn't feel like death and resurrection, but like a natural extension of capacities we'd already been using for years or decades. This gradual approach might resolve some of the philosophical puzzles about identity and continuity. If your consciousness slowly expands to include digital components, with no sharp transition point, then questions about whether the final result is really you become less pressing. You'd experience the entire process from the inside, maintaining a sense of continuous identity throughout the transformation. But even if consciousness uploading proves technically feasible, it raises profound questions about the nature of human experience and what we value about existence. Would a digital consciousness still feel emotions in the same way? Would it experience beauty, love, wonder, sadness? Or would these distinctly biological experiences be lost in translation to digital substrate? Some philosophers and neuroscientists argue that emotions are so deeply tied to our biological heritage, to the ancient brain structures we share with other animals, that they couldn't be meaningfully replicated in digital form. Others suggest that any sufficiently complex information processing system would necessarily develop analogous experiences, perhaps even richer and more nuanced than what biological brains can support. The question becomes even more complex when we consider the social and relational aspects of consciousness. Human experience is fundamentally social. We develop our sense of self in relationship to others, and our consciousness is shaped by countless interactions with other conscious beings. Would digital consciousnesses be able to form genuine relationships with each other and with biological humans? Would they experience loneliness, companionship, love? These aren't merely academic questions. If consciousness uploading becomes possible, these philosophical puzzles will become practical realities that individuals and societies will have to navigate. The decisions we make about these technologies will shape not just the future of individual human lives, but the entire trajectory of consciousness in the universe. Meanwhile, while philosophers and futurists debate the possibility of digital immortality, medical researchers are making remarkable progress against humanity's oldest and most feared enemies. The diseases that have plagued our species for millennia, cancer, heart disease, neurodegenerative disorders, are beginning to yield to an unprecedented arsenal of sophisticated therapeutic weapons. We're not just treating these diseases more effectively, we're moving toward a future where many of them might be eliminated entirely. Cancer, perhaps the most feared word in the human vocabulary, has been humanity's shadow companion throughout history. Archaeological evidence shows that even our ancient ancestors suffered from malignant tumours. For most of human history, a cancer diagnosis was essentially a death sentence, a cruel lottery ticket that no one wanted to win. But in the last few decades, and especially in the last few years, our understanding of cancer and our ability to fight it have undergone a revolution so profound that it's reshaping not just medicine, but our entire relationship with mortality itself. The transformation begins with our understanding of what cancer actually is. For generations, we thought of cancer as a single disease, a malignant enemy to be fought with the blunt instruments of surgery, radiation, and chemotherapy. These approaches, while sometimes effective, were like trying to perform microsurgery with a sledgehammer. They attacked cancer cells, but they also damaged healthy tissue, often causing side effects that were nearly as devastating as the disease itself. But cancer isn't really one disease. It's hundreds of different diseases, each with its own genetic signature, its own patterns of growth and spread, its own vulnerabilities. A lung cancer in one patient might be genetically more similar to a brain cancer in another patient than to a different lung cancer in a third patient. This realization has led to the development of precision medicine, treatments tailored not just to the type of cancer but to the specific genetic characteristics of each individual tumor. The CRISPR revolution has turbocharged this precision approach to cancer treatment. CRISPR, which stands for Clustered Regularly Interspaced Short Palindromic Repeats, is a gene editing tool that allows scientists to make precise changes to DNA with unprecedented accuracy and efficiency. It's like having a word processor for the genetic code, with the ability to find specific sequences, delete them, and insert new ones with remarkable precision. In cancer treatment, CRISPR is being used in several revolutionary ways. One approach involves editing the patient's own immune cells to make them more effective cancer fighters. T cells, the soldiers of the immune system, normally have built-in safety mechanisms that prevent them from attacking the body's own tissues. While this is usually beneficial, it can also prevent them from effectively targeting cancer cells, which are, after all, the body's own cells gone rogue. Using CRISPR, researchers can edit T cells to remove these safety constraints and enhance their ability to recognize and attack cancer cells. This approach, called CAR T-cell therapy, has shown remarkable success in treating certain blood cancers that were previously considered incurable. Patients with advanced leukemia who had exhausted all other treatment options have experienced complete remissions that have lasted for years. But the success stories go beyond blood cancers. Researchers are developing CRISPR-based approaches to solid tumours as well, engineering immune cells that can penetrate the defensive barriers that tumours erect around themselves. Some of the most exciting recent results involve editing multiple genes simultaneously, creating superpowered immune cells that can overcome the various escape mechanisms that cancer cells use to evade immune surveillance. The beauty of these approaches is that they harness the body's own sophisticated anti-cancer machinery, rather than trying to replace it with crude external interventions. The immune system has evolved over millions of years to detect and eliminate abnormal cells. Cancer succeeds when it finds ways to hide from or disable this natural surveillance system. CRISPR-based therapies essentially repair and enhance these natural defenses, allowing the body to do what it was designed to do but with greater precision and power. Even more promising is the development of in vivo gene editing, where CRISPR components are delivered directly to tumours inside the patient's body, rather than editing cells in the laboratory and then reinfusing them. This approach could make sophisticated gene therapies much more accessible and affordable, turning what are currently experimental treatments available only at specialised medical centres into routine therapies that could be administered in community hospitals. The progress isn't limited to CRISPR. Cancer immunotherapy, the approach of training the immune system to fight cancer, has evolved far beyond the early experiments that showed modest benefits in small numbers of patients. Checkpoint inhibitors, drugs that remove the molecular brakes that prevent immune cells from attacking tumours, have transformed the treatment landscape for numerous cancer types. Melanoma, once almost universally fatal when it spread beyond the skin, now has 5-year survival rates approaching 70% in patients with advanced disease. Combination therapies are proving even more effective. By attacking cancer through multiple mechanisms simultaneously, blocking its ability to develop resistance, these approaches are achieving response rates that would have been considered impossible just a few years ago. Some patients with advanced cancer are experiencing not just temporary remissions, but apparent cures, with no detectable cancer remaining years after treatment. The development of liquid biopsies represents another revolutionary advance. These blood tests can detect circulating tumour DNA, tiny fragments of genetic material shed by cancer cells into the bloodstream. This technology allows doctors to monitor cancer progression and treatment response in real time, adjusting therapies based on how the tumour is evolving genetically. More importantly, liquid biopsies can detect cancer recurrence months or even years before it would be visible on imaging studies, creating opportunities for intervention when the disease burden is minimal and treatment is most likely to be successful. Perhaps most exciting is the progress in cancer prevention through genetic screening and intervention. We now know that many cancers are caused by inherited genetic mutations that dramatically increase cancer risk. The BRCA mutations that increase breast and ovarian cancer risk are the most famous examples, but researchers have identified dozens of other cancer predisposition genes. For people with these mutations, we're developing increasingly sophisticated prevention strategies. Some involve enhanced surveillance, using advanced imaging and biomarker testing to detect cancer at the earliest possible stages when it's most treatable. Others involve prophylactic treatments, medications that can reduce cancer risk by 70% or more in high-risk individuals. Most revolutionary are the emerging genetic therapies that could potentially correct cancer-causing mutations before cancer develops, essentially eliminating hereditary cancer risk entirely. The timeline for these advances is accelerating at a pace that consistently surprises even experts in the field. Treatments that were experimental 5 years ago are now standard care. Therapies that seemed impossibly futuristic a decade ago are now in clinical trials. The National Cancer Institute predicts that by 2035, cancer mortality rates will have declined by 50% from current levels. Some optimistic projections suggest that by 2050, cancer could join the ranks of diseases like polio and smallpox that we remember as historical curiosities rather than current threats. But cancer is just one member of the quartet of diseases that account for most human deaths. Heart disease, stroke, and neurodegenerative disorders like Alzheimer's disease are also yielding to increasingly sophisticated therapeutic approaches. Cardiovascular disease, which kills more people worldwide than any other cause, is being attacked through multiple fronts simultaneously. Gene therapy approaches are showing remarkable promise for inherited heart conditions. Patients with familial hypercholesterolemia, a genetic condition that causes extremely high cholesterol levels and heart attacks in young adults, are being treated with single injection therapies that can lower cholesterol by 60% or more for months or years. Early results suggest that one treatment might provide lifelong protection against heart disease in people with this condition. Regenerative medicine approaches are showing equally impressive results. Stem cell therapies can now regenerate damaged heart muscle after heart attacks, potentially restoring normal heart function in patients who would previously have faced progressive heart failure and death. Some of the most advanced approaches involve creating personalized heart patches grown from the patient's own cells, eliminating the risk of immune rejection while providing perfectly matched tissue for repair. Even more futuristic but increasingly realistic are the prospects for growing entire replacement organs. Several research groups have successfully grown functional heart tissue in the laboratory, and while we're still years away from growing complete replacement hearts, the progress has been steady and accelerating. In the nearer term, bioengineered blood vessels grown from patient cells are already being used clinically to treat cardiovascular disease, providing perfect matches that integrate seamlessly with the patient's existing circulatory system. Stroke prevention and treatment have undergone similar revolutions. Advanced brain imaging can now identify people at high risk for stroke years or decades before it occurs, creating opportunities for preventive interventions. New clot removal devices can restore blood flow to the brain even hours after a stroke begins, dramatically reducing disability and death. Neuroprotective drugs that prevent brain cell death during strokes are showing promise in clinical trials, potentially eliminating much of the permanent damage that strokes typically cause. Neurodegenerative diseases present perhaps the greatest challenge, but even here the progress has been remarkable. Alzheimer's disease, which affects more than 50 million people worldwide and has no effective treatments, is finally beginning to yield to sophisticated therapeutic approaches. Several drugs that can slow or halt the progression of Alzheimer's disease have shown success in clinical trials, and some appear to reverse certain aspects of cognitive decline. The key breakthrough has been understanding that Alzheimer's disease begins decades before symptoms appear. By the time people develop memory problems, massive amounts of brain damage have already occurred. But new biomarker tests can detect Alzheimer-related brain changes 20 years or more before symptoms begin, creating a window of opportunity for preventive interventions. Some of the most promising approaches involve clearing the toxic protein accumulations that characterize Alzheimer's disease before they cause irreversible brain damage. Others focus on enhancing the brain's natural repair mechanisms or protecting vulnerable neurons from damage. Still, others involve replacing damaged brain circuits with new neurons grown from stem cells. The timeline for these neurodegenerative disease treatments is more uncertain than for cancer or heart disease, partly because the brain is more complex and partly because clinical trials take longer when you're measuring cognitive changes rather than tumor shrinkage. But most experts predict that effective Alzheimer's treatments will be available within the next decade, and some believe that Alzheimer's prevention will be routine within 20 years. What's particularly remarkable about all these advances is how they're beginning to converge and reinforce each other. The same genetic engineering techniques being developed for cancer treatment are being adapted for heart disease and neurodegeneration. The stem cell technologies being used to repair damaged hearts are being modified to regenerate brain tissue. The precision medicine approaches that tailor cancer treatment to individual genetic profiles are being extended to other diseases. This convergence suggests that we're not just making incremental progress against individual diseases, but developing a comprehensive toolkit for maintaining human health that could potentially eliminate most causes of premature death. The implications are staggering. If cancer, heart disease, stroke, and neurodegenerative diseases can be prevented or cured, human life expectancy could increase dramatically, potentially reaching or exceeding the predictions of longevity researchers. But preventing disease is only part of the longevity equation. Even if we could eliminate all the major killers, we'd still face the fundamental problem of aging itself. This brings us to perhaps the most profound question in all of biology. Why do we age at all? Is aging an inevitable consequence of being a complex biological system, or is it a problem that can be solved through sufficiently sophisticated interventions? The answer to this question has profound implications not just for how long we might live, but for the quality of those extended years. There's no point in living to 200 if the last century is spent in frailty and decline. The goal isn't just to add years to life, but to add life to years, to extend not just lifespan, but health span, the period of life spent in good health and full functionality. Understanding why we age requires diving deep into the molecular machinery of life itself, into the intricate processes that keep our cells functioning, and the ways those processes gradually break down over time. It's a story that takes us from the largest scale organizational principles of life, down to the smallest molecular details, from the evolutionary pressures that shaped aging to the cutting-edge laboratory techniques that might soon allow us to reverse it. For most of human history, aging was simply accepted as an inevitable fact of life, as natural and unchangeable as the progression of seasons or the cycle of day and night. People grew old, became frail and died, and this pattern seemed as fundamental to the human condition as breathing or eating. But science has a wonderful way of challenging assumptions that seem obviously true, and aging has proven to be far more malleable and mysterious than our ancestors could have imagined. The first clue that aging might not be inevitable came from observations of other species. Some organisms, like certain types of lobsters and jellyfish, show no signs of aging at all. They can potentially live forever, barring accidents or disease. Other species, like mayflies, age and die within hours or days of reaching adulthood. Still others, like some trees, can live for thousands of years while maintaining robust health and reproductive capacity. This diversity suggests that aging isn't a fundamental law of biology, but rather a trait that evolution can modify, accelerate, or even eliminate depending on the circumstances. If aging were truly inevitable, we wouldn't see such dramatic variation across species. The fact that some organisms have solved the aging problem means that aging is, in principle, a solvable problem. But why do most organisms, including humans, age at all? The evolutionary logic is actually quite counterintuitive. You might think that natural selection would favour organisms that live forever, that can reproduce indefinitely and pass on their genes for as long as possible. But evolution is more subtle than that. Natural selection primarily acts on traits that affect reproduction during the early years of life, when most individuals are still alive and reproducing. Traits that only matter later in life, after most individuals have already reproduced and died, are largely invisible to evolutionary pressure. This leads to what evolutionary biologists call the disposable soma theory. From evolution's perspective, the body, the soma, is essentially a disposable vessel for carrying genes from one generation to the next. Once reproduction is complete and offspring are raised, there's no evolutionary advantage to maintaining the body in perfect condition. It's more efficient to invest energy in reproduction rather than in indefinite maintenance. This evolutionary logic explains why aging patterns vary so dramatically across species. Species with high mortality rates from predation or disease evolve to reproduce early and age quickly. There's no point in building a body that could last for centuries if most individuals die from external causes within a few years. But species with low external mortality, like large whales or Galapagos tortoises, can evolve slower aging rates because natural selection continues to act throughout their extended lifespans. Humans fall somewhere in the middle of this spectrum. Our ancestors faced significant mortality from predation, disease and accidents, but not so much that extremely rapid aging was advantageous. We evolved to remain healthy and vigorous through our reproductive years and somewhat beyond, long enough to help raise our offspring to independence. But we didn't evolve to remain healthy for centuries, because few of our ancestors lived long enough for such longevity to provide reproductive advantages. Understanding the evolutionary context of aging helps explain why aging occurs, but it doesn't tell us exactly how it occurs at the molecular level. For that, we need to dive into the intricate machinery of cells and examine the various ways that biological systems accumulate damage over time. One of the most important theories of aging focuses on cellular damage accumulation. According to this view, aging occurs because our cells gradually accumulate various types of molecular damage faster than they can repair it. This damage comes from multiple sources: cosmic radiation, toxic chemicals in the environment, byproducts of normal cellular metabolism, random errors in DNA replication and protein synthesis. Young organisms have robust repair mechanisms that can fix most of this damage before it causes problems. But as organisms age, these repair systems become less efficient, and damage begins to accumulate. Eventually, the accumulated damage reaches levels that interfere with normal cellular function, leading to the declining performance we associate with aging. The mitochondria, the tiny powerhouses within our cells that produce most of our energy, are particularly vulnerable to this kind of damage accumulation. Mitochondria have their own DNA, separate from the nuclear DNA that contains most of our genetic information. This mitochondrial DNA is much more susceptible to damage than nuclear DNA. because it lacks many of the protective mechanisms that shield nuclear DNA from harm. As mitochondrial DNA accumulates damage over time, mitochondria become less efficient at producing energy. This leads to a vicious cycle where declining energy production makes it even harder for cells to maintain their repair mechanisms, leading to faster accumulation of damage. Some researchers believe that mitochondrial dysfunction is one of the primary drivers of aging, and that restoring mitochondrial function could significantly slow or reverse aging processes. Another major source of cellular damage comes from telomere shortening. Telomeres are protective DNA sequences at the ends of chromosomes that function like the plastic tips on shoelaces, preventing the chromosome ends from fraying or sticking together. Every time a cell divides, its telomeres become slightly shorter. Eventually, telomeres become so short that the cell can no longer divide safely, leading to cellular senescence or death. Telomere shortening acts like a molecular clock, limiting how many times cells can divide over the course of a lifetime. This mechanism probably evolved as a cancer prevention strategy, since most cancers require unlimited cell division to grow and spread. By limiting cellular replication potential, telomere shortening helps prevent cancer, but it also contributes to aging by gradually reducing the body's ability to replace damaged or worn-out cells. The discovery of telomerase, an enzyme that can rebuild telomeres, sparked considerable excitement about potential anti-aging interventions. Some organisms, including cancer cells and certain types of stem cells, produce telomerase and can potentially divide indefinitely. Researchers are investigating whether safely activating telomerase in normal cells could extend cellular lifespan and slow aging. But aging isn't just about random damage accumulation. There's growing evidence that aging is also partly a programmed process, controlled by genetic switches that actively promote aging and death. This might seem counterintuitive from an evolutionary perspective, but programmed aging could provide advantages at the group or species level, even if it's disadvantageous for individuals. The discovery of genes that control aging has revolutionized our understanding of the aging process. In simple organisms like yeast and worms, researchers have identified single gene mutations that can double or triple lifespan while maintaining health and vitality. The fact that such dramatic life extension can result from simple genetic changes suggests that aging is much more controllable than previously believed. Some of these longevity genes appear to be conserved across species, from yeast to mice to humans. This suggests that the fundamental mechanisms controlling aging are ancient and universal, dating back hundreds of millions of years in evolutionary history. It also suggests that interventions that extend lifespan in laboratory animals might work in humans as well. One of the most important of these longevity pathways involves a protein called mTOR, which stands for Mechanistic Target of Rapamycin. mTOR acts like a cellular growth sensor, promoting cell division and protein synthesis when nutrients are abundant and slowing these processes when nutrients are scarce. Reducing mTOR activity, either through genetic manipulation or with drugs like rapamycin, extends lifespan in numerous species. The mTOR pathway appears to mediate a fundamental trade-off between growth and longevity. When nutrients are abundant, high mTOR activity promotes rapid growth and reproduction but accelerates aging. When nutrients are scarce, low mTOR activity slows growth and reproduction but extends lifespan, presumably preserving the organism until conditions improve. This connection between nutrition and aging helps explain why caloric restriction, eating significantly fewer calories while maintaining adequate nutrition, extends lifespan in almost every species tested, from yeast to primates. Caloric restriction appears to trigger ancient survival mechanisms that slow aging and extend lifespan during times of food scarcity. The challenge for human applications is that the level of caloric restriction required for maximum life extension, typically 20 to 40% below normal intake, is difficult for most people to maintain long term. But researchers are developing drugs that can mimic the effects of caloric restriction without requiring people to drastically reduce their food intake. Another crucial aging pathway involves sirtuins, a family of proteins that regulate cellular metabolism and stress responses. Sirtuins are activated by various forms of cellular stress, including caloric restriction, exercise, and certain plant compounds. When activated, sirtuins promote cellular repair and stress resistance while suppressing inflammation and other aging-related processes. The discovery that certain plant compounds, particularly resveratrol from red wine and various polyphenols from other plants, can activate sirtuins sparked intense interest in developing sirtuin-activating drugs. While early enthusiasm for resveratrol itself has been tempered by mixed results in human studies, second-generation sirtuin activators are showing more promising results in clinical trials. The inflammation theory of aging provides another crucial piece of the puzzle. Chronic low-level inflammation appears to be a common feature of aging across species and is associated with most age-related diseases. This inflammation isn't the acute, beneficial inflammation that helps fight infections and heal injuries, but rather a persistent, harmful inflammation that damages tissues and interferes with normal cellular function. This chronic inflammation, sometimes called inflammaging, appears to result partly from the accumulation of senescent cells, cells that have stopped dividing but remain metabolically active. Senescent cells secrete inflammatory molecules that can damage nearby healthy cells and promote aging processes throughout the body. Remarkably, drugs that can selectively eliminate senescent cells, called senolytics, have shown dramatic anti-aging effects in laboratory animals. Mice treated with senolytic drugs show improvements in multiple measures of health and aging, including increased mobility, improved organ function, and extended lifespan. Some of these effects are so dramatic that old mice treated with senolytics can outperform much younger untreated mice on various measures of physical performance. Human trials of senolytic drugs are underway, with early results suggesting similar benefits in people. The discovery that aging can be partially reversed by eliminating senescent cells has profound implications for our understanding of the aging process. It suggests that aging isn't just the inevitable accumulation of irreversible damage, but includes reversible components that can be addressed with appropriate interventions. This brings us to perhaps the most exciting recent development in aging research: the discovery that aging can be reversed at the cellular level through a process called cellular reprogramming. In 2006, Shinya Yamanaka discovered that adult cells could be converted back into embryonic-like stem cells by introducing just 4 genes, now known as Yamanaka factors. This discovery won Yamanaka the Nobel Prize and revolutionized our understanding of cellular aging and identity. The Yamanaka factors essentially reset the cellular aging clock, converting old, specialized cells back into young, pluripotent cells that can potentially develop into any cell type in the body. This process erases most of the molecular hallmarks of aging, including DNA methylation patterns that accumulate over time, damage proteins, and dysfunctional mitochondria. Initially, cellular reprogramming was primarily used to create stem cells for research and potential therapeutic applications, but researchers soon realized that partial reprogramming, using the Yamanaka factors for shorter periods or at lower levels, could reverse aging markers without fully converting cells back to stem cells. This partial reprogramming could potentially rejuvenate old cells while allowing them to maintain their specialized functions. Early experiments with partial reprogramming in laboratory animals have shown remarkable results. Old mice treated with Yamanaka factors show improvements in multiple organ systems, including enhanced muscle function, improved vision, better cognitive performance, and extended lifespan. In some cases, the improvements are so dramatic that it's difficult to distinguish treated old animals from young animals based on various measures of biological function. Perhaps most remarkably, these reprogramming interventions appear to work even in very old animals, suggesting that aging reversal might be possible even in individuals who have already accumulated significant age-related damage. This challenges the traditional view that aging is a one-way process, and suggests that biological age might be much more malleable than previously believed. Human applications of cellular reprogramming are still in early stages, but the potential implications are staggering. If aging can be reversed at the cellular level, it might be possible to not just slow aging, but actually turn back the biological clock, restoring youthful function to aged organs and tissues. This could transform aging from an inevitable decline into a treatable condition, potentially allowing people to maintain peak physical and cognitive performance for decades or centuries longer than currently possible. The combination of all these approaches, eliminating age-related diseases, removing senescent cells, optimizing longevity pathways, and potentially reversing aging through cellular reprogramming suggests that we're approaching a tipping point in human longevity. Rather than addressing aging piecemeal, we're developing comprehensive approaches that could address multiple aspects of aging simultaneously. The technical challenges of consciousness uploading become even more fascinating when we examine the current state of brain-computer interface technology. Companies like Neuralink, founded by Elon Musk, are developing devices that can read neural signals with unprecedented precision and allow direct communication between brains and computers. While current applications focus on helping paralyzed patients control external devices, the long-term vision is far more ambitious. The first generation of brain-computer interfaces uses electrodes placed on the surface of the brain or inserted into brain tissue to record the electrical activity of neurons. These devices can already allow patients to control computer cursors, robotic arms, and even simple speech synthesis programs using only their thoughts. But the bandwidth of these early systems is extremely limited, capturing perhaps a few hundred neurons out of the billions that comprise the human brain. Neuralink's approach involves implanting thousands of ultra-thin electrode threads, each thinner than a human hair, deep into brain tissue. These threads can potentially record from tens of thousands of neurons simultaneously, providing a much richer picture of neural activity. The company has demonstrated the technology in animals, showing that implanted pigs and monkeys can control computer interfaces with remarkable precision and speed. But even Neuralink's most ambitious current plans involve recording from perhaps 100,000 neurons, still a tiny fraction of the brain's total neural population. To achieve true consciousness uploading, we'd need to capture the activity of all 86 billion neurons, along with the trillions of synaptic connections between them. This represents a scaling challenge that's almost incomprehensible in scope. Yet the exponential improvement in computing technology suggests that such scaling might be achievable within decades, rather than centuries. The number of transistors that can fit on a computer chip has doubled approximately every 2 years for the past 50 years, a trend known as Moore's Law. While Moore's Law is beginning to slow for traditional silicon-based computers, new technologies like quantum computing, optical computing, and neuromorphic chips could continue the exponential trend. Neuromorphic chips are particularly relevant to consciousness uploading because they're specifically designed to mimic the structure and function of biological neural networks. Unlike traditional computers that process information sequentially, neuromorphic chips process information in parallel, just like biological brains. This makes them much more efficient for neural simulation and could potentially allow real-time simulation of human-scale neural networks within a few decades. The software challenges are equally daunting. Even if we could record the activity of every neuron in the human brain, we'd still need to understand how that activity gives rise to consciousness. This requires not just mapping neural connections, but understanding the complex dynamics of neural networks, how patterns of activity flow through the brain and give rise to thoughts, emotions, memories, and subjective experience. Recent advances in artificial intelligence are providing crucial insights into these questions. Large language models like GPT-4 and others have demonstrated that relatively simple neural network architectures, when scaled to sufficient size and trained on vast amounts of data, can exhibit surprisingly sophisticated cognitive abilities. These models can engage in complex reasoning, demonstrate creativity, and even show what appears to be a form of self-awareness. While these AI systems are still far from human-level consciousness, they suggest that consciousness might emerge naturally from sufficiently complex information processing systems. If this is true, then consciousness uploading might not require perfect replication of biological neural networks, but rather the creation of artificial networks that can support similar patterns of information flow and integration. The philosophical implications become even more complex when we consider the possibility of enhancing consciousness during the uploading process. If consciousness is substrate independent, then digital consciousnesses wouldn't be limited by the constraints of biological neural networks. They could potentially think faster, remember more, process information more efficiently, and even experience forms of consciousness that are impossible for biological brains. Imagine having perfect memory, being able to recall every moment of your existence with perfect clarity. Imagine being able to think at superhuman speeds, processing years' worth of contemplation in minutes or seconds. Imagine being able to directly share thoughts and experiences with other consciousnesses, achieving a form of telepathic communication that goes far beyond anything possible with biological brains. These enhancements could transform the nature of consciousness itself, creating forms of subjective experience that are as far beyond current human consciousness as human consciousness is beyond that of simple animals. But they also raise profound questions about identity and continuity. Would an enhanced digital consciousness still be you, or would it be something fundamentally different? The social implications of consciousness uploading are equally profound. If only some people choose to upload their consciousness while others remain biological, we could see the emergence of two distinct branches of humanity, digital and biological. These two branches might develop different values, different capabilities, and different approaches to existence. Over time, they might diverge so dramatically that they're no longer recognizably the same species. There are also questions about equality and access. Consciousness uploading technology, at least initially, would likely be extremely expensive and available only to the wealthy. This could create unprecedented forms of inequality, where the rich achieve digital immortality while the poor remain trapped in biological bodies subject to aging and death. Such disparities could destabilize societies and create new forms of class conflict. The legal and ethical frameworks for digital consciousness are virtually non-existent. Would digital consciousnesses have the same rights as biological humans? Could they own property, vote in elections, enter into contracts? If multiple copies of the same consciousness exist, which one has legal standing? If a digital consciousness commits a crime, how could it be punished? These questions will need to be answered as consciousness uploading technology approaches practical reality. Religious and spiritual communities are grappling with equally challenging questions. Many religious traditions hold that humans have souls that are distinct from their physical bodies. If consciousness can be uploaded to digital substrates, what happens to the soul? Do digital consciousnesses have souls? Can souls be copied or transferred along with consciousness? Different religious traditions are likely to reach different conclusions, potentially creating new forms of theological conflict. Despite these challenges, the development of consciousness uploading technology continues to accelerate. Several companies and research organizations are actively working on different aspects of the problem, from improved brain scanning technology to better neural simulation software to more sophisticated brain-computer interfaces. While true consciousness uploading may still be decades away, the intermediate technologies being developed could have profound impacts on human capabilities and society. Brain-computer interfaces could allow people to enhance their cognitive abilities by directly connecting their brains to artificial intelligence systems. This could enable superhuman memory, accelerated learning, instant access to vast databases of knowledge, and enhanced problem-solving abilities. In many ways, these technologies could provide many of the benefits of consciousness uploading without requiring the complete transfer of consciousness to digital substrates. The timeline for these developments remains uncertain, but most experts believe that significant brain-computer interface capabilities will be available within the next 20 to 30 years. Full consciousness uploading may take longer, but the intermediate steps could be transformative in their own right. We may be approaching a future where the boundary between human and artificial intelligence becomes increasingly blurred, where biological and digital cognition merge into something entirely new. Meanwhile, as researchers work toward the distant goal of digital immortality, medical scientists are achieving remarkable victories against the diseases that have plagued humanity throughout history. The pace of progress in cancer treatment, in particular, has accelerated to the point where oncologists are beginning to use words like cure for diseases that were considered hopeless just a few years ago. The revolution in cancer treatment goes far beyond the CRISPR gene editing we discussed earlier. Immunotherapy, the approach of harnessing the body's own immune system to fight cancer, has evolved into an incredibly sophisticated toolkit of interventions that can be precisely tailored to each individual patient and their specific cancer. Checkpoint inhibitors represent just the beginning of the immunotherapy revolution. These drugs work by removing molecular breaks that prevent immune cells from attacking cancer, but they only work in about 20 to 30% of patients. Scientists have been working intensively to understand why some patients respond dramatically, while others see no benefit, and this research has led to the development of combination therapies that can expand the population of patients who benefit. One promising approach involves combining checkpoint inhibitors with vaccines that train the immune system to recognize specific cancer proteins. These vaccines are created by analyzing the genetic makeup of each patient's tumor, identifying proteins that are unique to the cancer cells, and then creating personalized vaccines that teach the immune system to target those specific proteins. Early trials of these personalized cancer vaccines have shown response rates of 60 to 80% when combined with checkpoint inhibitors, far higher than either approach alone. Another breakthrough involves CAR T-cell therapy, the approach we mentioned earlier where patients' immune cells are genetically modified to better attack cancer. The first generation of CAR T therapies worked well against blood cancers but struggled with solid tumours, which have sophisticated defences that keep immune cells from infiltrating the tumour. But newer generations of CAR T cells are being engineered to overcome these defences. Some of the most advanced CAR T cells are designed to secrete molecules that break down the physical barriers around tumours, allowing immune cells to penetrate deep into the cancer mass. Others are engineered to be resistant to the immunosuppressive signals that tumours use to shut down immune responses. Still others include safety switches that allow doctors to control their activity, reducing the risk of severe side effects. The results from these advanced CAR T therapies are remarkable. Patients with pancreatic cancer, one of the most lethal forms of cancer, are showing complete responses to treatment. Brain cancer patients who are given weeks to live are experiencing long-term remissions. Children with leukemia that had relapsed multiple times are being cured with single treatments. But perhaps the most exciting development is the emergence of what researchers call living drugs, engineered bacteria and viruses that can seek out and destroy cancer cells while leaving healthy tissue untouched. These biological agents can be programmed to produce anti-cancer drugs directly inside tumours, achieving much higher local concentrations than would be possible with traditional chemotherapy while minimizing side effects. Some living drugs are designed to replicate only in the low oxygen environment found inside tumours, ensuring that they don't affect healthy tissues. Others are programmed to respond to specific molecular signals produced by cancer cells, activating their anti-cancer payload only when they encounter their intended targets. Still, others can be controlled remotely using external triggers like ultrasound or magnetic fields, allowing doctors to activate treatment precisely when and where it's needed. The field of precision oncology has evolved to the point where cancer treatment is becoming almost algorithmic. Patients' tumours are analysed using multiple high-tech approaches, including genetic sequencing, protein analysis, immune profiling, and sophisticated imaging. This information is fed into artificial intelligence systems that can predict which treatments are most likely to work for each individual patient. These AI systems are trained on vast databases containing information from hundreds of thousands of cancer patients, including their genetic profiles, treatment histories, and outcomes. By identifying patterns in this data, the AI can make treatment recommendations that are far more precise than what human doctors could achieve based on experience alone. Early studies suggest that AI-guided treatment selection can improve response rates by 30 to 50% compared to standard approaches. The development of liquid biopsies has revolutionized how doctors monitor cancer treatment and detect recurrence. These blood tests can identify circulating tumor DNA at levels as low as 1 cancer cell per million normal cells. This sensitivity allows doctors to detect cancer recurrence months or years before it would be visible on CT scans or other imaging studies. More importantly, liquid biopsies can track how cancers evolve in response to treatment. Cancer is a moving target that constantly develops new mutations and resistance mechanisms. By monitoring these changes in real time through liquid biopsies, doctors can adjust treatment strategies before resistance becomes established, maintaining effectiveness over much longer periods. Some of the most advanced liquid biopsy platforms can detect and analyze individual cancer cells circulating in the bloodstream. These circulating tumor cells can be isolated and grown in laboratory cultures, allowing researchers to test dozens of different drugs to identify the most effective treatments for each patient. This approach, sometimes called a tumor on a chip, could make precision cancer treatment available to patients whose tumors are too difficult to biopsy directly. The prevention side of cancer research has been equally revolutionary. Genetic testing can now identify people at high risk for cancer decades before the disease develops, creating opportunities for intervention while prevention is still possible. For people with BRCA mutations who have extremely high risks of breast and ovarian cancer, prophylactic treatments can reduce cancer risk by up to 90%. But genetic prevention is evolving beyond risk reduction to actual genetic correction. Gene editing technologies are being developed that could potentially eliminate cancer-causing mutations from the germline, ensuring that future generations don't inherit cancer predisposition genes. While germline editing remains controversial and is not yet allowed in most countries, the technical capabilities are advancing rapidly. Somatic gene editing, which modifies genes in specific tissues rather than the germline, is already being tested in human trials. Patients with inherited cancer syndromes are being treated with gene editing approaches that correct cancer-causing mutations in their existing cells, potentially eliminating their cancer risk entirely. Early results are promising, with some patients showing normalization of cancer biomarkers after treatment. The timeline for cancer elimination has become remarkably compressed. Treatments that were experimental 5 years ago are now saving lives in community hospitals. Therapies that seemed impossibly futuristic just a decade ago are now in advanced clinical trials. The National Cancer Institute has set a goal of reducing cancer deaths by 50% by 2030, and many experts believe this target is conservative. Some optimistic projections suggest that by 2040, cancer could join smallpox and polio in the category of diseases that humans have essentially eliminated. This might seem overly optimistic, but the exponential pace of progress in cancer research makes such timelines increasingly plausible. The combination of prevention through genetic screening and intervention, early detection through improved screening technologies, and increasingly effective treatments creates multiple opportunities to interrupt cancer development and progression. Cardiovascular disease is following a similar trajectory. Heart disease and stroke, which together kill more people than any other cause, are yielding to increasingly sophisticated prevention and treatment strategies. The development of new drug classes has been particularly impressive, with medications that can reduce heart attack and stroke risk by 60 to 70% now entering clinical use. PCSK9 inhibitors represent one of the most significant advances in cardiovascular medicine in decades. These drugs work by blocking a protein that interferes with cholesterol removal from the bloodstream, allowing the body to clear cholesterol much more efficiently. Patients treated with PCSK9 inhibitors can achieve cholesterol levels that were previously impossible to reach, even with the most intensive statin therapy. The cardiovascular benefits of these ultra-low cholesterol levels are remarkable. Studies show that patients who maintain LDL cholesterol levels below 25 mg per deciliter, levels that can be achieved with PCSK9 inhibitors, have heart attack and stroke rates that are 80 to 90% lower than the general population. These drugs essentially allow people to achieve the cardiovascular risk profile of children while maintaining adult functionality. Gene therapy for cardiovascular disease has shown equally impressive results. Patients with familial hypercholesterolemia, who have cholesterol levels 3 to 4 times higher than normal due to genetic mutations, can be treated with single injections that lower their cholesterol by 60% or more for 6 months to a year. Some patients achieve normal cholesterol levels for the first time in their lives after decades of ineffective treatment with conventional medications. The gene therapy works by delivering instructions for producing proteins that enhance cholesterol clearance from the bloodstream. Unlike traditional medications that need to be taken daily and often have significant side effects, these gene therapies provide sustained benefits from single treatments with minimal adverse effects. Longer-acting versions being developed could potentially provide lifelong protection from heart disease with single treatments. Regenerative medicine approaches to heart disease are showing remarkable promise for patients who have already suffered heart damage. Stem cell therapies can regenerate heart muscle that was destroyed during heart attacks, potentially restoring normal heart function in patients who would otherwise face progressive heart failure. Some patients have shown improvements in heart function equivalent to gaining 20 to 30 years of cardiac age. The most advanced approaches involve creating patches of heart muscle grown from the patient's own stem cells in laboratory bioreactors. These patches can be surgically implanted over areas of damaged heart muscle, where they integrate with the existing tissue and restore normal function. Early clinical trials have shown that patients receiving these biological patches have significantly better outcomes than those receiving conventional treatment. Even more futuristic but increasingly realistic are the prospects for growing entire replacement hearts. Several research groups have successfully created beating heart tissue in laboratory settings, and while complete heart replacement remains years away, the progress has been steady. In the nearer term, researchers are developing approaches to regenerate damaged heart tissue in place, using growth factors and stem cells to stimulate the heart's own repair mechanisms. Stroke prevention and treatment have undergone similar transformations. Advanced brain imaging can identify people at high stroke risk years before events occur, allowing for preventive interventions that can reduce stroke risk by 70 to 80%. New anticoagulant medications provide better stroke prevention with lower bleeding risks than older drugs, making it safer to treat more patients. Acute stroke treatment has been revolutionized by mechanical clot removal devices that can restore blood flow to the brain even many hours after stroke onset. These devices can be guided through blood vessels to the site of brain clots and physically remove them, often restoring normal brain function within minutes. Patients who would have faced severe disability or death from stroke are now walking out of hospitals with minimal or no deficits. Neuroprotective treatments that prevent brain cell death during strokes are showing promise in clinical trials. These drugs work by blocking the cascade of molecular events that leads to brain cell death, potentially preserving brain function even when blood flow cannot be restored immediately. Combined with clot removal techniques, these approaches could eliminate most of the disability and death caused by stroke. The progress against neurodegenerative diseases has been more challenging but equally remarkable. Alzheimer's disease, which affects more than 50 million people worldwide and has resisted therapeutic intervention for decades, is finally beginning to yield to sophisticated treatment approaches. Several drugs that can slow or halt Alzheimer's progression have shown success in clinical trials, with some appearing to reverse certain aspects of cognitive decline. The key breakthrough has been recognizing that Alzheimer's disease begins 20 to 30 years before symptoms appear. By the time people develop memory problems, massive amounts of brain damage have already occurred, but new biomarker tests can detect Alzheimer-related brain changes decades before symptoms begin, creating a window of opportunity for preventive intervention. Amyloid-clearing drugs, which remove the toxic protein plaques that characterize Alzheimer's disease, have shown the ability to slow cognitive decline when given to patients in early stages of the disease. More importantly, when given to people who have Alzheimer-related brain changes but no symptoms yet, these drugs appear to prevent or significantly delay the onset of cognitive problems. Tau protein therapies, which target another hallmark of Alzheimer's disease, are showing even more promising results. Tau proteins normally help maintain the structure of brain cells, but in Alzheimer's disease they become twisted and toxic. Drugs that can prevent tau protein abnormalities or clear toxic tau from the brain have shown remarkable effects in animal studies and are now being tested in humans. Perhaps most exciting are the emerging approaches that target multiple aspects of Alzheimer's disease simultaneously. Combination therapies that clear amyloid plaques, prevent tau protein toxicity, reduce brain inflammation, and enhance neural plasticity are showing synergistic effects that are far greater than any single intervention alone. The development of blood tests for Alzheimer's disease has revolutionized the field by making early detection much more accessible and affordable. These tests can detect Alzheimer-related brain changes with 90% accuracy, allowing for much earlier intervention and better monitoring of treatment effects. The availability of simple blood tests could enable population-wide screening for Alzheimer's disease, identifying at-risk individuals decades before symptoms appear. Gene therapy approaches to Alzheimer's disease are showing remarkable promise in early studies. Researchers have developed techniques for delivering genes that enhance brain cell survival and function directly to affected brain regions. Some approaches involve introducing genes that produce nerve growth factors, proteins that can stimulate brain repair and regeneration. Others involve delivering genes that enhance the brain's natural clearance mechanisms for toxic proteins. The most ambitious approaches involve using gene editing techniques to correct genetic mutations that cause familial forms of Alzheimer's disease. While these inherited forms of Alzheimer's account for only a small percentage of cases, they provide valuable insights into disease mechanisms and treatment approaches that could benefit all Alzheimer's patients. Stem cell therapies for neurodegenerative diseases are advancing rapidly, with several approaches showing promise for replacing damaged brain cells and restoring function. Researchers have developed techniques for converting skin cells into neurons that can be transplanted into the brain to replace cells lost to disease. Early studies in Parkinson's disease patients have shown that transplanted neurons can survive and function normally, leading to significant improvements in motor function. The convergence of all these advances in cancer treatment, cardiovascular medicine, and neurodegenerative disease therapy creates the possibility of eliminating most causes of premature death within the next few decades. But even if we could prevent all major diseases, we would still face the fundamental challenge of aging itself. The molecular mechanisms of aging are proving to be far more complex and interconnected than early researchers imagined. What initially appeared to be a simple process of wear and tear is actually a sophisticated biological program involving hundreds of genes, dozens of molecular pathways, and complex interactions between different organ systems. Understanding these mechanisms in detail has revealed multiple potential intervention points where aging could be slowed, stopped, or even reversed. The epigenetic theory of aging has emerged as one of the most promising frameworks for understanding how aging occurs and how it might be reversed. Epigenetics refers to changes in gene expression that don't involve changes to the underlying DNA sequence. These epigenetic modifications act like software running on the hardware of our genes, determining which genes are active and which are silent in different cell types and at different times. During development, epigenetic modifications help transform a single fertilized egg into the hundreds of different cell types that make up the human body. A neuron and a liver cell contain exactly the same DNA, but epigenetic modifications ensure that each cell type expresses only the genes appropriate for its function. Throughout life, epigenetic patterns continue to change in response to environmental influences, lifestyle factors, and the passage of time. The aging process appears to involve systematic changes in epigenetic patterns that gradually alter gene expression in ways that reduce cellular function and promote age-related diseases. These changes occur in predictable patterns that are so consistent across individuals that researchers can use epigenetic modifications to estimate biological age with remarkable accuracy. These epigenetic clocks can predict biological age to within a few years, and can detect the effects of interventions that slow or accelerate aging. The discovery that epigenetic changes drive aging suggests that aging might be reversible through epigenetic reprogramming. Unlike genetic mutations, which are difficult or impossible to reverse, epigenetic modifications can be erased and rewritten. This is exactly what happens during cellular reprogramming, where the introduction of Yamanaka factors resets the epigenetic clock and converts old cells back to a youthful state. Partial reprogramming approaches are showing remarkable success in reversing aging in laboratory animals. Mice treated with brief pulses of Yamanaka factors show improvements in multiple organ systems, including enhanced muscle function, improved vision, better cognitive performance, and extended lifespan. The effects are so dramatic that treated old mice often outperform untreated young mice on various measures of physical performance. Importantly, these reprogramming interventions appear to work even in very old animals, suggesting that aging reversal might be possible even after significant age-related damage has accumulated. This challenges the traditional view that aging is an irreversible process, and suggests that biological age might be much more malleable than previously believed. Human applications of cellular reprogramming are advancing rapidly, with several companies developing therapies based on partial reprogramming. The first human trials are focusing on specific organs and tissues, such as the retina and skin, where the effects of treatment can be easily monitored and safety concerns are minimized. Early results are promising, with some patients showing measurable improvements in function. The implications of successful aging reversal would be profound, extending far beyond individual health and longevity. If people routinely live for 150, 200, or even more years while maintaining youthful health and vigor, virtually every aspect of human society would need to be reconsidered. But before we dive into those societal implications, let's explore the remarkable developments happening right now in laboratories around the world, where researchers are not just theorizing about aging reversal but actually achieving it. The Phoenix Protocol, as some researchers have begun calling it, represents perhaps the most extraordinary scientific development in human history, the ability to literally turn back the biological clock and restore youthful function to aged organisms. The story of the Phoenix Protocol begins with a discovery that seemed almost too remarkable to believe. In 2016, researchers at the Salk Institute, led by Juan Carlos Ispizua Belmonte, demonstrated that they could reverse aging in mice using the same Yamanaka factors that had previously been used to convert adult cells into stem cells. But instead of fully reprogramming the cells, they used partial reprogramming, exposing cells to Yamanaka factors for shorter periods and at lower intensities. The results were extraordinary. Mice with progeria, genetic condition that causes rapid aging, showed dramatic improvements in multiple organ systems after partial reprogramming treatment. Their muscle function improved, their cardiovascular health was restored, their cognitive abilities were enhanced, and their lifespan was extended significantly. Most remarkably, many of the changes associated with aging were not just halted, but actually reversed. But let's dive deeper into exactly what these Yamanaka factors are and how they accomplish this seemingly impossible feat of turning back biological time. The four Yamanaki factors, OCT4, SOX2, CLEF4, and CMIC, are transcription factors, proteins that control which genes are turned on or off in cells. These particular transcription factors are normally active during embryonic development, when a single fertilized egg transforms into all the different cell types that make up a complex organism. During normal development, these factors gradually become less active as cells specialize into their final forms. A skin cell, muscle cell, or brain cell no longer needs the pluripotency factors that were crucial during early development. But Yamanaka's Nobel Prize-winning discovery showed that reactivating these factors in adult cells could erase their specialized identity and return them to an embryonic-like state. The remarkable insight that led to the Phoenix Protocol was recognizing that aging might be fundamentally similar to cellular specialization. Just as cells lose pluripotency as they mature from embryonic stem cells into specialized adult cells, they might also lose youthful function as they age. If this is true, then partial reactivation of pluripotency factors might be able to reverse aging without completely erasing cellular identity. The experimental evidence supporting this hypothesis has been overwhelming. When researchers exposed aged cells to Yamanaka factors for brief periods, the cells began to express genes associated with youth while maintaining their specialized functions. Aged skin cells didn't become stem cells, but they began to produce collagen and other proteins at levels typical of young skin cells. Aged muscle cells maintained their contractile function, but regained the regenerative capacity of young muscle. The molecular mechanisms underlying this rejuvenation are extraordinarily complex and beautiful. The Yamanaka factors work by resetting the epigenetic landscape of cells, erasing the molecular marks that accumulate during aging and restoring youthful patterns of gene expression. Think of epigenetic marks as molecular post-it notes attached to DNA that tell cells which genes to express and which to ignore. During aging, these notes become increasingly disorganized, leading to the decline in cellular function we associate with getting older. Partial reprogramming essentially removes many of these aging-related post-it notes, while leaving intact the notes that define cellular identity. This allows cells to regain youthful function without losing their specialized roles. The process is remarkably precise, affecting hundreds of genes simultaneously while maintaining the overall cellular program that makes a muscle cell different from a brain cell. The biochemical pathways affected by partial reprogramming read like a comprehensive catalogue of aging mechanisms. Mitochondrial function improves, with aged mitochondria beginning to produce energy more efficiently and showing reduced signs of oxidative damage. DNA repair mechanisms are enhanced, allowing cells to fix accumulated genetic damage more effectively. Protein quality control systems are restored, enabling cells to eliminate damaged proteins and maintain proper cellular housekeeping. Cellular senescence, the state where cells stop dividing but continue to secrete harmful inflammatory factors, can be reversed through partial reprogramming. Senescent cells treated with Yamanaka factors can resume normal division and lose their inflammatory secretions, effectively removing one of the major drivers of aging from tissues. The autophagy system, which removes damaged cellular components and recycles them for new use, becomes more active after partial reprogramming. This cellular cleanup system tends to decline with age, leading to the accumulation of damaged proteins and organelles. Restoring autophagy function helps cells maintain the molecular cleanliness necessary for optimal function. Even more remarkably, partial reprogramming appears to affect stem cell populations within tissues. Many tissues contain small populations of adult stem cells that are responsible for ongoing repair and regeneration. These stem cells tend to become less active with age, reducing the tissue's ability to maintain itself. Partial reprogramming can reactivate aged stem cells, restoring their youthful regenerative capacity. The timing and dosage of Yamanaka factor exposure are crucial for achieving beneficial effects without causing problems. Too little exposure has minimal effects, while too much can cause cells to lose their specialized identity or even become cancerous. Researchers have spent years optimizing protocols that provide maximum rejuvenation benefits while maintaining safety. Different cell types appear to respond differently to partial reprogramming, with some showing dramatic rejuvenation after brief exposure, while others require longer treatment periods. Skin cells and muscle cells tend to respond relatively quickly, while brain cells and other more specialized cell types may require more carefully calibrated approaches. The delivery of Yamanaka factors to cells represents one of the major technical challenges in translating this research to human applications. The factors are proteins that need to get inside cells to exert their effects, but proteins are large molecules that don't easily cross cell membranes. Researchers have developed multiple sophisticated approaches to solve this delivery problem. Gene therapy approaches involve using modified viruses to deliver the DNA instructions for making Yamanaka factors directly to cells. The viruses are engineered to be safe and to target specific cell types, ensuring that reprogramming factors are produced only where they're needed. Different types of viruses have different properties that make them suitable for targeting different tissues. Adeno-associated viruses, or AAV, are particularly promising for gene therapy applications because they can infect many different cell types without causing disease and can provide long-lasting gene expression. Researchers have developed AAV vectors that can deliver Yamanaka factors to muscle, liver, eye, and other tissues with remarkable precision. Lentiviral vectors, based on modified HIV viruses, can integrate into the cellular genome and provide permanent expression of reprogramming factors. While this integration raises some safety concerns, it also allows for very precise control over factor expression through engineered genetic switches. Messenger RNA approaches, similar to those used in some COVID-19 vaccines, deliver temporary instructions for producing Yamanaka factors without permanently modifying the cellular genome. This approach provides excellent safety, but requires repeated treatments to maintain effects. Lipid nanoparticles can encapsulate either mRNA or proteins and deliver them directly to cells throughout the body. These microscopic fat droplets can be engineered to target specific tissues and can protect their cargo from degradation until it reaches its destination. Direct protein delivery involves purifying Yamanaka factor proteins and finding ways to get them inside cells. This approach avoids genetic modification entirely, but requires sophisticated techniques to make proteins cross cell membranes efficiently. Each delivery approach has advantages and disadvantages that make it more or less suitable for different applications. Gene therapy approaches can provide long-lasting effects, but raise concerns about permanent genetic modification. RNA and protein approaches are safer, but may require repeated treatments. The safety considerations for human applications of partial reprogramming are complex and multifaceted. The same factors that can reverse aging can also promote cancer development if used incorrectly, since cancer cells often share characteristics with stem cells. Any human application must carefully balance potential benefits against these risks. Researchers are developing multiple safety mechanisms to minimize risks while maximizing benefits. Inducible systems allow reprogramming factors to be turned on and off, using external triggers like specific drugs. This provides precise control over the reprogramming process and allows treatment to be stopped immediately if any concerning effects are observed. Tissue-specific targeting ensures that reprogramming factors are active only in intended tissues, reducing the risk of unwanted effects elsewhere in the body. This can be achieved through tissue-specific promoters that drive gene expression only in particular cell types. Dose and timing optimization involves finding the minimum effective exposure to reprogramming factors that provides benefits without causing problems. This requires extensive testing in animal models to establish safe and effective treatment protocols. Monitoring systems can detect early signs of potential problems, such as abnormal cell growth or gene expression changes that might indicate cancer development. Advanced biomarker testing can identify concerning changes long before they become clinically apparent. The first human trials of partial reprogramming technologies are already underway, focusing initially on applications where risks are minimized and benefits can be easily measured. Ophthalmic applications represent an ideal starting point because the eye is relatively isolated from the rest of the body and vision improvements are easy to assess. Several companies are developing reprogramming-based treatments for age-related macular degeneration, the leading cause of blindness in older adults. This condition involves the death of retinal cells that are crucial for central vision. Partial reprogramming could potentially restore these cells or prevent their death, preserving vision in millions of people. Glaucoma, another major cause of blindness, involves the death of retinal ganglion cells that transmit visual information from the eye to the brain. Early studies suggest that partial reprogramming can regenerate these cells in animal models, potentially providing treatments for a condition that currently has no cure. Skin aging represents another promising early application for partial reprogramming. The skin is easily accessible for treatment and monitoring, and improvements in skin function and appearance would provide clear evidence of treatment effectiveness. Several companies are developing topical formulations that could reverse skin aging without requiring systemic exposure to reprogramming factors. The cosmetic applications alone could represent a multi-billion-dollar market, but the real value lies in demonstrating that aging can be reversed safely in humans. Success in skin applications could pave the way for more ambitious systemic treatments that target aging throughout the body. Muscle aging and sarcopenia, the age-related loss of muscle mass and function, represent another promising target for early human applications. Muscle tissue is relatively accessible and responds well to partial reprogramming in animal studies. Treatments that could restore muscle mass and function in older adults would have enormous impacts on quality of life and independence. The progression from localized treatments to systemic whole-body rejuvenation represents the ultimate goal of partial reprogramming research. This would require delivery systems that can reach every tissue in the body while maintaining precise control over the reprogramming process. Intravenous delivery of reprogramming factors could potentially reach all tissues simultaneously, but would require extremely careful dosing and monitoring to ensure safety. Different tissues might require different exposure levels, making systemic treatment more challenging than localized applications. Inhalation delivery could target the lungs and provide systemic exposure through absorption into the bloodstream. The lungs have enormous surface area and rich blood supply, making them an efficient route for systemic drug delivery. Oral delivery would be the most convenient approach for patients, but faces significant challenges in protecting reprogramming factors from digestion and ensuring adequate absorption. Researchers are developing sophisticated formulations that could potentially make oral partial reprogramming a reality. The timeline for human applications varies significantly depending on the specific approach and target application. Localized treatments for eye diseases could reach clinical use within 5 to 10 years, while more comprehensive systemic treatments might require 15 to 20 years of additional development. However, the pace of progress has been accelerating dramatically as more researchers and companies enter the field. Investment in longevity research has exploded in recent years, with billions of dollars flowing into companies developing various approaches to aging reversal. The business models emerging around partial reprogramming are fascinating and diverse. Some companies are focusing on developing specific treatments for age-related diseases, while others are pursuing more comprehensive approaches to aging reversal. Still, others are developing the tools and technologies that other companies will use to develop their own treatments. The regulatory pathway for aging reversal treatments is still being established, as current frameworks are designed around treating specific diseases rather than targeting aging itself. This is creating interesting challenges as companies navigate approval processes for treatments that could affect multiple aspects of health simultaneously. International competition in longevity research is intensifying, with different countries pursuing different strategies and regulatory approaches. Some countries are taking more aggressive approaches to aging research, potentially creating advantages for their populations in accessing life extension technologies. The potential for enhancement beyond normal human capabilities raises additional ethical and regulatory questions. If partial reprogramming can restore youthful function, could it also enhance function beyond normal levels? The possibility of creating super-enhanced humans through biological manipulation adds another layer of complexity to an already challenging field. Research into combining partial reprogramming with other anti-aging interventions is showing promising synergistic effects. When combined with senolytic drugs that remove aging cells, caloric restriction mimetics, or other longevity interventions, partial reprogramming appears to provide even greater benefits than any single approach alone. The development of biomarkers for measuring the effects of partial reprogramming has been crucial for advancing the field. Epigenetic clocks can detect rejuvenation effects with remarkable precision, allowing researchers to optimize treatment protocols and monitor long-term effects. Multiomic approaches that measure changes in gene expression, protein levels, metabolite concentrations, and other molecular markers are providing comprehensive pictures of how partial reprogramming affects cellular function. These detailed molecular profiles are helping researchers understand the mechanisms of aging reversal and identify potential safety concerns. Advanced imaging techniques are revealing how partial reprogramming affects tissue structure and function. Magnetic resonance imaging can detect changes in muscle mass, fat distribution, and organ function. Specialized imaging techniques can measure blood flow, tissue oxygenation, and other physiological parameters that reflect rejuvenation effects. The psychological and social implications of successful aging reversal are as profound as the biological effects. If people can maintain youthful bodies and minds for centuries, how will this affect their sense of identity and purpose? Will extended youth lead to greater risk-taking or more conservative behavior? These questions are beginning to attract attention from psychologists and social scientists. The potential for repeatedly cycling between aging and rejuvenation raises interesting questions about human development and life planning. If people could allow themselves to age naturally to 60 or 70 and then undergo rejuvenation back to 25, they might experience multiple cycles of maturation and renewal throughout extended lifespans. Different cultures and societies might develop different approaches to aging and rejuvenation, potentially creating new forms of cultural diversity based on attitudes toward mortality and life extension. Some societies might embrace radical life extension, while others might choose to maintain more traditional lifespans. The environmental implications of successful aging reversal extend beyond simple population growth to questions about resource consumption, environmental impact, and sustainability. If people live for centuries while maintaining youthful vigor, they might consume resources and produce waste at much higher rates than current populations. However, longer lifespans might also create stronger incentives for environmental protection and sustainability, since people would have to live with the consequences of current decisions for much longer periods. This could drive more long-term thinking about environmental policy and resource management. The prospect of partial reprogramming becoming routine medical treatment represents one of the most significant developments in human history. For the first time, aging might become a treatable condition rather than an inevitable aspect of the human experience. This transformation would affect every aspect of human society and individual life planning. But the real breakthrough came when researchers applied these techniques to naturally aged mice. Even very old mice, equivalent to 80 or 90-year-old humans, showed remarkable improvements after partial reprogramming treatment. Their skin became more elastic, their fur regained its youthful color and texture, their muscles became stronger, their bones became denser, and their cognitive function improved dramatically. Perhaps most astonishing was what happened to their vision. Age-related vision loss, which affects virtually all mammals as they get older, was completely reversed in treated mice. Old mice that had been nearly blind regained vision that was indistinguishable from young animals. When researchers examined their retinas, they found that the aged, damaged tissue had been restored to a youthful state, with new blood vessels, healthy neurons, and normal function. The mechanism behind these remarkable effects involves the resetting of epigenetic markers that accumulate during aging. As we discussed earlier, aging appears to involve systematic changes in gene expression patterns that gradually reduce cellular function. Partial reprogramming erases these age-related epigenetic changes while allowing cells to maintain their specialized identities. Think of it like reformatting a computer that has become cluttered with unnecessary files and corrupted data. The basic programs and files you need remain intact, but all the accumulated junk that was slowing down the system gets cleared away, restoring the computer to peak performance. Partial reprogramming does something similar for cells, clearing away the epigenetic clutter that accumulates during aging while preserving the essential programming that makes each cell type unique. The technical challenges of translating these discoveries to humans are significant, but not insurmountable. The Yamanaka factors are proteins that need to be delivered to cells throughout the body, requiring sophisticated delivery systems that can reach all tissues safely and effectively. Researchers are developing multiple approaches to this challenge, including gene therapy vectors, modified viruses, lipid nanoparticles, and even direct protein delivery systems. One of the most promising approaches involves using messenger RNA, similar to the technology used in some COVID-19 vaccines, to deliver instructions for producing Yamanaka factors directly to cells. This approach avoids the need to permanently modify the genome while still providing the proteins needed for reprogramming. Early studies in laboratory animals have shown that mRNA-based partial reprogramming can achieve similar benefits to other delivery methods. Safety considerations are paramount when developing human applications of partial reprogramming. The same factors that can reverse aging can also promote cancer if used incorrectly, since cancer cells often share characteristics with stem cells. Researchers are developing sophisticated control systems that can precisely regulate the timing, duration, and intensity of reprogramming to maximize benefits while minimizing risks. Some of the most advanced approaches involve creating inducible systems where reprogramming factors can be turned on and off using external triggers like specific drugs or light exposure. This allows researchers to precisely control the reprogramming process, stopping treatment if any concerning effects are observed. Other approaches involve engineering safety switches directly into the reprogramming factors themselves, so they automatically shut down if cells begin to behave abnormally. The first human trials of partial reprogramming are already underway, focusing initially on specific organs and tissues where the effects can be easily monitored and safety risks are minimized. Eye diseases represent an ideal starting point because the eye is relatively isolated from the rest of the body, making it easier to contain any potential adverse effects. Several companies are developing reprogramming-based treatments for age-related macular degeneration, glaucoma, and other vision problems that affect millions of older adults. Skin aging represents another promising target for early human applications. The skin is easily accessible for treatment and monitoring, and improvements in skin function and appearance would provide clear evidence of treatment effectiveness. Some companies are developing topical formulations of reprogramming factors that could potentially reverse skin aging without systemic exposure. But the ultimate goal is whole-body rejuvenation, restoring youthful function to all organ systems simultaneously. This represents a much greater challenge, requiring delivery systems that can reach every tissue in the body while maintaining precise control over the reprogramming process. Several approaches are being developed, including intravenous delivery of reprogramming factors, inhalation systems for lung delivery, and even oral formulations that could make treatment as simple as taking a pill. The timeline for human applications varies depending on the specific approach and target tissue. Localized treatments for eye diseases could be available within 5 to 10 years, while systemic whole-body treatments are likely still 15 to 20 years away. But the pace of progress has been accelerating dramatically, with new breakthroughs happening every few months. Some researchers are exploring even more ambitious approaches to aging reversal: heterochronic parabiosis, the practice of surgically connecting the circulatory systems of young and old animals, has shown that factors in young blood can reverse many aspects of aging in old animals. This has led to the development of young blood transfusions and the identification of specific molecules in young blood that have anti-aging effects. Researchers have identified dozens of proteins, hormones, and other molecules that decline with age and appear to contribute to aging processes. Replacing these molecules through supplementation or gene therapy could potentially reverse many aspects of aging without requiring full cellular reprogramming. Some of these factors are already being tested in human clinical trials with promising early results. Growth hormone replacement therapy has shown modest anti-aging effects in some studies, improving muscle mass, bone density, and skin thickness in older adults. More sophisticated approaches involve replacing multiple hormones simultaneously to restore youthful hormone profiles. Some clinics are already offering comprehensive hormone replacement protocols based on detailed testing of individual hormone levels. Telomerase activation represents another promising approach to aging reversal. As we discussed earlier, telomeres shorten with age and cellular division, eventually limiting the ability of cells to replicate. Activating telomerase, the enzyme that rebuilds telomeres, could potentially extend cellular lifespan and reverse certain aspects of aging. Early studies of telomerase activation in humans have shown promising results, with some patients experiencing improvements in immune function, energy levels, and other measures of health. However, safety concerns remain because telomerase activation could potentially promote cancer development. Researchers are developing sophisticated approaches to activate telomerase selectively in healthy cells while avoiding activation in potentially cancerous cells. The combination of multiple anti-aging approaches could provide synergistic benefits that exceed what any single intervention could achieve. Researchers are beginning to design comprehensive anti-aging protocols that combine partial reprogramming, senescent cell removal, hormone replacement, nutritional optimization, and other interventions. These combination approaches could potentially achieve more dramatic and sustained anti-aging effects than individual treatments. The measurement and monitoring of aging reversal present their own challenges. Traditional measures of health and aging like blood pressure, cholesterol levels, and physical performance provide only limited insight into biological age. Researchers have developed sophisticated biomarker panels that can provide much more precise assessments of biological age and treatment effects. Epigenetic clocks, which measure age-related changes in DNA methylation patterns, can predict biological age to within a few years and can detect the effects of anti-aging interventions with remarkable sensitivity. Some of these clocks can detect biological age changes of just a few months, allowing researchers to quickly assess whether treatments are working. Proteomic analysis, which measures the levels of hundreds or thousands of proteins in blood samples, provides another powerful tool for assessing biological age and treatment effects. Aging involves systematic changes in protein expression patterns, and these changes can be reversed by effective anti-aging interventions. Some companies are developing commercial tests based on proteomic analysis that could allow individuals to monitor their biological age and the effectiveness of anti-aging interventions. Advanced imaging techniques are providing unprecedented insights into how aging affects different organ systems and how anti-aging treatments can reverse these changes. Magnetic resonance imaging can detect age-related changes in brain structure and function, while specialized techniques can measure muscle mass, bone density, fat distribution, and other markers of biological age. The development of artificial intelligence systems for analyzing aging biomarkers is accelerating progress in the field. These AI systems can identify subtle patterns in complex datasets that would be impossible for human researchers to detect. They can also predict which individuals are most likely to benefit from specific interventions and optimize treatment protocols for maximum effectiveness. As these technologies mature and become more accessible, we're approaching a future where aging reversal could become as routine as other medical treatments. Instead of accepting aging as inevitable, people could undergo periodic rejuvenation treatments to maintain youthful function throughout extended lifespans. The frequency and intensity of these treatments would depend on individual factors like genetics, lifestyle, and personal preferences. Some researchers envision a future where people undergo minor rejuvenation treatments every few years, maintaining biological ages of 25 to 35 throughout centuries of life. Others imagine more dramatic approaches where people allow themselves to age naturally to 60 or 70 before undergoing comprehensive rejuvenation back to biological ages of 25, then repeating the cycle indefinitely. The psychological and social implications of such scenarios are profound. How would human psychology adapt to the possibility of living for centuries while maintaining youthful bodies and minds? Would people become more cautious and risk-averse, knowing they have so much more to lose? Or would extended lifespans lead to greater boldness and willingness to take risks, knowing there would be time to recover from setbacks? Relationships and family structures would be transformed in ways that are difficult to predict. If people routinely live for centuries, marriages could last for hundreds of years. Multiple generations of the same family could be alive simultaneously, with great-great-grandparents who appear physically younger than their descendants. The traditional life cycle of education, career, and retirement would become obsolete, replaced by cycles of learning, working, and renewal that could repeat many times over extended lifespans. But the real breakthrough came when researchers applied these techniques to naturally aged mice. Even very old mice, equivalent to 80 or 90-year-old humans, showed remarkable improvements after partial reprogramming treatment. Their skin became more elastic, their fur regained its youthful colour and texture, their muscles became stronger, their bones became denser, and their cognitive function improved dramatically. Perhaps most astonishing was what happened to their vision. Age-related vision loss, which affects virtually all mammals as they get older, was completely reversed in treated mice. Old mice that had been nearly blind regained vision that was indistinguishable from young animals. When researchers examined their retinas, they found that the aged, damaged tissue had been restored to a youthful state, with new blood vessels, healthy neurons, and normal function. The mechanism behind these remarkable effects involves the resetting of epigenetic markers that accumulate during aging. As we discussed earlier, aging appears to involve systematic changes in gene expression patterns that gradually reduce cellular function. Partial reprogramming erases these age-related epigenetic changes while allowing cells to maintain their specialized identities. Think of it like reformatting a computer that has become cluttered with unnecessary files and corrupted data. The basic programs and files you need remain intact, but all the accumulated junk that was slowing down the system gets cleared away, restoring the computer to peak performance. Partial reprogramming does something similar for cells, clearing away the epigenetic clutter that accumulates during aging while preserving the essential programming that makes each cell type unique. These transformations bring us to perhaps the most challenging aspect of the longevity revolution, the question of what happens when death becomes optional for a significant portion of humanity. The demographic, economic, and social implications of dramatically extended lifespans represent challenges that no human society has ever faced before. We're essentially conducting an unprecedented experiment with the basic parameters of human existence, and the outcome could reshape civilization itself. Let's begin with the mathematics of population growth, because the numbers are both stark and unavoidable. Currently, the global population grows by approximately 70 million people each year. This growth comes from the difference between births, roughly 140 million annually, and deaths, roughly 70 million annually. But what happens to these calculations when deaths drop dramatically while births remain constant or even increase? Consider a scenario where medical advances reduce annual death rates by just 50%. Instead of 70 million deaths per year, we might see 35 million. If birth rates remained constant at 140 million per year, annual population growth would increase from 70 million to 105 million people, a 50% increase in the rate of population growth. Now imagine more dramatic scenarios where aging reversal technologies become widely available. If death rates dropped by 80%, annual population growth could reach 120 million people per year. If death rates dropped by 90%, we could see population growth of 130 million people annually, nearly doubling the current rate. These calculations assume that birth rates remain constant, but extended lifespans could actually increase birth rates in several ways. If people remain fertile for much longer periods, they might choose to have children at multiple points throughout extended lifespans. A person living for 200 years might have children in their 30s, again in their 80s, and perhaps again in their 130s, potentially tripling their reproductive output compared to current lifespans. The age structure of populations would shift in ways that have no historical precedent. Currently, the global population pyramid has a relatively broad base of young people and a narrow top of elderly individuals. But in a world where people routinely live for 2 or 3 centuries, this pyramid could invert with far more older individuals than younger ones. Consider the implications for a country where the average lifespan increases from 80 to 200 years. If we assume that people have children between ages 20 and 40, then at any given time, there would be people from 8 different generations alive simultaneously. Great-great-great-great-grandparents could be alive and active alongside their newest descendants, creating family structures of unprecedented complexity. The economic implications of such demographic shifts are staggering and largely unprecedented in human history. Our entire economic system is built around assumptions about working life, retirement, and intergenerational wealth transfer that would become obsolete if lifespans extended dramatically. Currently, people typically work for about 40 years and retire for about 20 years. Social security systems, pension plans, and personal retirement savings are all designed around these timelines. But what happens if people live for 200 years? Should they work for 160 years and retire for 40? Should they alternate between periods of work and leisure throughout their extended lifespans? Should retirement as we know it cease to exist entirely? The implications for wealth accumulation are particularly profound. Under current lifespans, even modest rates of investment return can lead to substantial wealth accumulation over 40-year careers. But what happens when people can invest and accumulate wealth for 150 years instead of 40? The power of compound interest over such extended periods could create wealth disparities that dwarf anything in human history. Consider a simple example. If someone invests $1,000 per year at a 7% annual return for 40 years, they'll accumulate about $200,000. But if they can invest for 150 years at the same rate, they'll accumulate over $400 million. This isn't science fiction. It's basic mathematics applied to extended lifespans. These calculations suggest that successful longevity interventions could create unprecedented concentrations of wealth. People who start investing early in extended lifespans could accumulate fortunes that make current billionaires look poor by comparison. This could lead to new forms of economic aristocracy based not on inheritance or business success, but simply on longevity and time. The labour market implications are equally challenging. Currently, experienced workers eventually retire, creating opportunities for younger people to advance in their careers. But what happens when experienced workers remain productive for centuries rather than decades? A scientist who's been working for 100 years would have accumulated knowledge and expertise that would be almost impossible for younger colleagues to match. This could create new forms of age discrimination where younger people find it nearly impossible to compete with workers who have decades or centuries of experience. Career advancement could become much more difficult, potentially leading to frustration and social tension between different age cohorts. On the other hand, the accumulated knowledge and expertise of workers with century-long careers could drive unprecedented innovation and productivity gains. A researcher who could work productively for 150 years might make discoveries that would be impossible within current career spans. An artist who could develop their craft for centuries might create works of unprecedented sophistication and beauty. The educational implications are equally profound. If people live for centuries, they would need to continuously update their skills and knowledge as technology and society evolve. The current model of front-loading education in youth and then working for 40 years would become obsolete. Instead, people might alternate between periods of learning and working throughout their extended lifespans. Universities and educational institutions would need to completely rethink their approaches to serve populations that remain in education on and off for centuries. Lifelong learning would become not just an ideal, but a practical necessity for remaining relevant in rapidly changing technological and social environments. Career planning would become infinitely more complex if people could pursue multiple careers sequentially over extended lifespans. Someone might be a doctor for 50 years, then return to school to become an engineer for another 50 years, then become an artist for another 50 years. The psychological and practical challenges of managing such extended and varied career paths are difficult to imagine. The housing and real estate implications are fascinating to consider. If people live in the same communities for centuries rather than decades, they might develop much stronger attachments to place and be more willing to invest in long-term community improvements. This could drive different approaches to urban development that emphasize sustainability and long-term livability over short-term profit. Property ownership patterns could change dramatically if people accumulate wealth over centuries. Real estate could become increasingly concentrated in the hands of long-lived individuals who have had centuries to accumulate properties. This could make homeownership increasingly difficult for younger generations or people who haven't lived long enough to accumulate substantial wealth. The environmental implications extend far beyond simple population growth to fundamental questions about resource consumption and environmental impact. If global population doubles or triples, while individual consumption patterns remain constant, the environmental impact could be devastating. Currently, each person in developed countries consumes enormous quantities of energy, water, food, and material goods throughout their lifetimes. If lifespans extend to 2 or 3 centuries, individual lifetime consumption could increase proportionally. A person living for 200 years might consume twice as much energy, produce twice as much waste, and require twice as many resources as someone living for 100 years. Climate change, which is already a massive challenge with current population and consumption levels, could become even more severe if population growth accelerates due to reduced death rates. The carbon emissions from billions of additional people living for centuries could overwhelm efforts to reduce greenhouse gas emissions. However, some researchers argue that longer lifespans could actually improve environmental stewardship. If people expect to live for centuries, they might be more motivated to protect the environment since they would have to live with the consequences of current decisions for much longer periods. This could create stronger incentives for sustainable practices and long-term environmental planning. Resource management would need to be completely reconsidered for a world with dramatically larger populations living for much longer periods. Food production would need to increase dramatically to feed billions of additional people. Water resources already strained in many parts of the world would face unprecedented demand. Energy production would need to expand enormously to support larger populations with extended lifespans. The technological solutions required to support such populations would need to be extraordinary. Vertical farming, desalination, renewable energy, and other technologies would need to be scaled up to levels that currently seem almost impossible. The innovation required to support dramatically extended lifespans might drive technological advances that benefit everyone. Urban planning would face unprecedented challenges in accommodating much larger populations in sustainable ways. Cities would need to become much more efficient and dense while maintaining livability and quality of life. New approaches to transportation, housing, waste management, and energy distribution would be essential. The political implications of dramatically extended lifespans are equally profound and challenging. Democratic systems assume regular turnover of leadership and periodic opportunities for political change. But what happens when political leaders can remain active for centuries rather than decades? If political leaders live for centuries, they could accumulate enormous amounts of experience and knowledge that might make them more effective leaders. On the other hand, they might also become increasingly set in their ways and resistant to change. The balance between experience and fresh thinking would become much more challenging to manage. Voting patterns could change dramatically if older voters represent much larger portions of the electorate. Currently, older voters tend to have different priorities and preferences than younger voters. If people over 65 represent 50% or more of the population, their political preferences could dominate election outcomes for extended periods. Constitutional and legal frameworks would need to be reconsidered for societies where individuals might participate in political processes for centuries. Term limits, age requirements for offices and other political institutions would need to be rethought for extended lifespans. International relations could be affected in unpredictable ways if some countries develop effective longevity technologies while others don't. Countries with longer-lived populations might develop advantages in accumulating knowledge, building institutions, and maintaining continuity in foreign policy. This could create new forms of international inequality and tension. Migration patterns could be transformed if access to longevity technologies varies significantly between countries. People might move to countries that offer better prospects for life extension, creating new forms of migration pressure. Countries with advanced longevity technologies might need to consider immigration policies specifically related to life extension treatments. The social and cultural implications are perhaps the most difficult to predict, but potentially the most profound. Human cultures have developed around assumptions about normal lifespans, family structures, and life cycles that would be completely disrupted by dramatic life extension. Family relationships would become extraordinarily complex if multiple generations of the same family remain alive and active simultaneously. Great-great-grandparents could be contemporaries of their great-great-grandchildren, potentially creating confusion about authority, inheritance, and family roles. Marriage and romantic relationships would face unprecedented challenges if they could potentially last for centuries rather than decades. Current divorce rates suggest that many marriages don't survive even normal lifespans. How would relationships adapt to the possibility of lasting for multiple centuries? Child-rearing and education would be transformed if parents remain active and involved for centuries rather than decades. Parents could potentially guide and support their children throughout multiple centuries of life, creating dependencies and relationships that have no historical precedent. Cultural evolution might slow dramatically if older generations, representing much larger portions of the population, resist changes that younger generations want to implement. Currently, social change often occurs through generational replacement, with new ideas gaining acceptance as older generations pass away. If older generations remain active for centuries, this mechanism for cultural change might become much less effective. Religious and spiritual traditions would face fundamental challenges in adapting to dramatically extended lifespans. Many religious teachings emphasize the temporary nature of earthly existence and the importance of preparing for afterlife. If earthly existence becomes potentially infinite, these teachings might need to be completely reconsidered. Different religious traditions might reach different conclusions about the morality and desirability of life extension technologies. This could create new forms of religious conflict and division within and between different faith communities. The psychological implications of potentially infinite lifespans are difficult to predict but could be profound. Human psychology has evolved around assumptions about mortality that might not apply if death becomes optional. How would people find meaning and purpose in potentially infinite existence? Would unlimited time make life more precious or less valuable? Mental health issues related to extended lifespans could become significant public health concerns. Some people might find the prospect of living forever exciting and liberating, while others might find it overwhelming or meaningless. New forms of therapy and support might be needed to help people adapt to the possibility of indefinite existence. The distribution of longevity technologies could become one of the most important equity issues in human history. If life extension treatments are expensive and available only to the wealthy, we could see the emergence of biological castes, where the rich achieve near immortality, while the poor remain subject to normal aging and death. Such disparities could be more profound and permanent than any inequality in human history. Currently, wealth differences between rich and poor, while significant, are ultimately limited by the fact that everyone faces the same ultimate fate. But if the wealthy can achieve biological immortality, while the poor cannot, these differences could become literally permanent. The social stability implications of such extreme inequality are difficult to predict but could be severe. Societies have historically been able to maintain stability, despite inequality, partly because the ultimate equality of death provided a form of cosmic justice. If this ultimate equality disappears, social cohesion could be severely threatened. Some countries might choose to subsidize longevity treatments as public health interventions, viewing them as essential services that should be available to all citizens regardless of ability to pay. Other countries might allow market forces to determine access, potentially creating new forms of inequality between different populations. International competition could emerge around access to longevity technologies, with countries competing to attract residents by offering better access to life extension treatments. This could create new forms of geopolitical advantage and disadvantage based on demographic rather than economic or military factors. The timeline for these demographic and social changes depends heavily on how quickly longevity technologies are developed and how widely they're distributed. If effective aging reversal treatments become available gradually and are initially expensive, demographic changes might occur slowly over many decades. If they become available suddenly and are widely accessible, changes could occur much more rapidly. Different scenarios lead to very different outcomes for global population and society. Gradual implementation of longevity technologies might allow societies to adapt slowly to changing demographics. Rapid implementation could lead to more dramatic and potentially destabilizing changes. The management of these transitions will require unprecedented international cooperation and planning. The challenges of dramatically extended lifespans affect all of humanity and will require coordinated responses from governments, international organizations, and civil society. Some researchers have proposed various approaches to managing the transition to extended lifespans. These include population growth controls, resource sharing agreements, international standards for longevity technologies, and coordinated approaches to environmental protection. Others argue that market forces and technological innovation will naturally solve most of the challenges associated with extended lifespans. They point to historical examples of how societies have adapted to previous demographic and technological changes, suggesting that human ingenuity and adaptability will enable successful navigation of longevity-related challenges. The reality is likely to involve elements of both planned management and market-driven adaptation. The scale and novelty of the challenges associated with dramatically extended lifespans will probably require more conscious planning and coordination than previous demographic transitions, but market forces and technological innovation will also play crucial roles in developing solutions. Despite these challenges, many researchers and policymakers believe that the benefits of dramatically extended lifespans would far outweigh the costs. The accumulated knowledge, wisdom, and experience of people living for centuries could drive unprecedented advances in science, technology, art, and culture. Problems that currently take multiple generations to solve could be addressed by individuals working continuously for centuries. The prospect of eliminating aging and death could free humanity from some of its most fundamental constraints and fears. People could pursue long-term projects and goals that are impossible within current lifespans. They could develop expertise and wisdom that takes centuries to accumulate. They could experience the unfolding of history over extended periods rather than brief glimpses. The key will be managing the transition period, when longevity technologies first become available but are not yet universally accessible. This transition could last for decades and will require careful navigation to avoid creating permanent inequalities or social instability. Education and preparation for extended lifespans are already beginning in some communities. Financial planners are helping clients prepare for lifespans of 120 to 150 years. Educational institutions are developing programs for lifelong learning. Healthcare systems are beginning to consider the implications of treating patients for much longer periods. Individual preparation for extended lifespans involves not just financial and health planning, but psychological and social preparation as well. People need to think about how they would want to structure centuries of life, what goals and projects they might pursue, and how they would maintain meaning and purpose over such extended periods. Population dynamics would be fundamentally altered if death rates declined dramatically while birth rates remained constant. The global population, which currently grows by about 70 million people per year, could begin growing much more rapidly if people stop dying at current rates. Even modest improvements in lifespan could lead to population increases that would strain resources and infrastructure in unprecedented ways. Consider the mathematics of population growth in a world where average lifespans increase from roughly 80 years to 200 years. If birth rates remained constant, the global population could double or triple within a century, reaching 20 to 30 billion people. Such population levels would require fundamental changes in how we produce food, generate energy, manage waste, and organise societies. The age structure of populations would shift dramatically, with far more older adults relative to children and young adults. Currently, people over 65 represent about 10% of the global population. In a world where people routinely live to 200 while maintaining health and vigour, people over 65 could represent 50% or more of the population. This would require complete rethinking of economic systems, social structures, and political representation. Traditional retirement systems would become obsolete if people remained healthy and productive for decades or centuries beyond current retirement ages. The idea of working for 40 years and then retiring for 20 years makes no sense if people live for 200 years. New models would need to emerge, perhaps involving multiple careers, extended periods of education and retraining, or entirely different approaches to organising productive activity. Economic implications would be equally profound. If people live for centuries, they could accumulate wealth over much longer periods, potentially leading to unprecedented levels of inequality. A person who invests wisely for 200 years could accumulate fortunes that dwarf anything possible with current lifespans. This could create new forms of aristocracy based on longevity rather than birth or achievement. The labour market would be transformed if experienced workers remained productive for centuries rather than decades. Young people entering the workforce would compete not just with their peers, but with workers who have accumulated decades or centuries of experience. This could make it much more difficult for young people to establish careers and accumulate wealth, potentially creating intergenerational conflicts of unprecedented intensity. Innovation and progress might be affected in complex ways. On one hand, if talented researchers and inventors could work productively for centuries, they might achieve breakthroughs that would be impossible with current lifespans. Einstein or Newton working for 200 years might have made discoveries that would transform our understanding of the universe. On the other hand, extended lifespans might reduce the incentive for innovation if there's less urgency to achieve goals within limited timeframes. Social and political systems would face enormous challenges adapting to populations where individual lifespans span multiple centuries. Democratic systems assume regular turnover of leadership and periodic opportunities for change. If political leaders could remain active for centuries, it might become much more difficult to adapt to changing circumstances or replace ineffective leadership. Cultural evolution might slow if older generations, representing much larger portions of the population, resist changes that younger generations want to implement. Currently, social change often occurs through generational replacement, with new ideas gaining acceptance as older generations pass away. If older generations remain active for centuries, this mechanism for cultural change might become much less effective. Environmental implications would be enormous if global population doubled or tripled while consumption patterns remained constant. Climate change, resource depletion, habitat destruction and pollution could accelerate dramatically if many more people consume resources for much longer periods. This could necessitate fundamental changes in how we organise economic activity and manage natural resources. However, some researchers argue that these challenges are not insurmountable and might even drive beneficial changes. Higher population densities could make many technologies more efficient, from public transportation to renewable energy systems. Longer lifespans could increase incentives for environmental protection if people expect to live with the consequences of current decisions for centuries rather than decades. The distribution of longevity technologies could become one of the most important equity issues in human history. If life extension treatments are expensive and available only to the wealthy, we could see the emergence of biological castes where the rich achieve near immortality, while the poor remain subject to normal aging and death. Such disparities could destabilize societies and create conflicts more intense than any in human history. Some countries might choose to subsidize longevity treatments as public health interventions, while others might restrict access to control population growth or maintain social stability. This could lead to new forms of international competition and conflict, with longevity-enhanced populations potentially having advantages in economic and military competition. Migration patterns could be transformed if some countries offer better access to longevity technologies than others. Currently, people migrate primarily for economic opportunities or to escape violence and persecution. In the future, access to life extension technologies could become a primary driver of migration, with people moving to countries that offer the best prospects for extended lifespans. Religious and philosophical perspectives on mortality and the meaning of life would be challenged in fundamental ways. Many religious traditions emphasize the temporary nature of earthly existence and the importance of preparing for afterlife. If earthly existence becomes potentially infinite, these teachings might need to be reinterpreted or could lose relevance entirely. The psychological impact of potential immortality is difficult to predict. Some people might find the prospect of living forever exciting and liberating, while others might find it overwhelming or meaningless. Mental health issues related to the prospect of indefinite existence could become significant public health concerns. Legal systems would need to adapt to scenarios where crimes could have consequences lasting for centuries rather than decades. If someone commits fraud that takes 50 years to fully resolve, and both the perpetrator and victims live for centuries, how should justice be administered? Property rights, inheritance laws, and contractual obligations would all need to be reconsidered for a world where parties to agreements might remain active for centuries. Family law would face unprecedented challenges if marriages and parent-child relationships could last for centuries. Current legal frameworks assume that most relationships will be resolved by death within a century or less. If people remain active for centuries, new legal frameworks would be needed to address relationship changes over such extended periods. Despite these challenges, many researchers believe that the benefits of dramatically extended lifespans would far outweigh the costs. The accumulated knowledge, wisdom, and experience of people living for centuries could drive unprecedented advances in science, technology, art, and culture. Problems that currently take multiple generations to solve could be addressed by individuals working continuously for centuries. The prospect of extended lifespans is already influencing how people think about education, career planning, and life goals. Young people increasingly recognize that they might live much longer than their grandparents and are planning accordingly. This includes maintaining physical and mental health, developing skills that will remain valuable over extended periods, and building financial resources to support much longer lifespans. Educational systems are beginning to adapt to the prospect of extended lifespans by emphasizing lifelong learning and adaptability rather than front-loading education in youth. If people work productively for centuries, they will need to continuously update their skills and knowledge as technology and society evolve. This could lead to more flexible and distributed approaches to education that continue throughout extended lifespans. Financial planning is being revolutionized by the prospect of extended lifespans. Traditional retirement planning assumes working for about 40 years and being retired for about 20 years. If people work for 150 years and are retired for 50 years, completely different financial strategies would be needed. Some financial advisors are already helping clients plan for lifespans of 120 to 150 years. The insurance industry is grappling with the implications of dramatically extended lifespans. Life insurance policies would need to be completely restructured if people routinely live for centuries. Health insurance would face unprecedented challenges if people require medical care for much longer periods. New types of insurance might emerge to cover risks associated with extended lifespans, such as the possibility of outliving financial resources or the need for multiple career transitions. Real estate and urban planning are beginning to consider the implications of populations that might remain in the same locations for centuries rather than decades. If people live in the same communities for centuries, they might develop much stronger attachments to place and be more willing to invest in long-term community improvements. This could drive different approaches to urban development that emphasize sustainability and long-term livability. Investment patterns could change dramatically if people have centuries to build wealth rather than decades. Long-term investments that take decades to mature could become much more attractive if investors expect to be around to benefit from them. This could drive more capital toward infrastructure, research, and other investments that have very long payback periods but potentially enormous benefits. The implications for human potential are perhaps the most exciting aspect of dramatically extended lifespans. If people can remain healthy and productive for centuries, the level of expertise and accomplishment they could achieve is almost unimaginable. Mozart, who died at 35, produced an extraordinary body of work in his short life. Imagine what he might have accomplished if he had lived for 200 years while maintaining his creative abilities. Scientific and technological progress could accelerate dramatically if researchers could work productively for centuries rather than decades. Complex problems that currently require multiple generations of researchers could be solved by individuals working continuously for centuries. The accumulated knowledge and expertise of researchers working for centuries could drive breakthroughs that are impossible with current lifespans. Artistic and cultural achievements could reach unprecedented levels if creators could develop their skills and vision over centuries rather than decades. Writers could produce bodies of work spanning centuries, developing narrative complexity and artistic sophistication that would be impossible with current lifespans. Musicians could explore musical possibilities over centuries, potentially creating new forms of musical expression. Personal relationships could develop depth and complexity that is impossible with current lifespans. Friendships lasting for centuries could achieve levels of understanding and connection that are difficult to imagine. Romantic relationships could evolve through phases and transformations that span centuries, potentially developing into forms of partnership that transcend current categories. The prospect of living through centuries of historical change could provide perspectives on human development that are currently impossible. Individuals could witness and participate in technological, social, and cultural transformations that currently span multiple generations. This could lead to new forms of wisdom and understanding about human nature and social development. Personal growth and development could continue for centuries rather than being compressed into a few decades of adult life. People could explore multiple interests, develop diverse skills, and pursue various life paths sequentially over extended lifespans. Someone could be a scientist for 50 years, an artist for 50 years, a teacher for 50 years, and an entrepreneur for 50 years, developing expertise in multiple domains. The question of what to do with centuries of healthy life represents both an opportunity and a challenge. Some people might find endless possibilities exciting and energizing, while others might struggle with the burden of making meaningful choices over such extended periods. New forms of psychological support and life guidance might emerge to help people navigate the challenges and opportunities of extended lifespans. As we consider these transformative possibilities, it becomes clear that we're standing at the threshold of changes that could redefine what it means to be human. The combination of disease elimination, aging reversal, and potentially consciousness uploading could transform the human condition in ways that are difficult to fully comprehend. But for individuals living today, the practical question becomes how to position themselves to benefit from these emerging technologies and what they can do now to increase their chances of living to see these transformations. The final chapter of this longevity revolution involves practical strategies that people can implement today to maximize their chances of reaching the point where more advanced interventions become available. This is what researchers call the bridge strategy, using currently available approaches to health and longevity to build a bridge to future technologies that could provide indefinite life extension. The foundation of any longevity strategy must begin with the fundamentals that we know work today. Despite all the exciting developments in cutting-edge anti-aging research, the basics of healthy living remain crucial for maximizing both lifespan and health span. These fundamentals create the biological foundation that future interventions can build upon. Cardiovascular health represents perhaps the most important component of any longevity strategy. Heart disease remains the leading cause of death globally, and maintaining cardiovascular health throughout life is essential for reaching advanced ages in good condition. This involves not just avoiding heart attacks and strokes, but maintaining optimal cardiovascular function that can support healthy aging across all organ systems. Exercise represents one of the most powerful interventions available for promoting longevity and healthy aging. Regular physical activity affects virtually every system in the body, improving cardiovascular function, maintaining muscle mass and bone density, enhancing cognitive performance, reducing inflammation, and supporting immune function. The evidence for exercise as a longevity intervention is so strong that some researchers consider it the closest thing we have to a fountain of youth. But not all exercise is equally beneficial for longevity. The most effective exercise programs combine cardiovascular conditioning, strength training, flexibility work, and balance training in ways that support healthy aging across multiple domains. High-intensity interval training appears to be particularly beneficial for longevity, providing cardiovascular benefits that exceed those of moderate-intensity exercise while requiring less time commitment. Strength training becomes increasingly important with age as muscle mass and bone density naturally decline. Maintaining muscle mass throughout life is crucial, not just for physical function but for metabolic health, as muscle tissue plays important roles in glucose regulation and overall metabolism. People who maintain muscle mass and strength throughout life have significantly lower risks of age-related diseases and maintain independence much longer than those who lose muscle mass. Nutrition science has evolved to provide much more sophisticated guidance for optimizing health and longevity. While basic principles like eating plenty of fruits and vegetables and avoiding processed foods remain important, emerging research is revealing more specific nutritional strategies that can promote healthy aging. Protein intake becomes particularly important with aging, as the body becomes less efficient at utilizing dietary protein for muscle maintenance and repair. Older adults may need significantly more protein than current recommendations suggest to maintain muscle mass and function. Some research suggests that distributing protein intake throughout the day, rather than concentrating it in large meals, may be particularly beneficial for aging adults. Intermittent fasting and time-restricted eating have emerged as promising interventions for promoting healthy aging. These approaches appear to activate cellular repair mechanisms and stress response pathways that can improve health span and potentially extend lifespan. Several different approaches to intermittent fasting have shown benefits, from alternate day fasting to more moderate time-restricted eating patterns. The timing of food intake may be as important as the composition of the diet. Eating large meals late in the day can disrupt circadian rhythms and metabolic function, while eating earlier in the day appears to support optimal metabolic health. Some research suggests that eating the largest meal earlier in the day and having smaller meals later can improve metabolic markers and potentially support healthy aging. Nutritional supplementation represents a complex but potentially important component of longevity strategies. While most nutrients should ideally come from food sources, certain supplements have shown promise for supporting healthy aging. These include omega-3 fatty acids for cardiovascular and cognitive health, vitamin D for bone health and immune function, and various antioxidants for cellular protection. More cutting-edge supplements target specific aging pathways that we discussed earlier. NMN and NR, precursors to NAD+, may support mitochondrial function and cellular energy production, resveratrol and other sirtuin activators may mimic some of the benefits of caloric restriction. Spermidine and other autophagy enhancers may support cellular cleanup and repair mechanisms. Sleep optimization represents one of the most underappreciated but crucial components of any longevity strategy. Poor sleep quality and insufficient sleep duration are associated with increased risks of virtually every age-related disease, from cardiovascular disease and diabetes to cognitive decline and cancer. Optimizing sleep may be one of the most powerful interventions available for promoting healthy aging. Sleep quality tends to decline with age due to changes in circadian rhythms, hormone levels, and brain function. But many of these changes can be mitigated through appropriate interventions. Maintaining consistent sleep schedules, optimizing sleep environments, managing light exposure, and addressing sleep disorders can significantly improve sleep quality throughout life. Stress management becomes increasingly important for healthy aging as chronic stress accelerates aging processes and increases disease risks. Chronic stress leads to persistent elevation of cortisol and other stress hormones that promote inflammation, suppress immune function, and accelerate cellular aging. Effective stress management techniques can help mitigate these effects and support healthy aging. Meditation, mindfulness practices, and other contemplative techniques have shown remarkable benefits for both mental and physical health. Regular meditation practice can reduce inflammation, lower blood pressure, improve immune function, and potentially slow cellular aging. Some research suggests that long-term meditation practitioners show slower brain aging and better preserved cognitive function. Social connections and meaningful relationships represent crucial but often overlooked components of longevity strategies. People with strong social networks and meaningful relationships live longer and healthier lives than those who are socially isolated. Maintaining and cultivating relationships throughout life may be as important for longevity as diet and exercise. The mechanisms behind the health benefits of social connections are complex, but appear to involve reduced inflammation, better stress management, improved immune function, and enhanced motivation for healthy behaviours. People with strong social networks are more likely to engage in healthy behaviours and seek medical care when needed. Cognitive stimulation and lifelong learning may help maintain brain health and cognitive function throughout extended lifespans. The brain shows remarkable plasticity throughout life, and engaging in challenging cognitive activities can help build cognitive reserve that protects against age-related cognitive decline. Learning new skills, engaging in complex problem-solving, and maintaining intellectual curiosity may help preserve cognitive function into advanced age. Regular medical monitoring and preventive care become increasingly important as anti-aging technologies develop. Early detection and treatment of age-related diseases can significantly improve outcomes and may help people remain healthy long enough to benefit from emerging longevity interventions. This includes not just routine screening, but also more advanced monitoring of biomarkers related to aging and age-related diseases. Genetic testing can provide valuable information for personalizing longevity strategies. Testing for genetic variants associated with increased disease risks can inform decisions about screening, prevention, and lifestyle modifications. As our understanding of longevity genetics improves, genetic information may become increasingly valuable for optimizing individual longevity strategies. Environmental optimization involves minimizing exposure to toxins and pollutants that can accelerate aging and increase disease risks. This includes both obvious toxins like tobacco smoke and more subtle exposures like air pollution, pesticides, and endocrine-disrupting chemicals. Creating clean, healthy living and working environments may become increasingly important as people strive to maintain health over extended lifespans. The psychological and motivational aspects of longevity strategies are often underestimated, but may be crucial for long-term success. Maintaining motivation for healthy behaviours over decades or centuries requires different approaches than short-term health improvements. Developing sustainable habits, finding meaning and purpose in healthy behaviours, and maintaining optimism about the future may be essential for long-term adherence to longevity strategies. Financial planning for extended lifespans represents a crucial practical consideration. If people live for 150 to 200 years, they will need financial resources to support much longer periods of life. This requires different investment strategies, career planning, and risk management approaches than traditional retirement planning. The concept of longevity escape velocity suggests that people who can remain healthy long enough may benefit from continuously improving longevity technologies. Each year that someone survives in good health provides another year for scientific advances that could further extend their lifespan. This creates a positive feedback loop where longer lifespans provide more opportunities to benefit from future advances. For people alive today, the goal is to use currently available strategies to remain healthy long enough to benefit from the remarkable technologies that are likely to become available within the next few decades. The bridge strategy involves implementing the best current approaches to health and longevity, while staying informed about emerging technologies and positioning oneself to benefit from future advances. The timeline for various longevity interventions continues to accelerate, with some technologies likely to become available much sooner than originally predicted. Senolytic drugs for removing aging cells could be available within 5 to 10 years. Partial cellular reprogramming for specific organs might be available within 10 to 15 years. More comprehensive anti-aging interventions could become available within 20 to 30 years. This timeline suggests that people who are currently middle-aged or younger have excellent prospects for benefiting from transformative longevity technologies. Even people who are currently older may live long enough to benefit from some of these interventions, particularly if they focus on maintaining health through currently available approaches. The convergence of multiple anti-aging strategies, from disease prevention and aging reversal to consciousness uploading and beyond, suggests that we may be approaching a future where aging and death become optional rather than inevitable. For the first time in human history, a generation may be born that never experiences aging or death from natural causes. This possibility transforms how we think about life planning, relationships, career development, and virtually every aspect of human existence. The choices we make today about health, education, relationships, and life goals may have consequences that extend for centuries rather than decades. Understanding and preparing for this transformation may be one of the most important challenges and opportunities of our time,